Sati Shahu Education Society. We are very much thankful to him for his constant inspiration, guidance, and sharing his valuable thoughts. Our college is providing education in 3 streams: arts, commerce, and science at undergraduate level, and at postgraduate level, the college has facility of education in MSc Chemistry, MSc Computer Science, and MSc Mathematics. And in the social sciences, the college has a facility of Master of Arts in English, Hindi, Political Science, Economics, and History. And we also have the facility of M.Com. The college is also running 2 professional, that is the job-oriented integrated courses like BSc Biotechnology and BSc Computer Science. The college is also providing a National Service Scheme, NSS, and Earn and Learn scheme for the students who are interested in social activities, and also having 1 platoon of 52 cadets of the NCC. Presently, 4,000 students are taking education in our college at UG, PG level, and in professional courses. The college has well-equipped laboratories, independent and spacious library office with softwares. And the important thing in the education system is the faculty. Our college has highly educated faculty. About 80% of the faculty has acquired the highest degree, that is the PhD. In this COVID-19 pandemic situation, everybody is facing various problems regarding education of students, research activity, medical facility, and to fulfill the day-to-day needs. Being the academic leader of the society, it is the responsibility of all of us working in higher education institution as well as the working in national research institution to suggest the solution to the problem arises, and also you have to work for solving the problem of mankind and nation. Taking all these things in consideration, our institution, particularly our Department of Physics, after consultation with the eminent personality in this field, has decided to request the eminent personality to share their views and research work in the field of material science and nanotechnology with the academicians, researchers, industrialists. With due respect to Honorable Dr. B.B. Kale sir, the Director of Center for Material for Electronic Technology, Pune, the inaugurator of the today's function, Honorable Dr. N.R. Singh sir, Scientist F, Dr. Baba's Atomic Research Center, Mumbai, and my research guide, Honorable Dr. P.M. Jadhav sir, Senior Professor in Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. We have decided to organize these 2 days National E-Conference on recent advances in material science and nanotechnology. I hope that these 2 days of you along with us and our this attempt will prove very motivating in this COVID-19 pandemic situation. Being the convener of this 2-day National E-Conference, I put before you the schedule of the 2 days. Now we have the eminent personality, Honorable Dr. B.B. Kale sir, Director of the CEMET, Pune, Dr. N.R. Singh sir, Scientist F, Chemistry Division, Bhabha Atomic Research Center, Mumbai, Dr. K.M. Jadhav sir, Senior Professor, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. The another invited speakers like Dr. Anurag Gautam sir from Hyderabad, GCET College, Hyderabad, Dr. Manas Srivastava sir, KBT College of Engineering, Nasik. Today, these 3 speakers, along with Honorable Dr. B.B. Kale sir, will deliver their research work before you. And in afternoon session, the college has provided the platform of this research e-conference for the new researcher to present their oral presentation after 2 p.m. For this oral presentation, we have appointed an examiner panel like Nathuram sir, ex-scientist, Dr. Babasaheb Ambedkar, Marathwada University, Aurangabad, Dr. K.B. Modi sir, Professor, Saurashtra University, Rajkot, Gujarat, and Associate Professor, Dr. Murkude sir from Aurangabad. I request them to work as an examiner for the oral paper presentation. And the best oral presentation will be awarded and their names will be declared during the valedictory function tomorrow. With these few words, I also want to clear you that tomorrow there are 3 invited talks like Honorable Dr. B.R. Sankapal sir, Professor, VNIT, Nagpur. Another speaker, Dr. Bhishma Pratap Singh, DST Inspire Faculty, Chemistry Division, Bhabha Atomic Research Center, Mumbai. And the last session of the invited talk will be of Honorable Dr. H.D. Dhole sir, Professor, Department of Physics, Savitribai Phule, Pune University, Pune. And for the valedictory function, the chief guest, Honorable Dr. D.R. Mane sir, V.V. Navarkhele sir, the director of our Rajarshi Shahu Education Society, the guest of honor, Honorable Dr. Srimati Palotkar madam, our vice principal G.N. More sir, and my colleagues will present. All these efforts we are took place or able to provide all the academicians, researchers under the able guidance of our present President of Rajarshi Shahu Education Society, Honorable Nanasaheb Palotkar. He is constantly inspiring us to make the use of the new technology and to come over being the academic leader of this Marathwada region to undertook the various activities that are useful for the academicians, researchers, and industrialists. With these few words, I took my place, but before that, first of all, I would like to congratulate all of you who are joined this 2 days national e-conference on recent advances in material science and nanotechnology. Thanks a lot.
Thank you very much, sir, for your introduction of the college and expressing your thoughts behind the organization of this conference, as well as putting a brief outline of this 2-day conference before the participants. Thank you very much. Now, as I already told all the participants that today we have 2 distinguished guests, Dr. N.R. Singh and Dr. K.M. Jadhav, in this inaugural function. The participants might be eager to listen to their brief introduction. So may I now request my colleague, Dr. Vijay Sanap, to give a brief formal introduction of these 2 guests. Dr. Vijay Sanap.
Thank you, sir. May I audible, sir?
Yes, sir.
Before introducing the guest of today's function, it is my duty to remember Honorable Founder of Rajarshi Shahu Education Society and former Minister of Maharashtra State, a great leader, visionary, late Sri Manikantha Palotkar. He identified the need of society of this region and provided the facility of education and employment for the students of Aurangabad region and especially the rural area of this region. On this occasion, the Honorable Chairperson of inaugural function of 2 days national conference in recent advances in material science and nanotechnology organized by the Department of Physics of Yeshwantrao Chavan College, Skill Road. President of Rajeshri Shahu Education Society, Honorable Prabhakar Rauji Palkar, sir, who always motivate and support us and provide all facilities to organize such events. The inaugurator, Honorable Dr. Yanar Singh from BRC, the keynote addresser, Honorable Dr. Bharat Kale, sir, Director of CIMET, Pune. The guest of honor for today's function, Dr. K.M. Jadhav, sir, Senior Professor from the Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, who guided and supported us for this event, and without whom this event is very difficult for us, as well as the principal of our college and the convener of this conference, Dr. Ashok Pandit, sir. I welcome all the dignitaries and the members and student participants. I welcome all once again. It is a great pleasure for me to introduce the dignitaries present for inaugural function. First of all, I would like to introduce Dr. K.M. Jadhav, sir, without whom such events are difficult to organize. He is the constant source of motivation and encouragement for his students like us. He is the person under the guidance of whom number of students get employed in various fields and their families were settled, which is shown which can be observed through his biodata. He is always ready to guide, support the students. Actually, his name is sufficient for the introduction, but as a part of program, I try to introduce him. Currently, he is working as a senior professor in the Department of Physics of Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. He has nearly 8 years of work experience as well as the administrative experience of 3 years. He has the research experience and teaching experience of nearly 30 years. He had guided number of students, 42 students. That students awarded the PhD, and 8 students are working now. His area of thought is high temperature superconductors, nanofluids, bionanomaterials, glass and ceramics, hollow magnetoresistance material, ferrite thin film, ultrasonic studies of liquid mixture, magnetic nanomaterials, ferromagnetic materials, gamma and laser irradiation, nanoferrites, composite materials, peroxide materials, and so on. So this list is very big. He has published 282 papers in the international journals, 192 papers in the conferences, and total is nearly 500. So its index of citation, it is 4,824. His PH index is 39. He got 4 patents from his work, and he have completed number of research projects sanctioned by UGC, DAE, CSR, as well as DST. He has published 7 books, and the awards received by Jadhav sir. He is elected as fellow of Maharashtra Academy of Science, Pune. He got the Best Research Professor Award in 2017 by Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. He received Bharat Gaurav Award in October 2016 by India International Friendship Society, New Delhi. Rotary Vocational Award he got, as well as Paryavaran Bhushan Puraskar from Bharat Mata Buddha Bahudeshya Samstha Navdurga. He is the life member of research societies like IPA, MSI, IFPT, ISC, USI, MRS, and academic member of various statutory bodies. And by this brief introduction, I will go towards the introduction of second guest. The second guest, that is the inaugurator of today's function. I would like to introduce the remaining personality which we have today. He is Dr. N.R. Singh. He is the source of motivation for young researchers and the students. He is also enthusiastic and down-to-earth personality. Looking at his biodata, so I will introduce him from his biodata now. Uh, Dr. N.R. Singh have done PhD in chemistry from Manipur University in 1994. He finished his PhD in chemistry from IIT Kanpur in the area of magnetic and superconductivity of metal nitrides in 2004. He joined Park Mumbai as scientific officer in 2006. After completion of Dr. K.S. Krishnan Fellowship, he presently working as a scientist F at Chemistry Division, VRC Mumbai. He has got he has did his PhD doctoral fellowship at University of Victoria, Canada. He got a fellow, the National Academy of Science India 2016, also the fellow of Maharashtra Academy of Science in 2013. He got the Scientific and Technical Excellence Award, DAE 2012, and he received Young Achiever Award from SSPS 2010. So he is the motivator for the youngsters. He he publishes about 140 papers in various journals. He reviewed 5 articles, 7 book chapters he also written, and his EH index is 47. Total citation is 6,333, and he is working as a reviewer for many journals. So with these brief words, I introduce today's guest. One more guest we have today, who is the keynote speaker for today's keynote session. So the introduction of Dr. B.B. Kale, who is the director of CMED, will be given in the keynote address. Will be given before the keynote address. So with these few words, the brief introduction of both the personalities, I conclude my speech and request to Professor Pardeshi sir to conduct the next part. Thank you very much.
Thank you very much, sir, for your brief introduction of today's guests. From this introduction, the participants might have got some idea about these two guests, and it is indeed a matter of pride for us that we have two persons Honorable N.R. Singh. Hello, am I audible, sir?
Yes. I'm listening. Yes.
Okay. Yeah. So now we are going to listen to the inaugural address, which is to be delivered by our guest, Honorable Dr. N.R. Singh. So may I now request Honorable Dr. N.R. Singh to begin his inaugural address.
So, good morning.
Good morning, sir.
Yeah. So can I start?
Yes, sir. Yes.
Yeah. Okay.
Welcome,
good morning,
sir.
ladies and gentlemen. Thank you to each and every one of you for being here with us. Today's seminars, e-conference, only since advance in material science and technology 2020. Organized by the Department of Physics, the Southern College of Arts, Commerce and Science, Shillot, Aurangabad District, Maharashtra, India. I'm very happy to present here, and I thank chairperson of this conference, as well as the chairman of the Rajashree Sahu Education Society, Honorable Nana Saheb Babakar. And also, I thank Professor K.M. Jadhav for Jadhav, Dr. BAMU Aurangabad, in presence of this conference. Also, I thank the principal of this college, Dr. Asoke Pandit. And also, I thank our today's the keynote address speaker, Dr. Bibi Kare. And also, I thank the 6 resource persons, the names Dr. Anurag Gautam, Dr. Manas Srivastava, Dr. B.R. Sankarpan, and Dr. B.P. Singh, Dr. S.D. Dhore, and also many participants and attendees. I thank you all to be present with me and in this my inaugural space. Today's the topic conference recent advance in the materials science and technology is the appropriate titans of this society. Materials science deals with the properties of materials, their application to the various area of science, engineering, and physics. The physics, chemistry, biologists, environmentalians can work together to bring a new interdisciplinary spins. Research can be performed from college level to the university level and the institutional levels. This wind brings new materials. Advanced materials are the materials whose properties or characteristics superior over the traditional materials for particular or targeting applications. Advanced material can be produced by the new synthesis route or modification of the existing ones. Let's take one example, gold nanoparticles. Gold is actually is used in the many ornaments, but they are also non-toxic in our environments. But gold is difficultly used for jewelry since it is extremely soft in its cars or in its steps. Thus, it is alloyed with a certain amount of copper, silver, gold, platinum, nickel as impurity to melt harden. Depending on the amount of above impurity, its color changes from reddish yellow to the green yellow and reddish after dropping of silver or copper. Pure gold has a particle size of microns, and thus it could not be used for the ultrasensing in biological applications. Example, biosensor, diagnosis of a disease, biotechnological environment monitoring, awareness monitoring. We need to sense the particle size and the shape to the nano regions. So we need engineering aspect. After preparation of such nanoparticles, post-processing such the patterning of nanoparticle in the form of film and the surface modification of the functionalization of with the proper ligands and molecules or antibody is necessary. In case of catalysis, catalytic property gold particles change with the size and the shape. And example, spiricant, the nanowires, nanorods, prism, star, coronets, and dictymedium. Every particles can have interesting properties, which are suitable for particular application. But every particle can have interesting properties which are suitable for particular application. But every particle may not have useful in the different area of applications. Engineering aspects are necessary to make the material for a particular applications. Advanced materials can be of the following type: metals, semiconductors, insulator, composite, magnetic, ferroelectric, piezoelectric, shape memory, thermochromic, photochromic, magneto-rheological, smart materials. Interesting properties of metals for a particular application can be brought by the engineering aspect: size, porous defects, combination of other materials through the modification synthesis procedure, post-processing after getting the initial materials. Technology can advantage bring a strategy to regularize the materials for industry society needs. Collaboration among the R&D sector industrial partnership will bring new materials for advanced materials. These advanced materials will be used by the company for the launching of new product which has many features or superior properties and satisfy the many customers so that company achieve the profitability goals. The company has to follow the regulatory and the compliance and sustainability. Scientists, academicians, and engineering need to start innovative ideas which are required for the present and future scope in the area of the environment and fairly sustainability, security, prevention of pathogen microbe, including the today like this one, the coronavirus, in energy in a high value added market. Existing of the advanced patent is the reasons of demand of for the particular application in early stage up to certain stage, but at certain time may become obscure after some time if the new development arises due to the conditions or environment or time. New development may arise due to incidental discovery or modification of the existing methods of technology. Let's take few examples. There are many allotropes of carbon. Diamond is one of the allotropes of carbon. Has insulating properties in electrical conductivity, high hardness, high thermal conductivity, and has been used for cutting, polishing tool, and even sand for high pressure applications. Carbons in the carbon having the sp2 hybridization in the diamonds. Diamonds are found in art. Depending upon the demand of its users, its colors need to be modified. Fancy color diamond is highly encountered by the purchasers. Only 0.01 natural diamond are colors. This color can be brought by the incorporation defects, additional impurities such as nitrogen, boron, others elements. This can be done by scientists. This can be proven by the mini synthesis route. Mini synthesis methods are developed in terms of economic variable and industrial way. So far, a large quantity of diamond is not achieved. The cost of synthesis of diamond is very expensive, but its demand in the market is high. We would like to bring a note to the researchers that the advanced synthesis method is required to provide its demand and requirement in the market. Concepts of material science can bring new synthesis procedure for diamonds in economic way. Initially, graphite was considered as the best material for electrical and thermal conductivity as well as the chemical and thermodynamic stability. Because of these interesting properties, they are useful in electronics products such as the battery, solar panels, electrodes, as well as the factories in the high temperature material processing application in absence of oxygen. Carbon in the graphite is sp2 hybridations. Between the layer, there is a van der Waals force, and that precipitate lubricant properties. This layer is called graphene, which are later prepared in 2004. Two types of hollow carbon molecules are the close case, this is called fluorine or bucking bond, carbon 60, carbon 70. As cylindrical type, this is a nanotube. 1995, carbon 60 fluorine was prepared from the vaporization of graphite load using the laser in the atmosphere helium gas. That was the first time before of the preparation of the nanoside carbon molecules. The fluorine molecules comprise of carbon 36 to carbon 176 with the respective size of 0.5 to 1.2 nanometer. This is the starting of carbon nanotube or carbon nanoparticles. Carbon 60 has a 0.9 nanometer. Carbon 60 atoms has a single and double bonds to form the hollow sphere with a 20 hexagonal and 12 pentagonal faces that like a soccer ball. This molecule can donate accept electron in the reactions. Because of this, they are used many applications such as the battery, catalysis, and nanoelectronics. The addition and substitution reaction can take place in the surface of sphere. Thereby, many derivatives are prepared. These derivatives are used in many applications, including the biosensor, with the addition of alkali metals like lithium, potassium, cesium, rubidium to form the M3 carbon 60. It is a superconductivity up to 40 K. 1991, carbon nanotube was prepared in the carbon arc discharge, which was similar to those prepared to prepare the fluorine molecules. There are two types of carbon nanotube. One type is considered single one carbon nanotube, which is composed of the half of the fluorine case attached to the end of the tube or hollow cylinder and flat graphene, which roll up into the nano-sized hollow cylinder. Single one carbon nanotube exhibit a ballistic transport rather than conducting electricity via the electron transport and a fast rotating movement around the hollow tube. Another type is the multi-carbon nanotube, which have the multiple layers of the carbon over the inner layers. Amongst the layers, there are van der Waals forces. Carbon atoms undergoes mixture of sp2, sp3 hybridization. Such carbon nanotube shows the enhanced film emission properties have been used as a tube in the STM and the FM. It has that high thermal conductivity, high electrical conductivity, high tensile strength, high Young's modulus of electricity. Because of the above properties, it brings an advanced scope in different area of material science. Small-sized nanotube are used in medicines, medical science, and neurosensor and nanoemitter, etc. Many researchers are thinking to develop carbon fibers, single layers, brand graphene without loading since 1960. In graphitic integration compound, graphene layers can function as either the acceptor electrons from the or donation of the electron to the integrated space. Examples are the mentioned are potassium graphite is donor graphite integration compound, whereas the bromine graphite is the acceptor compound. With the progress of material science, new atoms of carbon, such as graphene atomic layers, was prepared by mechanical exploration of the small mesas of graphite in 2004 in the UK globe. The graphite is of a 2D matrix with a new layers, few layers obtained sp2 sp3 sp2 chemical bond. It is interesting properties such as the high electrical conductivity, high thermal conductivity, like metallic denser, strong M bipolars, electric field effect, and room temperature mobility. Now, graphene other derivatives and composites have been prepared by different graphite fluid and post-processing emulsion. Thus, new development of materials for the different applications have been found. Our neurostructure, silicon, load, hollow, star shape, bell shape, and also many iron oxide, epitope, silicon-based this coarse structure and the neurostructure ministry has prepared. Many nanoparticles have been used as catalysis neurocarriers for drug contrast agents in MRI, heat generator in the hyperthermal-based treatment, magnetic-based separation for bacteria, toxic ions and compounds, etc. For every device and application in its synthesis stages, post-processing, so that this can be utilized in an economic way. Environmental friendly, surface modification, and modification particle and suitable functioning globe is important in designing material for this. So ceramic materials, such as glass, fibers, are very important in materials view. So maintaining hard magnetic materials is useful to prepare the different defense purpose. So the preparation of the different shape of the ceramics is one of the challenging in materials view. Polymer are important in bringing the durability, lightweight, flexible properties of materials. Composite hybrids are important materials which can have more properties than individual ones. Biomaterials are the materials which change hand care in better ones. Laser-based synthesis, fabrication, fine-tuning techniques, atomic layer deposition, high-purity single constant preparation, 3D, 4D printing are important new challenging in the material science field. In addition to above materials, engineering of shape, size, coordinates, and dimensionality of the particles, post-processing will be required to bring new materials. Advanced materials can be grouped into the following one on the basis of performance: high performance, ceramics, alloys, carbon-based materials, lightweight, high hardness, high strength, high temperature, high pressure, high radiation, extreme conditions, energy, fluorescent, battery, solar, photovoltaic, additive manufacturing, 3D 14 printing, nanomaterials, and nanostructure and nanoengineering. And the semiconductor-based integrated circuit is used in computer and mobile robotics, biomaterial, drug delivery, repairing of DNA and RNA to the nanocarriers, replacement of bone and teeth, smart materials, sensor, actuator materials, and that sense the electric environment condition or stimuli say mechanical and chemical and electrical and magnetic signal. Environment, material for recovery, reuse of the substance, environment friendly, harmless, and to the environment and eco-friendly. Surface coating and surface engineering of the materials for the materials or particles, thin film to enhance stability and the multi-utility. Material works, material processing technology important, it is shape. And joining, and join means welding and joining is very important. This is the one of the challenges in the today. Durability, flexibility, polymer base, rubber base, resistant to the any fatigue and thermal effect, multifunctional, hybrid, and composite and core cell materials. Greens, economic way of the resource, then environmental friendly, light amplification, laser rated cutting, drilling, drawn, outcompensation photonics, laser-based devices in electric optics, magnetic optics, healthcare, industry security, laser surface, green optimization, and chemical reactions, patterning, fine-tuning, and marking and communication, printing, lithography, sensor and guiding, and heat generation, mounting purpose. These are important area of the material science. So with this view of this something, I think that scientists and academicians, engineers need to start innovative idea to bring the new materials. So today, I think that many resource persons has going to give their own just research area, and many presenter will present. I hope that this will be new success of this conference because of your presence. With this word, I thank you all for attending my talk. Thank you.
Thank you very much, sir. Your inaugural address will definitely acquaint the researchers about the recent developments and advancements in the field of material science and technology. Sir, I once again express my gratitude towards you for your speech. Now it is time to turn to another resource person, that is Dr. K.M. Jadhav. Dr. K.M. Jadhav is a senior professor from Dr. Babasaheb Ambedkar Marathwada University, and it will be an academic feast for all of us to listen to the thoughts of Dr. K.M. Jadhav. So may I request Dr. Jadhav to share your ideas with us?
Sure.
Dr. Jadhav, sir, am I audible, sir?
Yeah, I am all.
Okay. Welcome, sir, welcome.
Hello.
Hello, welcome, sir. Sir, please begin your address.
Yes.
Okay.
Screen where this account. I am visible on screen. Hello.
Yes.
Yes, sir. Yes.
Hello.
Yes, sir. You are visible, sir.
I am visible. Okay.
Yes, sir.
Okay.
Please go ahead.
Yes. Good morning to one and all who are present attending this e-conference organized by the Yashwantrao Chauhan College, Sillot, Department of Physics. Honorable Sri Nana Sahib Palotkar Sahib, the chairperson of this college. Honorable Dr. B.B. Kale, the director, CIMET, Central Institute of India, Pune. My friend from BRC, Dr. Raghumani Singh. The other speakers in these conferences, Dr. Sangpal sir, Dr. Bhishma Pratap Singh, and others. Convener of this conference, the principal Ashok Pandit, my student, Dr. Sanab, the co-convener of this conference, and the chairman of this IQAC cell of this college. Dear participants, very warm welcome to all of you for joining me and listening me. Now, the conference is organized on the topic of recent advances in the material science and the nanotechnology. Material science is nothing but a very huge field. It is an interdisciplinary field in which one scientist or the researchers from various groups, that is from physics, chemistry, mathematics, biology, engineering, can work together and invent or discover the new material with better properties and for suitable application. So in short, to define the material science, it is an interdisciplinary field involving the properties of matter and its application to various areas of science and engineering. The science was exist long back. It was not started just like nanoscience and nanotechnology. The material science is very old from the mankind. The tools, weapons, and the appliances need in the history of human civilization. In early age, there was archery, there was a sword. So all these are made up of various kinds of material. So the tools, weapons, and appliances needs in the history of human civilization categorize predominant material ages as Stone Age, Bronze Age, Iron Age, like this. So there were, with the invention of the new material, there was a different ages so far. The material science is one of the leading science. It is a branch of the science, and most of the researchers throughout the country are working in the field of material science. It has 5 aspects for the material science. It all deals with the various kinds of materials. So importantly, the first is the processing of these materials, the manufacturing of this material, the preparation of these materials. Various materials need different preparation procedure. For example, glass can be prepared by the melt quenching technique, whereas other materials in the form of bulk can be prepared by the ceramic technology. If you want a material to be in nanoscale dimension, then you need to have adapt wet chemical process. So the first part of this material science is the processing of the material, and it is very important because through the processing we can get an homogeneous, chemically stable and a high quality of the material. Then the second part of the material science is the characterization of the material. The prepared material should be characterized by some techniques like thermal gravimetry analysis or X-ray diffraction or scanning electron microscopy or infrared spectroscopy. So many techniques are now being developed and they are used for the characterizing the material. So characterization is a very important part of the material science. Through these characterization techniques, we should be able to know the structure of the material, whether it is a cubic, whether it is a tetragonal, whether it is a hexagonal, it is a monoclinic, rhombohedric, all these to be determined through the various characterization technique. So structure is very, very important. That is the third aspect of the material science. Then after characterizing the material, we should understand the properties of that material. All the materials will not exhibit the same properties. Some material will exhibit the optical properties, some will exhibit the electrical properties, some will exhibit the magnetic properties, some will exhibit the other properties. Some of them materials are exhibit both the properties like ferrite, which can have the electrical properties as well as magnetic properties. So different materials are available and all these materials exhibit different properties. So we must study these properties. We must understand their behavior under the influence of electrical field or magnetic field or optical. So depending on our application, we should study the properties of the material. And lastly, the performance of this material. Once we investigate their properties, then we have to see their suitability for a particular application. We have to explore them for a desired application, because ultimately when we prepare the material, we have to use it for some of devices, and therefore their performance is also must. So in short, the material science has a five aspects: the processing, characterization, structure, properties, and performance. As the material science deals with the various materials, so the materials are classified into four categories. They are basically the metals, polymers, semiconductors, and ceramics. Now, what we mean when we say the material? When we say the metals, it means that we have the aluminum, copper, steel, nickel, titanium, like that. When we say it is a ceramic, so it is a clay, it is a silica glass, it is a alumina or quartz, like these. So these are the examples of the ceramic. Similarly, for the polymers, we have polyvinyl chloride, Teflon, various plastics, glue, Kevlar, etc. The composite materials, the wood, carbon fiber, resin, concrete, all these are the examples of this composite. So metal, plastic, ceramics are the basically the types of the material. The basis of all material science involves relate the desired properties and relative performance of a material in a certain application to the structure of the atoms and phases in that material through characterization. In the recent years, material, fundamental material science has been propelled nanoscience and nanotechnology to the forefront at many universities and research organizations. So recently, the nanotechnology has given some new ideas for this material science. Now, nanotechnology, as all you know that nanoscience and nanotechnology, but still in brief, I'll give you what is nanotechnology. Nanotechnology is a manipulation of matter on atomic, molecular, and supramolecular scale with at least one dimension size from 1 to 100 nanometer. So it all deals with the structures whose size lie between 1 to 100 nanometers. You all know this is nanoscience or nanotechnology. Nanotechnology, including diverse fields of science such as surface sciences, organic chemistry, molecular biology, semiconductor physics, energy storage engineering, microfabrication, and molecular engineering. So many subjects are involved in the nanotechnology and nanoscience. Nanoscience made us possible the direct control of matter on atomic scale, which has created new approaches based upon molecular self-assembly from developing new materials with dimension in the nanoscale. So it deals with the material on the atomic scale size. Now, why we must study the nanoscience and nanotechnology? It is because that the study of fundamental principles of nanostructures between bulk and atomic properties lead us to the nanoscience, and the application of nanostructure into the useful devices leads to the nanotechnology. Nano is very interesting. The nanomaterials or nanoparticles are very interesting. The particles are very small. It has a high surface to volume ratio. They react differently, act differently, interact with light differently, are on the scale of small biological structure. So it can match or compatible with the small structure, biological structure of the size of the nanoscale. So these are the advantages of this nanoparticle. The quantum mechanics meet the classical mechanics. All the concepts of the behavior of the nanomaterial can be explained on the basis of the quantum mechanics. It is interesting that new structures can be formed. Nanomaterials are interesting material with nanoparticles embedded in it. Now, all of you will say that this nanoscience and nanotechnology was recently been developed. It is not like this. Though the Richard Feynman put his idea in 1959, and since then we start saying the nanoscience and nanotechnology, but it was exist from the long back from the history. But that time there were no tools or no equipment available to know the size of the material or the particle, and that's why we don't know the nanoscience nanotech. But it was present. In the 500 to 1400, there was a stained glass. These are the examples of the nanomaterial. 800 to 1600 nanoparticles is in pottery. Then in 1200 to 700, Damascus steel swords. As I told that weapons were used, and these weapons like sword are made up from the nanoparticles. They can work from the both sides. In 1910, the particle size described in nanometer. In 1959, the Feynman speech, the principle of physics, as far as I can see, do not speak against the possibility of manufacturing through atom by atom, the manipulating by atom to atom. So Richard Feynman was give a birth to the nanoscience and nanotechnology. Then after 1901, in 1970, the nanotechnology coin was emerged. In 1981, first atom was seen being enrolled through STM. In 1986, engines of creation, the coming age of the nanotechnology by Richard Dexler. So it is very important to study the nanoscience and nanotechnology. The application of nanotechnology is in various fields. It is useful for energy sector. It is usually and commonly used in medicine and drug, nanobiotechnology, nano devices, optical engineering. It is used in defense and security, bioengineering, cosmetics, nanofabrics, even in food and agriculture also it is used. There are different applications of the nanoscience and nanotechnology in different areas. Researchers are working in different areas. Important is that the nanomaterials, they exhibit different properties altogether different from the bulk material. For example, if you take the electrical properties, then we'll observe that the band gap increases as particle size decreases. So to increase the band gap for a desired application or for a particular devices, then we must reduce the size of the particle, and it is possible through the nanoscience and nanotechnology. So this is one of the example of the properties, how the properties can be changed by the nanoscience and nanotechnology. Now, in India, the nanotechnology, many researchers are, various groups are working, almost all of them are working in the field of nanoscience or nanotechnology. In IIT Mumbai is the premium organization in the field of nanotechnology. Research in the field of health, environment, medicines are still going on. Starting in 2001, the government of India launched the nanoscience and nanotechnology initiatives. So, looking to the importance of this nanoscience and nanotechnology, the government of India has also created a new department of nanoscience and nanotechnology. In 2007, the nanoscience and nanotechnology mission was initiated with an allocation of rupees 1,000 crores for a period of 5 years. So big investment was made by the government of India in the field of nanotechnology. What is the main objective of the government or of this nanotechnology? The main objective of the nano mission are basic research promotion, that is to promote the basic science researches, infrastructure, development for carrying out front-ranking research, development of nanotechnologies and their application, human resource development, and international collaboration. So, government is spending a lot of money in the development of the nanotechnology. Nanotechnology may make it possible to manufacture lighter, stronger, and programmable material that require less energy to produce than conventional material and that promise greater fuel efficiency in land transportation, ships, aircraft, and space vehicles. So you see that how the nanotechnology is useful in the various sectors of the life. The future of the nanotechnology could be include the use of nanorobotics. These nanorobotics have the potential to take on human tasks as well as the tasks that humans could never complete. The rebuilding of the depleted ozone layer could potentially be able to be performed. So one of the future application of this nanotechnology is the nanorobotics. You will see in the COVID hospital, it is not possible for a common man to enter, or people are avoiding to reach the patient. So in that case, the robots are useful to help the patients in the COVID situation. There would be an entire nanosurgical fields help cure everything from natural aging to diabetes to bone spurs. There would be almost nothing that could be repaired with the introduction of nanosurgery. So these are the future development of the nanoscience and nanotechnology, or it may be possible. In summarizing, the study of material science and nanoscience and nanotechnology is of great importance to many researchers as it deals with the various kinds of material, their synthesis, their properties and applications in newer fields. So large number of researchers throughout the world are working in the field of material science. The inception of the nanoscience and nanotechnology in the field of material science has accelerated the research on new materials with improved properties. The nanoscience and nanotechnology has motivated many young researchers to work in the field of material science. The progress or the development of the nation depends on the invention of new materials for various applications. Due to the COVID-19 pandemic situation, it is not possible to organize the conferences, seminar, workshop, etc. in physical manner. So, in order to avoid the crowding, it is the e-commerce or e-seminar are now being practiced by many colleges or many researchers. So this e-seminar or e-conference will be helpful to interact the researchers and to present their work in front of the expertise in the field. So I hope that the college, the Yashwantrao Chauhan College, Shillod, has organized this e-conference and it will be very useful for all the scientific community. I hope all the participants who have joined this e-conference will enjoy the two-day e-conference on material science and nanotechnology. They will get benefited by the resource persons, by their talks of the research person. The research persons of this seminar are from the different areas, from the National Institute as well as from the universities, and they have vast experience in the field of nano science and nanotechnology. I request all of you to take the benefit and enjoy this 2 days conference organized by this Yashwantrao Chauhan College, Shillod. Lastly, before concluding my talk, I am grateful to the Secretary, Sri Nana Sahib Ji Palatkar, the principal Ashok Pandit, Dr. Sanap, Datta Kakade, and other team members of this college who taken a lot of effort in organizing this conference. I expect there is a grand success for this conference, and give my best wishes to all the participants who are joined this conference. With this word, I would like to conclude myself. Thank you very much for giving me the opportunity to be interact in this 2 days conference organized by your college. Thank you very much.
Thank you very much, sir. Honorable Dr. K.M. Jadhav, sir, made a studious commentary on the nature and scope of material sciences and nanotechnology in a very lucid language. Sir, I am obliged to you for your invaluable guidance. Now, before going ahead, I want to make an important announcement. The Department of Physics has received more than 70 abstracts, and we have made a compilation of these abstracts in a PDF format. This PDF format will be available in our college website, and we shall send it to all the participants on their email also. But for the time being, may I request Dr. N.R. Singh to virtually inaugurate this PDF compilation. We shall share the screen from our side. Please wait for a few seconds. We are going to share the screen of this PDF compilation of 17 abstract papers.
Yeah, it's very nice. This is one of the wonderful conference, this abstracts. Yeah, one by one by the sea. Yeah.
So this is the compilation of abstract paper, abstract book.
Okay, very good. Yeah. So I inaugurated this function.
Okay, sir.
Thank you for all. I welcome all participants for attending this conference.
Thank you very much, sir.
Yeah. Thank you. Yeah.
So now we are going towards the conclusion of this inaugural function. So may I now request the President of Rajarshi Shahu Education Society, Honorable Shri Prabhakar Rao Palodkar, to share his thoughts with the participants. Honorable Shri Prabhakar Rao Palodkar.
आमच्या राजर्षी शाहू शिक्षण संस्थेच्या संचलित असलेल्या यशवंतराव चव्हाण महाविद्यालयाने आयोजित केलेल्या या राष्ट्रीय कॉन्फरन्समध्ये राष्ट्रीय कॉन्फरन्स जी आयोजित केली परिषद, त्या परिषदेचे उद्घाटक डॉक्टर NR सिंग, भामाणू संशोधन केंद्र मुंबई, ज्यांच्या मार्गदर्शनाखाली बऱ्याच वेळेस आमचे कोणत्या ना कोणत्या निमित्तानं संबंध आलेले असतात, आदरणीय डॉक्टर BB काळे साहेब, संचालक सेंटर फॉर मटेरियल्स ऑफ इलेक्ट्रॉनिक टेक्नॉलॉजी पुणे, डॉक्टर बाबासाहेब आंबेडकर मराठवाडा विद्यापीठाचे ज्येष्ठ शास्त्रज्ञ आणि प्राध्यापक डॉक्टर M साहेब, आज भौतिकशास्त्र विभागाचा आम्हाला सातत्याने या महाविद्यालयाला मार्गदर्शन त्यांच्या निमित्तानं फार मोठ्या प्रमाणात होत असतं. त्याचप्रमाणे या महाविद्यालयाचे प्राचार्य डॉक्टर अशोक पंडित सर आज या महाविद्यालयामध्ये जी परिषद आयोजित केली त्या निमित्तानं ज्या सर्वांनी आपल्या याच्यामध्ये सहभाग नोंदवला ते सर्व शास्त्रज्ञ, प्राध्यापक, आमच्या या भौतिकशास्त्र विभागाचे सर्व प्राध्यापक, त्यांचे सर्व सहकारी, उपस्थित बंधू आणि भगिनींनो, यशवंतराव चव्हाण महाविद्यालयाबद्दल प्राचार्य पंडित सरांनी आपल्याला संपूर्ण माहिती दिलेली. एक डोंगराळ अशा भागामध्ये असलेला हा पूर्वीचा मागास तालुका, जिथं 10वीचं शिक्षण सुद्धा घेता येत नव्हतं, त्या काळामध्ये आमचे वडील माणिकराव दादा पालोदकर साहेबांनी ज्यावेळेस राजकीय क्षेत्रामध्ये आपलं स्वतःच योगदान द्यायची सुरुवात केली आणि त्या निमित्तानं राजर्षी शाहू शिक्षण संस्था 1971 मध्ये स्थापन केली. स्थापन झाल्यानंतर विविध शाळा आणि महाविद्यालय, त्यामध्ये सिल्लोड सारख्या तालुक्याच्या ठिकाणी हे यशवंतराव चव्हाण महाविद्यालय स्थापन केलं. आणि या महाविद्यालयामध्ये आजची जर बघितलं आपण, त्यावेळेसचा असलेला आर्ट, नंतर कॉमर्स, नंतर सायन्स, आणि आज मात्र आम्ही BSc आणि बायोटेक इथपर्यंत या महाविद्यालयावर शिक्षणाची व्यवस्था करण्याचा प्रयत्न आमच्या वडिलांच्या काळापासून चालत आला, तो करण्याचा प्रयत्न केलेला. आज जर बघितलं या महाविद्यालयामध्ये 9 विविध असलेल्या पदव्युत्तर स्तरावरच्या विषयाचे आज इथं शिक्षण दिल्या जातं. एवढा हे सांगण्याचा उद्देश एवढाच, अशा या ग्रामीण भागामध्ये जिथं सतत आम्ही दुष्काळाचा सामना करतो, त्या दुष्काळाचा सामना करत असलेल्या महाविद्यालय असलेल्या खेड्यापाड्यातील असलेल्या आमच्या 303 खेड्यातील विद्यार्थी आज फार मोठ्या प्रमाणात शिक्षण घेतात. आणि हे शिक्षण घेत असताना हा ग्रामीणचा असलेला आमचा सगळा विद्यार्थी यांना मात्र कसं उच्च शिक्षण देता येईल या निमित्तानं प्रयत्न सातत्यानं आमचे प्राचार्य आणि प्राध्यापक करत असतात. आणि यातूनच आमच्या विद्यार्थ्यासहित आमचे प्राध्यापकांना कुठेतरी परिषद घेऊन कुठेतरी मार्गदर्शन व्हावं, आणि म्हणून त्या दृष्टीनं अशा परिषदाला आम्ही सातत्याने आयोजित करत असतो. यामध्ये आज आपल्या पुढे फार मोठं एक देशाच्या समोर संकट आलेलं आहे. जागतिक स्तरावरचं संकट आहे कोविड-19च्या निमित्तानं. आणि अशा वेळेस आपण एकत्र येऊ शकत नाही, आणि म्हणून आधुनिकतेची काळ धरलेला आपला देश, यामध्ये आता या परिषदा आपण आज एक वेगळ्या टेक्नॉलॉजीच्या रूपाने घेऊ लागलेलो. खरं म्हणजे ज्यावेळेस एकत्र आपण सगळे समूहानं येतो, त्यावेळेस वैयक्तिक चर्चा आणि त्या सगळ्या बदल घडवत येत असतात. पण दुर्दैव या जागतिक स्तरावरच्या या संकटाला समोर जात असताना फार मोठ्या आपल्याला जरा किंमत मोजावं लागलेली. आज दरडोई जर पाहिलं तर भारताचा आजचा रेट जर बघितला तर इकुरीचा रेट कोविड-19चा 63.73 आलेला आहे. ह्याचा अजून आपल्याला पुढे कसा वाढ करता येईल या दृष्टीनं शास्त्रज्ञ आणि आमचे आरोग्य आणि सरकार फार मोठं प्रयत्नशील आहे. याच्यात बऱ्याच मोठ्या प्रमाणात यश येऊ लागलेलं आहे. पण आजच्या विषयाला संबंधित धरून आज जो आपण विषय इथं भौतिकशास्त्राच्या निमित्ताने ठेवला, तो रिसेंट ऍडव्हान्सेस इन मटेरियल सायन्स आणि नॅनो टेक्नॉलॉजी. नॅनो टेक्नॉलॉजी तर फार दिवसापासून आलेले वेगवेगळ्या क्षेत्रामध्ये आपण काम करतात, सर्व शास्त्रज्ञ काम करतात. भारतामध्ये जर आज आपल्याला पुढे जायचं असेल तर सगळ्यात मोठं आपल्याला जर रिसोर्सेस निर्माण करायचे असेल तर औद्योगिक क्षेत्रामध्ये करावं लागेल. हे आम्हाला सगळ्यांना याची जाणीव आहे. आणि म्हणून त्यामध्ये नॅनो टेक्नॉलॉजी किती मोठ्या प्रमाणात आपल्याला नवीन पद्धतीने ऍड करता येईल याचा विचार करणं हा देशाच्या आणि राज्याच्या हितानं आपल्याला सगळ्यांना त्या निमित्तानं पाहायला मिळेल. आज आपण पाहिलं कोविड-19चं संकट. आज अनेक आपल्याला आजपर्यंत कोणती लस जागतिक स्तरावर निर्माण झालेली, फक्त काही डिक्लेअर केले, काही दिवसात येणार. याच्यामध्ये सुद्धा आपल्याला आरोग्य याच्यामध्ये जर याचा कुठं उपयोग होत असेल तर त्या दृष्टीनं आपण सगळ्यांचे पर्याय सुचवण्याचा प्रयत्न या निमित्तानं केला पाहिजे. हे संकट आता फार मोठ्या प्रमाणात 2 संकट सध्या आपल्या देशावर आहे. जागतिक स्तरावरचं कोविड-19 आणि दुसरं संकट शेजारच्या देशाला चीननं आज आपल्या भारताच्या बॉर्डरवर केलेली अस्थिर परिस्थिती. म्हणजे या मागचा सांगायचा हेतू की याच्यात सुद्धा आपल्याला आपल्या संरक्षण करण्याच्या दृष्टीनं देश पातळीवर या नॅनो टेक्नॉलॉजीचा विचार करून जर पुढे काही आपल्याला जाता आलं, आपल्या सर्व शास्त्रज्ञांना या निमित्तानं काही सुचवता आलं तर त्याचा सुद्धा सरकार गांभीर्याने विचार करावा लागेल. कारण आपण सगळे शास्त्रज्ञ फार मोठ्या प्रमाणात यामध्ये भाग घेतात आणि म्हणूनच आज कुठेतरी आपण प्रगतीपथावर तिसरी महत्वाची बाब जर असेल तर आपल्या देशाची रचना, आज आपला असलेला ग्रामीण भाग उपजीविकेचे साधन म्हणून जर पाहिलं असेल, हा शेती व्यवसाय हा सगळ्यात मोठा आहे. आणि शेती व्यवसायामध्ये आज एवढ्या मोठ्या स्पर्धा आता निर्माण झालेल्या आहे. आपल्या विविध भागामध्ये विविध प्रकारचं वेगवेगळे उत्पादन घेणाऱ्या वनस्पती आहे, फळझाड आहे आणि वेगवेगळ्या प्रकारचे धान्य पिकवणाऱ्याच्या आपल्या त्या प्रदेशामध्ये एक वेगळं आहे. आणि म्हणून त्याच्यामध्ये आपल्याला याचा कसा उपयोग करता येईल, शास्त्रज्ञाच्या दृष्टीने एक फार मोठं आव्हानाचं काम आहे. पण मला वाटतं याच्यावर फार मोठं काम चालू झालेलं आहे आणि हे काम करत असताना याला परत एकदा आपल्याला कसं मुहूर्तमेढ रोवता येईल या दृष्टीनं सुद्धा फार प्रयत्न करण्याची गरज आहे. कारण भारताचा बहुतांश भाग आज जर आपण पाहिलं तर शेतीवर आधारित असलेला आमचा ग्रामीण भागातला सर्व लोकांचा हातभार आहे. आणि याच्यामध्ये आज दरडोई उत्पन्न वाढवायला आता तिसरी हरित क्रांतीची आपल्याला कशी करता येईल आणि त्याच्यामध्ये नॅनो टेक्नॉलॉजीचा वापर हा प्रामुख्यानं कसं करता येईल याही दृष्टीनं आपल्या शास्त्रज्ञांनी विचार करण्याची आता काळाची गरज होती. कारण आज आपण पाहिलं असेल जगामधले काही देश हेक्टरी त्यांचं जर उत्पादन पाहिलं एवढ्या मोठ्या प्रमाणावर करतात. आज त्या मानानं आपण दुसरी हरित क्रांती केली, त्या बरोबरीनं आपण आलो. आज मला अभिमानानं सांगता येईल की आजपर्यंतच्या शेतीमध्ये जर आपण पाहिलं तर फार मोठ्या प्रमाणात आमूलाग्र बदल आले, ज्याच्यामुळं आजपर्यंत आपल्या भारतामध्ये महाराष्ट्राचा तुम्ही आम्ही दुष्काळ बघितला, त्या भारताच्या दुष्काळामध्ये अन्नधान्याची टंचाई होती, पाण्याची टंचाई नव्हती आणि त्यावेळेस आपल्याला आयात करावं लागलं. आज मात्र भारत हा आपला अन्नधान्य निर्यात करतो, याचा स्वाभिमान आपल्या सगळ्याला असला पाहिजे. पण एवढ्यावर आपण चालणार नाही, कारण आज 135 कोटीची असलेली लोकसंख्या, याच्यावर असलेला आपला शेती ही दरडोई कमी होत चालली. याचा उत्पन्न वाढीचा वेग आपल्याला वाढवावा लागेल, तरच पुढच्या काळामध्ये हे शक्य होणार आहे. आणि म्हणून त्याचा उपयोग या नवीन असलेल्या आपल्या रिसेंट ऍडव्हान्सेस इन मटेरियल मध्ये सायन्समध्ये नॅनो टेक्नॉलॉजीचा वापर करून त्यामध्ये काय करता येईल हे बदल आपल्याला शास्त्रज्ञाच्या दृष्टीने फार आव्हानात्मक आहे. त्याचाही आपण योग्य वापर करून घ्याल अशी अपेक्षा आपल्या सर्वांकडून राष्ट्र निर्माण केली तर काही मला वाटतं काही कमी वाटेल असं मला वाटत नाही. आणि म्हणून अशा या सगळ्या भौतिक सुविधाच्या दृष्टीनं देशाच्या सुधारणेमध्ये आपल्याला पुढे जायचं असेल तर आपला सगळ्यांचा सहभाग हा सगळ्यात मोठा राहणार. आणि त्या सहभागामध्ये आज ज्यांनी या कॉन्फरन्समध्ये भाग घेतला त्या खरं म्हणजे त्या सर्वांचं मनापासून अभिनंदन करावं वाटतं. आताच आमचे उद्घाटक आर्यन सिंग साहेबांनी भामाणू संशोधन केंद्राचे प्रमुख फार मोठा सहभाग त्यांनी नोंदवला. त्यांच्या भाषणातून जे काही त्यांचे उद्दिष्ट लक्षात आले ते फार मोठे. त्याचबरोबर आमचे काळे सर तर आम्हाला नेहमीच मार्गदर्शन पुण्याच्या या सगळ्या याच्यातून महाराष्ट्रामध्ये सगळ्यात प्रसिद्ध आहे. आणि त्याचबरोबर आमच्या विद्यापीठाचे असलेले आमचे मार्गदर्शक आदरणीय डॉक्टर NCRAMSN जाधव सर यांचं सुद्धा सातत्यानं आमच्या सगळ्यांना मार्गदर्शन होत असतं. आणि म्हणून आमचं महाविद्यालय आज या स्तरावर येऊन ठेवलं. आज या कॉन्फरन्स आम्ही ही कॉन्फरन्सच्या रूपानं आपण घेऊ लागलो. आज पुढच्या काळामध्ये होईल ज्यावेळेस त्यांची समजेल परत एकदा एखादा आपल्या सर्वांना एकत्र येण्याला आम्ही संधी उपलब्ध करून देऊ. त्या निमित्तानं आपण याल अशी रास्त अपेक्षा व्यक्त करतो. आपल्या या सगळ्यांच्या संशोधनाकरता परत एकदा आपल्या सर्वांना शुभेच्छा व्यक्त करतो. ज्यांनी ज्यांनी भाग घेतला त्यांचे मनापासून अभिनंदन करतो. आणि पुढचा काळ आपला भोग सुख समृद्धीचा जावो एवढी एक ईश्वरचरणी प्रार्थना करून आपल्या प्रत्येक प्रयत्नाला यश येऊ एवढी एक रास्त अपेक्षा भगवंताचरणी करून माझे 2 शब्द संपवतो. धन्यवाद.
Thank you very much, sir. The Honorable President of our institution shared his feelings with all of us. He pointed out his concerns over the agricultural field and how nanotechnology can be used to improve the productivity of agricultural field. Our president is the guiding force behind us, and he's always there to support us for any academic endeavor. So we are obliged to you. I express my thankfulness on behalf of all the participants also. Thank you very much, sir. Now, I want to thank all the dignitaries and resource persons who have joined this webinar. Let me first extend my gratefulness to Honorable Shri Prabhakar Rao Palotkar, the President of our institution. Then I am also thankful to Dr. N.R. Singh, the scientist, for his inaugural address. I am also obliged to Dr. Kamlakar Jadhav, who was a chief guest in this inaugural function and who also shared his thoughts on this topic. I am also thankful to the principal and convener of this conference, Dr. Ashok Pandit, for welcoming all the participants and sharing his thoughts not only about the college, but about the conference of this conference organized by Department of Physics. I am also thankful to my staff members, my colleagues, Dr. Vijay Sanap, Dr. Dattatreya Kakade, the technical support team, Dr. C.D. Sonone, Dr. Santosh Wagh, Dr. D.R. Pandhade, as well as the supporting staff of the college. And I declare that this inaugural function is now over. But let me make one another announcement that we are shortly going to begin the keynote address by Dr. B.B. Kale. So please stay tuned. We are now going to begin the keynote address. May I now request my colleague Dr. Dattatreya Kakade to give a formal brief introduction of today's keynote speaker, Dr. B.B. Kale.
Hello, am I audible to all? What this is, sir?
Yes, yes, you are audible, sir.
Okay. Good morning to all of you. I feel very glad to inform all the delegates that we have a distinguished resource person, Dr. Bharat Bhanudas Kale, among us. Now, he is a scientist and director, Center for Materials for Electronic Technology, Pune. He has completed his master in physical chemistry from Pune University. He completed his research work in PhD in chemistry in CSIR National Chemical Laboratory, Pune. He is having 27 years research experience in various fields like nanostructured advanced materials, photonic materials, solar cells, thermoelectric solar cells, lithium ion, lithium air battery, so and so. He is having administrative experience. He handled the research group of 20 to 30 people since 20 years, having the responsibilities as a director MCAT Pune lab in March 2014. His Google Scholar Research Index is 43. He has been published more than 246 research paper in various national international journals. He has been registered 22 patent, out of which 4 patents of government of United States of America. Under his valuable guidance, 22 research student has been completed their PhD degree. He's investigated 24 research project of budget 1,878.05 lakh, out of which 3 were international, Indo-UK, Indo-Solvia, and Indo-Japan. And currently, he is investigating 9 projects of having around a budget 2,689.83 lakh. Am I audible? Huh? Okay. Hello, am I audible to all?
Yes, yes.
Oh, okay. There was some technical issues. Okay, we resume it. Shall I continue?
Yeah.
Okay. Dr. Kale sir has foreign collaboration 5 collaborative projects: Indo-Slovenia, Indo-Japan, Indo-UK, Indo-Korea, Royal Society, and United Kingdom. Other collaboration is having University of Leeds, UK, TN Tech University, USA, both University, USA. He has been having a technology transfer, 3 technology transfer, number of other, he has been organized, number of conferences, 3 national and international, 3 conference he co-chaired, 3 workshop also he chaired. He has been given invited talks in various national, international conferences, more than 110 in India and at international level, UK, Slovenia, South Korea. He's been awarded, he is a fellow of Royal Society of Chemistry, London, 2020, APM Academium, Asia Pacific Academy of Materials, 2019, Royal Society of Chemistry International Collaboration, 2017, Proposal Award with University of Leeds. Award of year 2013 on photocatalyst by KRICT, South Korea. Editorial board member of Metals and Materials International Springers. MRSI Gold Medals Award 2010 Bangalore. And various awards he has won. So with this brief introduction, I conclude and hand over the proceeding to Assistant Professor J.D. Pardesi sir. Thank you very much. Pardesi sir.
Thank you very much, Dr. Kakle sir, for giving a brief introduction of today's keynote speaker, Honorable Dr. B.B. Kaya sir. Sir, I welcome you in this e-conference, and I request you to begin your keynote speech.
Can you hear me now?
Yes, sir. You are audible, sir. Please go ahead.
Yeah, thanks to organizer, and thanks to Jadhav sir, then basically Palatkar Sahib, because we are closely associated with him. Then Pandit sir and other professors of the Yeshwantrao Chavan College. Thank you very much for inviting me and for this conference. Basically, this is on material science, and now I can share the screen. It's okay. So also, thank you to Dr. Nagumani, and he has given good survey of what is material science, what kind of materials we can what kind of materials we can they have the importance in the Indian context. Can you see my presentation now? Post participants. Can you share the screen, please?
Break this way.
First invited talk.
Can you share the screen, please? I have already shared the screen, but you have to, something has to be done from your side. It is not.
Sir, screen share करा. Sir, screen share समझे आपल्या बाजूने.
सर
आकडे सर.
बोलता बंद करून ठेवा तुम्ही.
Okay. Now visible.
Now visible. Okay. So today I'm going to talk on more on materials, because materials are important. You know, everywhere how this material significance is very you can find, because you can if you take any all areas, like you take electronics, you take agriculture, you take automobiles, in all sectors, materials are important. Like your day-to-day, day-to-day your duties, and if you say day-to-day your what maybe instruments you are using, they all are made up of some materials. So materials are important today. I'm not going to talk on a very specific topic today, a specific material. I would like to share the total so many other materials which are very important for us, for the nation. And today we have a very good opportunity, good opportunity to all of us to under Make in India. We can do all kind of such materials and supply to all companies, or like automobile. Nobody can sustain, nobody can give the nobody can accommodate that much production of one company. So we can have many people, many production units to support all kind of big manufacturing companies. Let me introduce CMET. What is CMET? We are here in Pune, working on all kind of chemicals, materials, related polymers, glasses. Then we have one lab in Trichur. They are in electrochemics, because our motto is only for focus to on electronics, so and strategic sector. Materials for strategic sector and materials for electronics. Then this Trichur lab is totally on ceramics required for the electronics. Hyderabad is pure metals, 99.999, 5 impurity, 7 impurity, and required for the electronics, required for the strategic sector like ISRO, DRDO, because their strength is there. Because our strategic sectors, their consumption may be less, but somebody has to give them this material, so we provide them this kind of material. In Pune, we have anyway, we are today I'm going to talk on LTCC, this LTCC based applications development and material. This LTCC means low temperature copied ceramics based packaging, electronic packaging, because any electronic device needs the packaging, proper packaging. There are so many circuits in the devices. It has to be connected layer by layer by layer. So this connection of these circuits and packing of this all components together is electronic packaging. So low temperature co-fired ceramic is a well-known packaging, electronic packaging, which is required in electronics. So, and basically we established this facility in Pune to cater the need of our strategic sector like ISRO and DRDO In 2005, we have initiated this, and now we have established, and we are, there are many important circuits for our atomic energy, and as well as ISRO and DRDO. We are doing very typical program for them. Then basically today's theme is nanostructure materials. So all kind of nanostructures we make nanowires, nanometals, nanoalloys, semiconductors, oxides, chalcogenides, everything we do. We grow in polymers, we grow in glass. We have alloy, in alloy we can grow specific nanomaterials and change the properties of alloy. So these are a variety of things we can do. Then we have graphene carbon nanotube. Then we have carbon dots now. Now we have graphene dots now. So this kind of things coming in the future. So we are doing that. Then under renewable energy, we have hydrogen generation under natural sunlight. We use from water, we produce hydrogen, from H2 we produce hydrogen. Then thin film solar cells, dye-sensitive solar cells, fuel cells, all kind of things, materials for it and their devices, all kind of things we do. Then energy storage, we have full-fledged program on supercapacitor. Then lithium-ion battery. Then now we started sodium-ion battery and come to some stage because sodium is a cost economical, so we are doing it. Then flexible batteries. So next generation is all flexible electronics. So we also feel that they need flexible batteries because in future we may have bendable TVs or foldable TVs, foldable mobiles and other devices, electronic devices. So they need, now we may have foldable cars. The cars we can hang in the parking. This kind of technologies will come very soon. It's within 5 years, this kind of technology will come. The electronics so going ahead. You see, today I have one technology of electronics. So tomorrow may not. That may be disappeared and something comes. So electronics, basically, we are talking to all European guys and our American guys. We are very, in electronics, we are very ahead because very few months back, we had a talk on these foldable cars. In one parking now, only one car we can have, but in one parking, we can 4 cars, we can hang it. So this kind of things will come. Then we can, your TV will be as a foldable TV. Just hold it, put it in your desk, in car and go anywhere, open it, watch it through internet. So this kind of things, so very, very interesting things will come in the market very soon. And see how this research is very important. You know? The research is basically required for the humankind, how their life can be made very easy life. It has come, it has come from the olden age. So initially people were not having cloths. They started wearing cloths, then different colors of cloths, then different, everything has come. So it has changed with this research. It has not just came just like that. So these are a very interesting things comes. Interesting research will come, has to be done now in the country because research is a wealth of the country. See, anything we develop, it has a value. So now you see flexible battery, if you develop, it has a value. It will have a value. Okay. So we can patch these flexible batteries, we can patch on the cloth, our shirt. We can charge our mobiles like just like that. Okay. So the patch type batteries will come in the market. So when we go walking it, now people are thinking whether we can have air solar cell connected with these batteries. So patch solar cell, very thin solar cells, we can have the shirts. And while walking in the sunlight, we can charge the batteries. But these things, it is not far away from the today's. Then flexible batteries, then metal air batteries, because batteries has a problem. See, there are two ways. People, you should know what is the function of the batteries, what is the function of, like solar cells. It's a light driven energy generation system. Like thermoelectric is a heat driven electrical generation. It absorbs the heat. See, is a material property which absorbs the heat. We get the electricity voltage. The same material, if you apply the voltage, other end we get a cooling. It's a thermoelectric, it's a Seebeck effect and Peltier effect. There are two effects, very important. Seebeck effect means we can generate the electricity through the, when absorb the heat to the material. When we give the voltage to the material, other end we can get a cooling. Very fantastic application of these two effects. In our country, we have a lot of heat available. In the summer, you see temperature goes to 45 degree, 30 degree, 45 or 50 degrees in some of the places. Why don't you use that heat and generate the electricity? Like in like cities in Aurangabad, nearby places. We have our farmers are, means our economy is based on totally on farmers, 80%, 70%, almost 80%. But today we do not have good cooling systems, because your milk, every day you are putting milk in the dairy, whether all milk is going to the Mumbai, no. Because of insufficient cooling, it gets spoiled. That's the problem. Your onion, your tomatoes, your fruits, you cannot keep long time because of this cooling. We do not have that kind of system, because it's not, our ECs are not cheaper way to do it. This kind of filter system definitely will help such kind of pharmaceutical, such type of application. Suppose if you have a Peltier cooling effect or any thermoelectric solar cell on the top of the roof, whether we can cool the room at 10 degree, 15 degree. Definitely it is possible. Why we are not giving voltage through the battery? We will give the voltage to the solar cell. We have a solar cell facility. Solar cell will produce the voltage, give the voltage to the materials, and other end will have cooling. Tremendous effect. All farmers will have small coolers. All farmers can have bigger coolers where they can keep their fruits, crops, grains. No maintenance, no cost. It's only initial investment. So these kind of things are very important for a country like us. I think all engineers, and they can, we are here to inspire them and we are here to help them, but they should think properly and devote their efforts in this direction, not very, because any research, when we are doing any research, it should be applicable to the society. That is very important today. See, you can do the fundamental research simultaneously, but on the other hand, we should also see whether our research is really helping to our common man or not. I'm more, that's why today's my lecture, I will just give the glimpses of what we did. And any questions, anybody may have any questions, you can ask me related to, I will just answer it. I talked to that LTCC based can see at the corner here, this is the device. You know how many layers it is? 1, 2, 3, 4, 5, 6, 7 layers. These all circuits together and packed it in one pack within these low temperature copper ceramic systems. So it's very compact. Like now we started doing fuel cells, solar cells with this low temperature copper ceramics. Very tiny and very sturdy. And this facility we are giving to all kind of all strategic sectors. Here you can see this figure. You can see how this very complicated structure we can make in this LTCC. And it's here's micro circuits for the communications. You see very complicated circuits. These circuits we made in our laboratory, and maybe 3 layers, 4 layers. Now you can go to 24 layers. So another is a night vision feed to here we can see. Then gas sensors also have, I can show you here. You can see here. So all this in made up in LTCC based technologies. We have a hub. I can say our lab is a hub of nanostructure materials. You can see all these kind of things. Nanorods, wires, quantum dots, semiconductor oxides, sulfides, oxides, all kind of nanometals, nanometal alloys. Then we have quantum dots, embedded glass, composite glass. Then we grow polymer we grow nanoparticle in polymer. If you have a porous material, in this porous material, we can grow small nanoparticles. All this material combination we do. It's very essential to any researcher to find out applications. How, see, any materials has specific applications, specific characteristics. You have to see these characteristics and see, apply your mind where it will go. What I found, some of the materials required useful for batteries, they are also useful for solar cells. Some of the materials we've seen that they are also used in hydrogen production. See, because they have similar properties they needed in this application. So we have to think and model there and present it, use it properly. See, these structures are very important. You know, as Raghunath Mani has told you that shapes are important. See, all kind of shapes we do. You see, very typical. See, making this kind of shapes very important. Like you see, this is actually thin film. First photograph I have seen, that is a thin film. On the thin film, you have you can see the structure like this. This mountains of very small particles together. Then another picture is a graphene, but these are not the simple graphene. We purposely made them perforated. Then this is MOS2. Metal oxide, molybdenum disulfide is a similar properties to the graphene. Structure is like graphene, it is a layered structure. Graphene has a layered structure, it's a gray structure. You can have single layer, single layer of MOS2 is a semiconductor. Bimetallic, three layers. It's a semiconductor. And when it's a bulk one is a metallic. So we can make semiconducting MOS2, such kind of structure. It's like honeycomb-like structure. Then you can see flower-like structure. See, if you see the flower, you see flowers are in micron, but their thickness of the petals, they are huge petals. You know, if you see if you can see the petal of any flower, only if you take it out one petal, you can see that petal is a thin petal and it's a high surface area. And they assembled each other, self-assembled and form the flowers. And because of this self-assembling and porosity, they have a good storing capacity, or they have high surface area. So activity is more. And this is typically applicable to very few applications, not for all applications. Typically, we do all kind of sensor, gas sensor, optical sensor. See, this zinc oxide rod is, they have a secondary growth again of small nanowires, here. This is hairy structure. This hairy structure is nothing but a very, it has high surface area. So any sensor requires the hairy structure to capture the gas or to absorb the gas and all kinds of things. Then another, same zinc oxide, you have nanoneedles, you have nanorods. Then we thought that whether we can use two methods together and see the shapes, how the shapes of the zinc oxide can be tuned. Then we found that when you use sonochemical and hydrothermal reaction, we can get cups of zinc oxide. You see, there is a hexagonal cap and there is a hexagonal cup. Very interesting structure. And these are the quantum dots, all kind of quantum dots we can make. These are the graphene sheets we produce. Now we can produce in large scale. These are the perforated graphene, basically required for some other application. I will go at the end of the application of this. We purposely made them perforated. We have technique to make them perforated because the graphene in some of the, graphene may have high surface area. But if you have a bunch of graphenes, then we cannot have, will not have that kind of effect in the application which have single layer graphene. Single layer graphene production is very critical. But we can make graphene in some bilayer, T-layer components. So there we can have this kind of porous structure. So we can have the same effect, porosity and all these things, surface area increase. Keeping in mind that we use it for battery applications. Then we produce nanomaterials in large quantities, 100 grams per hour. This is a plasma reactor. So it goes to atomic, it is a, here is one plasma reactor. Like aluminum nanoparticle you want to make, aluminum rod is one of the cathode there. It gets evaporated to the plasma, and then this atomic level vapors of aluminum get quenched at minus 70 degrees centigrade, and we collect here continuously aluminum nanoparticle. So this is a unique reactor we have. We can have aluminum, copper. We will do also copper. You see 100 gram, 120 gram Pascal per hour. This is aluminum nanopowder. Why we made this? Because this is required in propellant. To increase the efficiency of the propellant, they are used as oxidant. See, suppose copper nanoparticle of 1 micron, they use 10 grams for the as a propellant. This is 1 gram of nanoparticle of copper, give the same efficiency because surface area increase. Means in a small weight, 0.1 gram and 10 gram of bulk with the same property, same efficiency. Why it is used? Because the load of, anyway, suppose you are you are launching vehicle, suppose a rocket, this propellant is used. The theme will be how we can reduce the weight of the propellant, because huge amount of propellant is required. So if you use 30% of copper in that, again it adds in the weight. If you use this kind of drastically 20% weight is reduced because of nano effect. So we supply to the DRDO our Hyperx Research Center, 5 kg material of this. Now, on the basis of this, we are putting large scale production in HMR. As I told you that we can make all kinds of nanoparticles and all these things, but some nanoparticles are not stable at room temperature, stabilized in the glass. This is a unique process we developed. You will not find in other website such kind of materials. We grow cadmium sulfide, cadmium selenide, base metal, or all kind of chalcogenides. Now we develop metal oxides in the glasses. Very steady up to 500 temperature. If you give the temperature of 500 degree also, they are stable, 1 to 2 nanometer size. Very important. And this band gap, see, shape and size is very important in the, like semiconductors. The quantum dot size changes the band gap. With size, band gap changes. That's why you can see here, this may be in the glass. This is a cadmium sulfide glass. It is a transparent glass. There is no nanoparticle of CDS. This is 2 nanoparticle of CDS, yellow glass. This is blue, 5 nanometers of CDS, and this is 8 nanometer of CDS. You can see there is a change in color. That means there is a change in band gap. Okay, here is the band gap is different. Here is the band gap is different. Here is the band gap is different. Simultaneously, you can see the particle size inside the glass of cadmium sulfide is 5 nanometer. In red is a 5 nanometer. Then we also CDSAC nanoparticles. There also you can see the change in band gap. Here you can see how this absorption changes with the size. And these are used as in the remote sensing camera as an optical filter. We can make absorption, we can make the glasses which has absorption from 400 nanometers to almost 860 nanometers. So this kind of optical cutoff filter manufacturing, at least technology is available with this now, thus now in the country, because only 2 pioneers are there in the short glasses and Corning. They can make it now, but we have this technology now. Whenever somebody is not giving to us, we can start making out of this. So we are now our CISRO program and DRDO program, we have kept this technology very aside. Here you have CDSAC nanoparticle. See color yellow, red, blue because of change in particle size. Very huge change in absorption. You can see with size. This is CDSAC glass. Initially absorption is 300. There is 1 nanometer. As you increase the particle size, absorption increases up to 700 nanometer. Okay. So one material can give all kind of this band gap with size. So this is very important. This we make, and you see all glasses are transparent. 90% transmittance. In 90% transmittance, very tiny nanoparticles embedded in the glass. That is very important here. Then we go for the applications. See, I have showed you the all kind of materials. Now, hydrogen is very important today because hydrogen is a future fuel, energy-rich fuel, very energy-rich fuel, and green fuel. All fuel cells technologies are dependent on hydrogen, but hydrogen problem is how to make pure hydrogen in low cost. See, hydrogen production is very well established technology, like steam reforming of methane. We produce hydrogen, but hydrogen, along with hydrogen, we have carbon dioxide, carbon monoxide, all these kind of things are. And temperature up to 400 degrees centigrade. So this kind of technologies, this kind of process gives very costly hydrogen. If you make hydrogen cheaper than petrol, definitely this hydrogen engine will come, hydrogen storage facility will come, hydrogen storage also will increase, so that all the hydrogen storage solids, we can pump the hydrogen in the solid, and these solids can be kept in the atom two-wheeler or three-wheeler, and this three-wheeler can use this hydrogen slowly. And two-wheelers, three-wheelers can be run on the hydrogen. If you go to BHU, they have made some three-wheelers. They can run on the hydrogen. They have big solid material. In the solid material, they store hydrogen, and the solid material kept just like in petrol, we keep it like that. They have a box, and this they just heat it to 50 degrees centigrade. Hydrogen is releases, and that hydrogen is slowly used for the as a fuel. Very energy rich fuel. No, it's not like petrol or diesel. Very huge amount of energy is generated by the hydrogen. Calorie pickup of hydrogen is so high. Everybody knows that. So how to make cheaper hydrogen? So photocatalytic process, whether water and H2S is a good source in India, cheaper source, we don't have to pay anything for the water. At room temperature, whether we can produce hydrogen. Again, it is a material technology. A material which can produce, we can absorb sunlight, produce electrons and holes are responsible for the hydrogen production. How it is possible? There is a tract that when we produce hydrogen, when we take water, in water we can have the semiconductor nanoparticles. Nanoparticles I'm talking because nanoparticles use very small amount of use and surface area is high. And band gap. The band gap we have to use, which can like 2.4 to 1.2 electron volt, which can absorb all kind of whole spectrum of solar energy. The material should have that capability to absorb all this spectrum, and which produce then electrons and holes rapidly. Now, electron holes is a continuous process. So when electron goes to excited, it will come down again, it will recombine holes. Okay, it is happening in any kind of semiconducting metal. Disturb this cycle. I don't want holes during my reaction. So trap these holes and make the free electrons more. When we make the free electrons more, again, free electrons are excited. They want somebody to fight, to reduce their energy. And they reduce this water into hydrogen and oxygen. We use H2S, hydrogen into sulfur. So there is a track. So while playing with this catalyst, we should play with the parameters. And first parameter will be band gap should be in visible region. Another is how we can make high surface area or material. It should be stable because it should not react with water. If material start reacting with water, problem. So stable materials are very important. So the materials technology with this kind of tuning, it's our duty to tune them and for our applications. So all kind of applications, we can use in computers, everywhere we can, atom wires, everywhere the hydrogen will be used if you have. And no pollution. Nothing is coming out except water. So this is the great advantage of this fuel cell technology. This is the room temperature. I told you that photocatalyst here. At room temperature, we're getting hydrogen and oxygen. Then hydrogen and oxygen can be separated through the filter. This is the H2S technology, currently class process. Produce only sulfur. Our plan is how we can make H2S into hydrogen and sulfur. So that is very important. Then tune the band gap. I told you tuning the band gap, like NB205 is only UV catalyst. It absorbs only UV light, but very stable compound. NB2, very stable compound. It doesn't react with water. It doesn't react with alkali. It doesn't react with acid easily. So then what we did, we doped with nitrogen. As amount of nitrogen going into the lattice, the band gap of this NB205 changes. It comes to the visible region. And this we produce use this catalyst for water splitting. And you can see that different nitrogen content, very high nitrogen content in the NB210 gives good hydrogen production because the band gap is in visible region. And a very interesting thing that happens in the nitrogen doping, when you dope nitrogen in this solid, the surface becomes porous. Because what nitrogen does, one oxygen, partially oxygen is replaced with the nitrogen. So while this processing, some nano holes or nano pores are generated. Here you can see, here's a bigger size. You can see here at the surface, very porous structure. Very quite obvious. As I told you, like MOS2. This is bilayer of MOS2. And very single layer MOS2 you can see here. This kind of structure I required because it's high surface area and definitely gives good photocatalytic activity, hydrogen you see. Then we thought that like MOS2 is stable, why don't you use why don't you club have some phase pure compound along with it? Make it phase pure compound. Then we are thinking that whether we can make cadmium molybdenum sulfide as a phase pure compound. We did it, and we also analyzed for structurally because it was a new compound. We have structurally analyzed modeling and simulation. Here we can see that very flower-like structure. Surface area is good, and you see the hydrogen, very huge hydrogen production. And same way like SN304. First time we doped nitrogen in SN304 to have good production, to have good photocatalytic activity. But as compared to SN2, we get good photocatalytic to SN304. Further, we want to enhance it, doped with nitrogen. So that is the strategy we made. And it showed good performance. Another photocatalyst we use as a heterogen, nano heterostructure, KiO2 nanoparticles and cadmium sulfide. We made cadmium sulfide and we decorated with TiO2. Maybe 1% cadmium sulfide in 91%, 99% TiO2. And we found that at a typical concentration of zinc in cadmium sulfide, we get good amount of hydrogen, good hydrogen production. Zinc tungsten is a very stable compound. So we thought that, but it is in UV region. Then we doped with nitrogen for the first time. We will not find any papers, nitrogen doped zinc compound. Only we only invented that either it is possible to dope a slight amount of nitrogen in the ZnWO4, and you see very huge absorption at in the visible region, and which gave good photocatalytic activity. Then nitrogen doped ZnWO4, same. So our motto was to dope with nitrogen and enhance the capacity, and that we did it here. So all this kind of structure we use, like cadmium sulfide, We use flower-like structure. We use nanotubes of that, and silver zobgeno. The new compound with lanthanum indium sulfide. Lanthanum indium sulfide is such kind of structure. Then we can make nanowires. Then we made zinc indium sulfide, rose-like structure as well as hollow structures we made. We gave good photocatalytic activity. So making these structures very important in the laboratory and use them. This reactor is for hydrogen production. I'll come later because I have that slide. I'll show you that. Then, as I told you that Ag3O4 nanoparticles in the glasses, and we can have smaller particles of this yellow means maybe 1 nanometer, this is 3 nanometer, this is 5 nanometers of Ag3O4. Ag3O4, when we keep it open, it gets oxidized immediately because it is a very photosensitive material. But if you grow in glass, they are very stable. And this first time we have shown this we have published in Environment Science, this paper. Good hydrogen as well as later on we use for this for water purification. See, this is glasses which I showed you. This glasses, if you have smaller nanoparticles in the glasses, we can have band gap from visible to almost higher region. I thought that whether we can use this as a photocatalyst, and first time we use as a photocatalyst. We have US patent on this. Then we cadmium sulfide, cadmium selenide, all these glasses we use photocatalyst, and we found that though it is a 0.5% particles inside the glass, it shows much more photocatalytic activity than the powder form, normal powder, and stable. Being a glass, it gets settled, wash it water and use it again. That is the advantage. So this CDSAC, then we met this month. You see, Ag3O also made this. Then we thought that let's put in these glass particles inside on the large scale production of hydrogen. And our team produced hydrogen 2000 ml per hour using this system. This is a reactor system, and then open to the sunlight from 11 a.m. to 4 p.m. We took the reading, and it's very interestingly you find as sunlight goes on increasing, decreasing, that the automatically hydrogen also production also get decreased. When you cover this reactor with a black paper, hydrogen stops. So it's so sensitive to hydrogen, so sensitive to sunlight. Very interesting. Then, as you know, the hydrogen storage is also important because we can, in small vehicles, we can use a solid kind of thing. We can, as I explained you, the hydrogen can be trapped in the solid. And this solid can, if heated to 50 degrees Celsius, same hydrogen we can use. So in the solid, till date we can have 7-8% hydrogen. Is it up to 6%? Now we are trying to 7 to 9%. Then this technology will be feasible. So making porous structures like MOF we are talking about, metal organic framework. Through this metal organic framework, there are moieties, small cavities, and get hard surface area, and this can be used for hydrogen storage. This we use silica spheres. The silica spheres, the advantage is inside the silica sphere there is a channels forms, and this hydrogen gets trapped in the channels. So this is very important. So such kind of material construction is very important. Like here, one of the MOF5 we have prepared such moieties, and this porous structure help in trapping more hydrogen. Then we have sensor. We make a sensor of carbon monoxide, NH3, VOC, then like NOx, SOx. We made it for ISRO, DRDO. Temperature sensors we have made for DRDO with materials for prototype sensing. This is a NOx sensor we made for the ISRO. Now, this NOx sensor we can make it. How can make it optical sensor? Now it is a normal sensor with gas, NOx gas. But optical sensor through light, whether we can sense this NOx. Then we have battery facility. See, when you generate any energy, there should be some storage. Like we are using batteries, charging and discharging. We charge the batteries, and this batteries we use for whole day. Okay. Like in windmills, whatever energy generated is getting stored in the battery first, and then it gets circulated. So storing energy is very important. There are two ways to do it. One is a battery, another is a supercapacitor. Function of supercapacitor, in supercapacitor, what happens? Charging and discharging is very fast, 20 seconds. But power density is very high, energy density is less, less energy density. But power density, huge power density of supercapacitor. Huge power is generated. So we use it as a starter. On vehicle, when you start the vehicle, that time this supercapacitor works. Then it goes to battery. So initially, to start the engine, we need a huge amount of energy. So supercapacitor used. It charge fast and discharge fast. Battery, power density is low, not like supercapacitor, but energy density is very high. Charging take 2 hours, discharging take 24 hours. Whenever you use it, how you use it, that is a discharge. The mobile battery, suppose I am using it for, continuously I am using it. So it may last for 4 hours, 5 years, 6 hours. How this your use is. Then thought comes in mind that whether we can have a combination of two. One has the lower energy density, other has a high energy density. One has a lower high power density. Another is a low power density. Whether we can make it combination of it. It's possible. One anode can be used as a lithium-based, battery-based anode, and another supercapacitor. So we can increase the energy density. So whatever may be high power charging is there, we will be able to store in the battery. But still we are struggling. There are so many problems. There are trains now come up in the market that they will charging it to only 20 seconds, 30 seconds, supercapacitor based railways and buses. So every station, they will have the electrical connection. When the bus stop it, the supercapacitor gets charged. Supercapacitor get charged, because supercapacitor need very high to store fast charging. Then this module, like hybrid modules, if you have this charge, at least we can use it 5-10 seconds, 5-10 minutes, 20 minutes, 30 minutes, using batteries, the hybrid module. So next stage, when next station train again stops, again it will just have the charging to the current, because they may have this arrangement. So every bus stop will have that kind of arrangement. So this kind of system use can be railways, buses, So very economical way of handling this energy. So one is energy generation and energy storage. Energy storage is also important. You want to make, see, now people are talking about 10,000 milliamperes here, your battery pack for charging anything. Power pack, I can see. If you have materials, again, battery is a materials technology. Again, it's materials technology because I'll show you. This single cell is, means you have a cathode, you have an anode. One is between electrons. Simple. This is a basic battery concept is simple. Like lead acid battery also, one is a cathode, one is the anode. Lead acid batteries, problem is lead. Huge amount of the weight of lead creating problem. We cannot, suppose I want to use a car in lead acid battery. The lead acid battery weight itself is 100 and 150 kg. That will not work. Because it will add on the weight of the vehicle, and if you add the weight of the vehicle, your average of the goes down. So lithium is a very simple, lightweight material. That's why people are preparing lithium. See, more number of lithium ions get transported to the cathode while charging, and more number of while discharging. Means capacity of the battery is much more higher in lithium ion batteries as compared to lead acid. While charging, lithium ion goes through electrolyte to anode. They sits on the anode. So your anode material should have a layer structure. Your anode material, like carbon, is a layer structure. You can, like lithium titanate is a layer structure. So when lithium ion sits on that, there should be some wide edge to accommodate these lithium ions. The anode material, which has a capability to accommodate more number of lithium ions, you get more capacity. Okay. So now this is the cylindrical cell. In this cylindrical cell, we have so many single cells together. It's a pouch cell in your mobile battery. You may be 24 single cells get attached. One single cell is 120 milliampere hours per gram. Suppose I want to make the battery for the mobile, you say 5,000 milliamperes. Then I can make 120 milliampere for this one. So I need almost 50 stacks connected parallel in series to have proper voltage and proper current, ampere. So this is again battery management. You can have you should have a single cell fabrication technologies. Any type of battery you can make. So India doesn't have single cell fabrication technology. Now we have that. We developed that with materials. So this is button cells we made. Pouch cell also we made as a single cell. Then we made this one, the mobile battery. Charge it within 1 hour. Again, all kind of material we used. Those we use for hydrogen, some of them we use in battery, and we get good results. Because of this porous structure, because of their conductivity, because of the electrical conductivity, all kind of matters which are required for the battery, we selected and we use it and found very interesting. This is the MOS2, honeycomb-like structure, 400 milliampere hours per gram, very high capacity we get for lithium-ion battery. Then we thought that whether we can have copper sulfide together with MOS2, but copper sulfide is not stable. It has come down. The capacity has come down. Then we are also some of the students also working on new materials, like whether instead of phosphate, whether molybdenate can be used, sodium molybdenate, lithium molybdenate, other things can be used. So, and we found very interesting results for this. Now we are also modeling simulation for structural study of this. You know, additive manufacturing is very important today. Very new technology. Additive manufacturing means you can have you can draw the circuit on the cam card, okay, and similar kind of thing can be printed on any substrate or statue. You can if it's a polymer statue, you can have the picture of statue fit in the computer. Similar statue can be made with this technology. Nothing else, everything automatic. Another way is, suppose in your motorbike, your some of the aluminum part has gone. If you have a design of that aluminum part, you can make any service station can make that with low cost. They don't have to depend on the manufacturer. So these technologies will come in the market. Now battery, I'm doing it, coating it, anode, putting cathode, then electrolyte. This single machine which can print cathode, we can print anode. If you have solid state electrolyte, we can also print electrolyte. And see structure, we can make such kind of porous structure, stack it. Definitely, it's a very thin batteries with good capacity. Then micro batteries, then 3D printed solar cell also we can make use of this. So these new technologies, now we have a center of excellence in this. We have center of excellence in rechargeable batteries. We can make lithium-ion batteries, and we can have research on all kind of research. So we can we have collaborated with industries, and people are working in this center. Now Center of Additive Manufacturing has come in Pune, CIMET Pune. It's some 20 crore projects, partially funded by the industry. Here also anybody can come and work and utilize this facility. Basically, we did it for electronics, so slowly we are going for automobile and all kind of things. Here, only constraint is how to make printers. So we have identified some industries. They are helping us to making printers. So this is the plan going towards the automobile. Then we also made sodium-ion batteries instead of lithium. Instead of lithium, we are making sodium-ion batteries, and we are very close to lithium capacity. Then we have made this. We also use this perforated graphene, and show the very wonderful. We made flexible batteries with a flexible electrolyte we can use. It's a flexible electrolyte. Using this flexible electrolyte, we have flexible battery. If you roll it, then there is no change in intensity. So rolled batteries we made. You can roll it here. It's not working. So we can roll the batteries. Cell. No, there is a continuous. We will study the bendability of the batteries. Bendability study. Not much of difference. So other kind of carbons we use, like electrospun carbon, which is required for this flexible batteries. Then we also little work on fuel cell. So we did platinum, cobalt nanoparticle for this PM fuel cells. And these glass nanoparticles embedded, you see the glass nanoparticles, if you see the portion, This is a glass nanoparticles inside, the bismuth nanoparticles inside. And the glass is transparent, but this we use for the X-ray absorption, because lead has been used as an X-ray absorption, but we use lead-free glasses for the X-ray absorption. Only 0.5% quantum dots inside the glass, use 100% exposure. The same glasses with quantum dots we use as a optical currents isolators. As but now we want to make the fibers that is in progress. Similar quantum dot glasses which can absorb sunlight and water can be boiled and distill it, and we can use pure water at room temperature. So this is working out with the Royal Society. We are very close to, now we get 90-degree temperature through this sunlight using these quantum dots. So these are the technologies we have transferred. One is the photon, this is a photonic sensors, which is used in atom boil. Then X-ray absorption, the lead-free apron. This with the lead is a 7 kg apron weight. Our is a nanoparticle coated is a 2 kg weight. So this is a huge difference. So now doctors are very happy with this. Then for the ISRO, we are producing 99% hafnium for their nozzles. We are making 320 kg per hafnium per annually and producing, give it to them. Then supercapacitor, we have made carbon of aerogel carbon, and we are making supercapacitor out of it. This is societal application. This is actually the thermistor. This is the breast cancer detection unit. This is the blouse. Inside the blouse, we have these thermal sensors. Any bed cell's temperature is less. So it measures the temperature scan the temperature, and if the scan the temperature is below the live cells, and then this is the scanning done by this through these sensors, and it will give the idea. Very cheaper technology we produce with Trichy laboratory we have done. Good one. Recently we did for COVID, COVID-19. All these swabs were imported. First time in India we invented these swabs. We reverse engineer it. It was coming from Italy and other places. And now we are producing it. Cost was 450 rupees per piece. Now cost is 7 rupees per piece. That is the difference. Now it is easily available in the market. So now we could do many testings. This technology has been transferred to other people. They are producing it. Then nano coating, like this is a nano coated masks. We have done the viral study and this one. So they kill the viruses when they sit on the top of the cloth. And basically these nanoparticles deactivate the surface of the virus when it sits on it. Then we made, so we can coat any kind of mask. So coating is 20 milligrams, 15 to 20 milligrams on each mask. Then this is basically the gel made up out of nanoparticles. We can have the gel. Any doctor can use this gel. It will last long, almost 5-6 hours of whole day. It will sense. Unless you wash it over hand, it will live with you, and it will protect from the viruses. So these are the technologies we have already I have explained. So this is my conclusion. Generally, I do. So there are many things to do. Many things. It's an ocean for us, and I think all today's engineers or postgraduate people should think how we can utilize our experience to the common man. And if somebody is having very high-flying ideas, come to us, we can implement it. Very low-cost ideas. Thank you very much, and thanks a lot for giving me opportunity, sharing our research. Thank you, sir.
Thank you very much, sir.
If you have any questions, you can. If somebody has questions, you can ask any questions.
परदेशी सर कन्क्लूड करा. परदेश सरला मला कन्क्लुजन करा म्हणा. साना सरचा आवाज चालू आहे जरी.
Hello, am I audible, sir? No.
Okay, sir. No question.
Okay, sir. If there will be any question from the audience, please ask the question by unmuting your mic. Is there any question? Sir, there is one question in the chat
Dr.
box.
Raghumani, any question?
It's okay. Yeah. Very nice talks. Very nice. I learned many things from you. Yeah. I learned many things because extensively given all kinds of photocatalysis, sensor, everything. I like your talks so much.
Thank you. Thank you very much.
Sir, one question is there in the chat box.
Yes.
I will
Can you read that question?
Yeah, sir. How can we synthesize nanoflower and honeycomb structure, whether either by changing parameters like temperature, etc., or changing the precursors, or there is any special synthesis technique, sir? This question is from Sai Supriya Lakshmi.
Yeah, basically, suppose you want to make a flower-like structure. See, some of the materials has a pristine structures are like that, like indium sulfide. Indium sulfide has a layer structure. Those are a layer structure generally. And if you do hydrothermally, like indium sulfide, cadmium sulfide, zinc indium sulfide, even you can say copper sulfide, copper oxide. They when you have hydrothermal, this should hydrothermal reaction, because growth cannot takes place within 1 second or 2 seconds or 1 minute or 2 minutes. Growth is a long process. In hydrothermal, what happens when it forms initially, and we are giving times 24 hours, 30 hours. Okay. So there is a growth in one direction or 3 direction or 2 direction. In one direction means you get a layer structure like suppose it's a graphene kind of things. It's a 2-layer structure. So one side growth takes place through these hydrothermal reactions. So when typically you want to have flower-like structure, then you should have hydrothermal reaction. Then honeycomb structures. Like molybdenum sulfide has the hexagonal type of structure. Any hexagonal type of structure, like zinc oxide also hexagonal type of structure. So there is a possibility of making such kind of honeycomb-like structure with hydrothermal reactions. How? So when initially you have a big complex of maybe suppose molybdenum, maybe I have ammonium molybdenum disulfate, something like that. Ammonium-based compound or sodium-based compound. Then use that kind of thing. So there should be some materials, combustible material inside, when you do it at 200 degrees centigrade or 220 degrees centigrade, not combustion, I say, it will be decomposed at that temperature and get dissolved in water or other solvent. So they make a structure, okay, they make a frame like of structure, and when inside the spores, this kind of some complexes which are intermediate complex, they are soluble in that solvent, they get dissolved and they create a cavity. They create a cavity. So this is the order structure sometimes we get in through these hydrothermal reactions, and only hydrothermal reaction. Suppose I want to see these reactions, we made cadmium molybdenum sulfide by hydrothermal reactions. We made molybdenum sulfide films through the CVD. That is again different structure. In there also the molybdenum sulfide we get initially we get layers of molybdenum sulfide. Okay, when you increase the concentration of molybdenum and sulfur, then we get a vertical growth of molybdenum sulfide. So that kind of structure also we observe. So CVD also will get, but not like honeycomb structure, but it's a different kind of structure. It's a structure. It's a single layer. On the single layer, we have small MOH2 plates. I could not show you that because I have that this one. Then we same time we make cadmium sulfide, copper sulfide on the graphene or on the molybdenum sulfide. So this heterostructure also we made, and we get a fantastic structure. Now these nano-hetero structures we are utilizing for neutrino energy capturing. That is a more very advantageous, very good project we have. So people are thinking that there is the neutrino energy is there. This neutrino energy can be captured and used for good purpose. So now we are collaborating with Germany. We are arranging one talk on 9th on this neutrino energy for capturing from the German scientist and through Maharashtra Academy of Science. 9th there is a seminar. Everybody can join and see how. So how this device also made, people have made devices, and how these devices can capture this neutrino energy, and these devices give the voltages up to 1 volt, 2 volt, 3 volt voltage. So that is very interesting. But how it is happening, we don't know. So we're in the process, simulation, all these things, and then find out what is how it is happening. Are you satisfied or anything he wants?
I think the participant is not there. So we wish she will be satisfied with your answer, sir. So if there will be one more question from the participant.
They can mail me, no problem.
Okay. So we will conclude.
Okay, thank you very much.
Next session.
Thank you very much.
I would like to thank to the Dr. D.B. Kale sir for giving his valuable time and guiding us with the different topics, and he shared the devices which their center developed which is very useful in such pandemic situation. So I thankful to the Dr. Bharat Kare sir from the Department of Physics and our college. Thank you very much, sir.
Thank you. Thank you, sir. Okay, then. Bye.
Yeah, okay, sir. Okay, thank you.
Nice text. Yeah.
Now we'll go to the next session, that is invited talk first. And as we have the resource person for this invited talk, Dr. N.R. Singh sir, scientist of chemistry division from BARC Mumbai, and the introduction of sir is already done in the inaugural function. So I request Dr. N.R. Singh to continue his talk and guide us. His topic of lecture is rare earth dope nanomaterials for light emitting display, light harvesting, security, ink, temperature sensors, and biological applications. So I request to Dr. N.R. Singh to guide us, to guide our participants. Dr. N.R. Singh, sir.
Thank you. So I'm very happy that today's Dr. B.B. Kare has given ons, for photocatalysis sensor. I mean, he has given ons. I'm very proud of that. He has given on applications. So today, today's I can say it is very useful to us that after listening. Can you show me that this one? Can you show me that? I don't see the screen. Hello. Hello.
Hello.
Which one, sir? Which one?
I don't see this my screen.
Okay.
Yeah. Also, good afternoon.
Good afternoon.
So in India, we can say good afternoon.
Yeah.
It is hungry, I know,
Good
because of this. And also, maybe it is suppose listening in Japan, maybe now say evening times, maybe taking tea and something. Maybe USA, maybe somebody is sleeping nicely. So I think that today I want to say very happy that actually on interaction through this webinar, and this platform is very good for the scientific community. And today I have opportunity to given me for this talk. So can you give me my slide was not seen, my slide.
Okay, you can share now, sir.
I share. Okay, just a minute. I share again. Again, I share again.
Yeah.
I share again. Yeah, I share. Yeah.
Okay, seen, sir. Okay, sir. Okay.
You see now? Okay.
Yeah.
Just.
You can start, sir.
Yeah, very good. Okay. Okay. Since that I know they're very hungry, everybody, so I just try to minimize as one as. There are DOP nanometers for light emitting display and light harvesting security in temperature sensor and biological applications. I belongs to the chemistry division, provide to me research in Mumbai. Any questions, any query, any doubts, you can email to me. My email is rsn@brc.gov.in. Okay, and so I thanks Dr. K.M. Jadhav, Dr. B.A.M.U. Aurangabad, and he's my senior colleague and collaborator, and Dr. Ashok K. Pandit, convener of this conference, and Logan Organizing Committee, Department of Physics, the Sorrento College of Arts, Commerce and Science, Shirot, Aurangabad District, Maharashtra, India, for inviting me to deliver talk through the online in 2 days national conference on recent advances in material science and technology. This is very important today. Today, I just try to minimize, so I just give some few areas. There is the rare DOP material for light emitting applications. Second is the rare DOP nanometer for light and energy harvesting and temperature sensor and optical switching and the security in. Rare DOP nanometer for biological applications. You see periodic tables. Now periodic tables, the left side hydrogen, you see the right side helium. Just on and then in between this D block, P blocks, and yeah, on S block, P block, D block, they can make any materials, whatever materials what people want. But now today already I discussed the rare earth. So rare earth, we are talking rare earth because they are rarely available in the earth. So this is one of the rare earth we want to say. Scandium ytteria is included in the in this rare earth. So that rare earth we talk about the lanthanide and actinide series. In addition to this, scandium ytterium is important. It is also included because they are not available, and they are always some they found in similar rocks and minerals. Abundance is 1 to 66 ppm, except chromatrium, it is a radioactive 10 to 15 ppm available. So I just talked to you in the chemistry point of view. The P block elements and S block elements, you see S block and D block elements, F block elements. So you see here, this S block elements, you see outermost S electrons, P block is outside is the P outside outermost the P. D block elements, they have that see in the 3D5 4s2. But if you remove the electrons, in suppose manganese, if you remove the electrons, 3D5 electrons are remaining. Okay, so and in case of F electrons, European suppose example 63 atomic number, but you remove 3 electrons because the stable oxygen state 3, so this 60 electron. Okay, this so when the electronic configuration is in 4f6 is surrounded by 5s2, 5p6. So when you European or manganese interact with the ligands, okay, So surrounding ligands. Always the manganese 3D5 interaction was there. But European cases, for F6 doesn't interact anything. So this because of the thing, most of 3D series, the absorption course is very, very broad because Christian pin environment affecting. But in the case of F electrons, doesn't affect it, so they are the FF transition very sharp. So this is, but all our transitions are very, very weak because FF transition and D transition are forbidden. So these are manganese emission, you see absorption, you can see very broad peak, okay? But in the case of europium or lanthanide, for example, europium is actually, they have the magnetic dipole transition 5D0 to 7F1 at 591 is very sharp. But in the case of electric dipole is 5D0 to 7F2 is 615. And this is the very, very sharp. So these transitions are used, possible or F-block transition, usually possible is the FF transition, FT transition, and methane transition, okay? So electric dipole transitions, you see the 4S, spin Sooner change is 0, delta N instrumentation quantum number is less than 6, and the spin orbit coupling delta J is less than 6. This so-called opposite parity is called electric dipole. And the magnetic dipole is the delta S 0, delta N 0, and the delta J is 0 plus minus. This was same parity. Magnetic dipole is really allowed. For electric counterpole, you see this is there, okay? Then sometimes JJ mixing, okay? Mixing keeps the possibility of the transition. See that I want to tell say selectivity of this one, but for the FF D block elements, delta S is the spin around transition, delta N is the orbiting around transition. This origin. Sometimes relax because of the spin orbit couplings, and sometimes harmonic couplings and mixing. So I will not explain too much because they are hungry, I know. So the europium for F6 is actually you see here the electronic configuration. If you see that for F actually 6, so they can transition for F to 5T transition, and in any environment cubic or this one, any environment 6 coordination or 8 coordination, 9 coordination something. But because of the electronics repulsion and the attraction, they can have the ground state to the excited state event. Okay, this is called ground state is called 7FZ, and excited state 5D0, 5D01, 5D02, 5X6, and G. So many excited state. Okay, depend upon your how the attraction and the repulsion between electrons and F electrons. But when the spin orbit coupling and that is ground state configuration, you see here 7FZ. This one. Okay, so this splitting 7F0, 7F1, 7F2, 7F3, 7Z, 6. Okay, so this then you see in the 50 in the excited state. You see now absorption cross section absorption occurs actually 5D0 to the 5N694. Okay, absorption. Okay, but emission usually occurs lowest excited state event 5D0 to the 7F0, 7F1, 7F2. This transition is called 580. It's called 5D0 to 7F0 is the not route transition, okay? Because J0, the Gen 0 is not a route transition. But 5D0 to 7F1 is 591 magnetic dipole transition. 5D0 to 7F2 is the 6PF, this electric dipole transition, okay? Still, this 7F1 and 7F2, the Christian pin is means particularly crystallinity very high. You can see very stark splitting, okay? 7F1, you know, this again a 3 stark sub-event, and 7F2, 5 stark sub-events. So lanthanide compound, you see, I tell you that today that there are most focusing. So lanthanide compound is the europium oxide, it's a dispersion carbon, you can come across many later art, okay? But still, the luminescence very sharp, but the poor luminescence, okay? But the poor luminescence lies due to the necessary FF transition, this comparative selection rule. So in the simulator, lanthanide is sometimes people doping because to enhance luminescence. So this actually are doping because of it to enhance the luminescence because they reduce the cross-section amongst the lanthanide ions. This is called consequencing effect. However, this forbidden natural transition can be relaxed by Christian pin when the lanthanide ions occupy the site. Therefore, few amounts of lanthanide, 1 to 18% to ppm level, are dropped in simultaneously in order to reduce the cross-section. I want to explain you how the cross-section happen as the basic science. You see, I am talking that most of this lanthanide, I told you, lanthanide usually drop in the force. The host is actually Y2O3, is semiconductor. This semiconductor is this host is this is doesn't show luminescence. Okay, so this luminescence doesn't show luminescence. Okay, this is a host. This is this two-dimensional host. You see oxygen Y or something. Okay, in that you drop, but in the case of europium oxide, it's the same. You know, the cubic structure you see. This europium is they have the electric dipole interaction. Okay, because of this, the cross section happens. But when you're doping in the europium, the Y2O3 europium, just small 1 ppm, 2 ppm, or 1 atomic percentage doping, it's going to host gas relationship. Okay, you see europium distance. If you see a europium distance is more, in that time cross section between the europium is reduced. Means electric dipole reduced. Okay, so I want to explain how the concentration effect you see here. The europium 1, who is excited by the suitable light, T94 again, and goes to excited stellar band and come back from 501 to 5G0. But if we're having nearby europium, another europium ions, and this when this transfer from 5G1 to 5G0, that this 7F0 to 7F3 transition occurs. This energy when try to come down to the one energy is now is reduced because this nearby europium has absorbed. Okay, europium 2 has absorbed. So this is called concentration quenching effect. But if the distance, the europium distance very far away, this concentration quenching was reduced. This is why happened. We are dropping 1 or 2% or 5%. Advantage of lanthanide doping in semiconductor. Large number of proton can be absorbed through the band gap of semiconductor. Doing this, many electrons from valence band can be brought to the conduction band. Many holes are created in the valence band. Electron hole recomposition may give the emission. If the emitted light from semiconductor could be absorbed by the nearby dopants, emission intensity is very high because of the energy transfer from semiconductor to the lanthanide ions. See, now is this light emitting diode is one of the interesting and very useful for our society and for the energy saving. So this Nobel Prize goes to 2014 in physics. This is the Japanese group, Isamu Akashi and Hiroshi Amano, then Suji Nakamura. They have won a Nobel Prize in 2014 in physics for invention of blue light emitting diodes. They produce a light blue light emitting beryllium nitride, okay, base. They grows the Nobel Prize. This actually what happened is, but only thing that how happened is actually the Akashi he started the beryllium nitride papers in 1990, and after later on Amano had joined as a PhD student under the Akashi, and they started that beryllium nitride fabrication, okay, for the blue light. Then, but when they preparing beryllium nitride, they use ammonia as a reducing agent and the nitrogen, okay, nitrogen source. But when they heat, when the compound preparation, the luminance and quenching, okay. But when the irradiation or heated, the luminance enhancement. This explanation was given by Nakamura in 1990. What he said, when you heated when you have compound preparation beryllium nitride, ammonia is decomposed nitrogen and the hydrogen. This hydrogen is sitting in your intrusion side. This then luminance quenching. So he give the this mechanism, and because of this they share the Nobel Prize. But questions like come to me, whether only beryllium nitride base is solved in light emitting diode? Answer no. Only beryllium nitride cannot solve on this. It needs rarer earth to produce the white light in colors. This only, okay? So blue light is just source only. To produce a white light any color, it needs rarer earth because they are very cheap as compared to any compounds. So in that time, before the announcement on Prize, I was submitted my paper to 14 in the February. I submitted. In that time, I saw the important beryllium nitride in one of my focus mission science. My PhD guy is Professor N.S. Gusby from Nagpur, and so I was working with him in the PhD in my PhD time, and we published synthesis and electron transport properties of transmitted nitride and applications. So this we saw that important beryllium nitride, and then we saw that beryllium nitride want to produce a white light, then beryllium nitride have to cover with the zero emitter. This is called Y2N2O2 cerium. Cerium is a layer out. Okay, from that you can produce the white light. From the white light, use the band pass filter, you can get any color, blue, green, red, okay? So that you can close. So you can see in details how to plot the normal price was written in this paper, okay? So I'm lucky that we, in the time before the normal price announcement, I written this ministry about we can write right. You see two types of luminescence actually. Luminescence, what is it? Luminescence, I told you that you excite light, any kinds of mechanically or any source of light, and then they remove your excited source, emitted the excited electron come to the ground state. This called electron emission occurs. The emission occurs. But two types of emission. What is emission? You see here, one is down conversion, and one is the up conversion. So left side is the down conversion, right side is up conversion. Down conversion, what happens is you see ground state of semiconductor because the excited state is the actually I want to say excited ground state is actually we call valence band in the semiconductor. Excited state in the case of the semiconductor we call the conduction band. So electron going from the ground valence band to conduction band. Now excess electron in the excited state conduction band, and then after the happening this come down to the some trap event. Okay, and then from that emission occurs. So now some energy is lost coming to the trap event, and because emission occurs, so energy absorbed by the semiconductor is more than of the emitted light. This is why energy loss is called down conversion. In the case of up conversion, what happened is what happened is now thus the ground state to excited state is electrons going, okay, but now the excited state there's a trap there is a levant. So that electron can sit sometimes, occupy some position, sometimes, but the microseconds, okay? But transition occur, nanosecond, okay? The transition occur. Because what happens is, microsecond longer lifetime, before coming down, another electron hit this, okay? Hit the excited state, okay? This is like a one bond going to the upper level. Before bond come down, one bond another hit, okay? And then hitting then another the excited bond hit to the go to another excited element. Okay, this is gone. Then after this excited energy level, another level, come down to the excited ground state. In the time, the emitted light energy is more than of the absorption energy. This is visible only most of the we do the continuous excitation. Okay, CW. Okay, wave excitation. This is we call sometimes nonlinear phenomena occurs in the case of conversion. These two will be discussed in today. Down conversion use a luminescence actually example actually. There are two neometals similar or antenna force and a gas. Okay, you see semiconductor's conduction band, valence band, conduction band, absorb the light, electron goes to the conduction band, and go to trap band, emit occurs. But if you have the antenna ions nearby these electrons going to the trap band is transferred to the excited state level of the antenna ions. So because of happening this excited this one because of this it can emit occurs. Okay, but only thing I want to tell you, without the semiconductor this antenna absorption process is very weak. But since the semiconductor absorption process is very high, this energy transfer is very good. So this why emitted light is very enhanced. Okay, this doping is very important in the semiconductor. Okay. Now how to prove that the pure europium oxide is that compound and doped SNO2 europium we prove. You see excited state or absorption cross section. You see europium oxide they have the 395 citation absorption, but you see unitary is around 20 this one. But in case of the SNO2 europium, the absorption cross section is better. Okay, around say close to 100. So it means this is the one of that we want to explain you that the doping in the semiconductor enhance the absorption cross section. This actually one of the first gas that the semiconductor and the antenna ions very important. You see, I want to example I give you that GdPO4 is the GdPO is gadolinium vanadate. See doping of the 2% dysprosium. The absorption cross section is very high in vanadium oxide transfer around 300 nanometers, but only thing that the dysprosium, the absorption cross is very weak is in this ground. You see, if you expand this, you see 354. Okay, 354 they have the ground state or this absorption of the dysprosium, but but this but one oxygen transfer is very strong. So you see how to see that how this emission how to occur this exciting from the 100 oxygen transfer or dispersion oxygen, okay, or another dispersion oxygen transfer around to 270 also, okay. So this light part of this compound, you see that I exciting 270 the dispersion oxygen transfer, 310 is 100 oxygen transfer, and 354 direct dispersion absorption, okay. Now I see 310 is the highest absorption or emission occurs, okay, and this energy transfer to the dispersion, this dispersion emission occurs, okay. And this, and then after that, you know that the 270 dispersion transfers were then 354 very weak. So direct excitation of the dispersion is very weak as compared to 100 oxygen transfer. Okay, so this is the one of the why we are dropping in the end, why this similar use. Okay, and this after that you see we are compound, we have PPR many compounds, means another GD BO4, YBO4. We prepare doping with the dysprosium, europium, samarium, and the thorium. You see that we make that, you know, water dispersion, dispersion green, and europium red, you know, the samarium brown, brownish colors, samarium blue. So again, we make a thin film because thin film is used for the our light emitting display unit, and this liquid disbursement is used for the biological application because bioimaging we can use. Okay, so this we use for applied work. I take opposite for that another just quantum dot, just also Dr. BB Karya has explained. Just quantum dot, I just explained one or two lines in addition to his. Okay, quantum dot is actually, you see, BBC quantum dot is this actually emitted light mostly in the near light emission. Okay, so you see emission and the quantum dot prepare for injection method. You prepare different size of particles. You prepare from, you know, emit from 100 to up to 1600, but they can emit up to 3000. Okay, centimeter inverse. Okay, they can nanometer 300. Okay, 3000 nanometer. Why this happening? Because the BBC quantum dot, they had a set of voltage is around 50 nanometer. Because of the less than 50 nanometer, the particle size, they can show the quantum side effect. Okay, emission and absorption can change from visible or UV2 to the up to 300 nanometers. Okay, so 3000 nanometer they can sense. The wireless changes. Okay, because of the excited voltage is really large. So this then you see quantum dot. How just explain you? Okay, that actually what is quantum dot? Quantum dot actually is a small size particles, but the size of the diameter size or this less than voltages. Oh, another way is another produce quantum dots. Even sizes bigger. Okay, maybe more than voltages, but it can produce a quantum dot by changing dielectric medium. Okay, even dielectric medium can change voltages. Even particle size more voltages, you can bring the quantum dot by changing the surrounding dielectric mediums. Okay, this also can be brought by the. Okay, this I want to addition to the BB Curry. I want to explain this. These two things can happen in the quantum dot. So quantum dot, what characteristics of it is the absorption. You see absorption. This blue line is the absorption of the here. Okay. Now in the BBC quantum dot, you see here. You see E0 is the lowest energy absorption. Then E1, E2, E3. This is called a discrete energy level for it. Okay. Quantum dot for the absorption in the discrete energy level. But emission occurs in the only you see red region is emission occurs and nearby to the lowest energy levels. This is a quantum dot characteristics. Okay, this is a characteristic quantum dot. You have to show this. Okay, so what happened? This valence band conduction band indicates a quantum dot, but since the particle size smaller, it is the band gap increase. Also, they have the valence band conduction band. They have the discrete energy level. This discrete energy level you can see in CPB's quantum dot. This is one of the characteristics of the quantum dot. How to expand? They have to show discrete energy level. Okay, and also band gap should be increased. This is the characteristics of the quantum dot. You see different quantum dot, PBS quantum dot. You see PPR different size. You know this one, the star shape. In star shape, you see here the nanolod. You see different aspect ratio of the diameter and the length ratio. So different can use PPR. Okay. Also, spherical particle, 3 nanometer particles, 5 nanometer, and 7 nanometer, and 9 nanometer. This is monodisperse. You see plus minus 1 only. You can see. Okay. the error bar. Okay, this is very quantum dot because this use no water content. This is the whole injection. Okay, this is wonderful that you can prepare monosphere particles. Now, how can you use this PVC quantum dot? This is one of the important in the point of view. The light harvesting is more important because what happened is in our source light, you see 3 to 5% is coming from the less than UV light is coming to our Earth, but 40% or 45% it is visible light. Okay, but above this, the visible light is 50-55 is lost energy, which we don't use. Okay, this thermal energy we don't use. Okay, this means near light we don't use. So this is solar spectrum. You see solar spectrum. It's a 500 is the highest absorption, 500 nanometer is absorption, but energy again lost. Okay, here. So this is the absorption energy because of water content making they absorb light. Okay, this is because of this. Okay. Now just how to simulate this spectrum. You see we prepare the PVC quantum dot. That this you see different size of quantum dot we mix up. You can see they absorb from the UV light to the 2500 is the actually solar light. Okay, they absorb light. You see here quantum dot they absorb anything. Okay, this absorption because of this absorption they can produce light. Okay, but now this light the absorption, how to prove this absorption of this near light? You prove by the photoconductivity. What is the photoconductivity? In the presence of light, electrical current is coming off. Okay, then you call photoconductivity. Okay, it means light driven light produce the conductivity. Okay, so we see one of the we have proved that PVC quantum dot. You see here, this is the blue light is actually without this light in the dark condition. We see photoconductivity means current versus voltage. We can see you see here the blue light. You can see electrical conductivity means this is actually light without the light means in the dark condition the PVC absorbs the near light and the conductivity occurs. Okay, and then when the light is passing in this, okay, so just those light will pass on it, electric conductivity increase. So it means they are absorbing visible and near light. This is proved by our paper. This one. Okay. Another was I told you that most important today is the white light emission. Because white light we can get the all light you can produce because you can get anything because you use the copper band pass filter you can produce. You see here we prepare by the this one white pure dysprosium drop something. So as prepare sample use blue light, but heated 509 to produce the white light. From this white light you use a band pass filter. You can see white, blue, green, yellow, red. Okay, you can get many things. We publish transfer communication using 12. So from that, this PVC, this dysprosium dop, then lithium co-doping, we can produce the blue and the white light. Okay. Another was there some paper just want to publish in Nordic Chemistry one paper we published on 14. What is some lanthanum vanadium? Okay, lanthanum vanadium. Many people say tetragon phase is more than of the monoclinic phase or hexagon phase because tetragon phase more dominance in the European topic. But we explain that not necessarily tetragon phase more dominance. We prove that even other phases like monoclinic phases may be more dominance. So you see here, you see this bar diagram. You see here bar diagram. This red region is a monoclinic phase more as compared to the tetragon phase because this system when compound prepared they source the monoclinic tetragon phase. Okay, the XRD. Okay. But when compared to XRD monoclinic tetragon phase, the monoclinic phase is more, but still luminescence enhancement. So how to explain this actually? This actually compound is the lanthanum vanadium, europium, and co-doping of the bismuth. Okay, the bismuth co-doping happened is the monoclinic phase is more, but bismuth is SP the absorption in the UV light. Okay, because bismuth is absorbing as a as a sensitizer. They sensitize. Means what is sensitized in the luminescence activity? Sensitive activator to term is there. Activator means luminescence produce. Materials luminescence produce is called activator. Sensitizer is that they do not produce the emission captured by activator. Okay, they just absorb the light and the energy transfer the activator. Okay, this is sensitizer. Okay, so in this case, said lanthanum vanadium, europium, and drop it with the bismuth. Bismuth absorb light as a sensitizer. The europium produces emission. This europium act as the activator, bismuth as the sensitizer. This is one of the beautiful words we saw here. Then what happened is, the beautiful of this the luminescence, like sensitive to the activity in its transfer. This is one of beautiful. Okay. So one of we work in the the GDPO port. Okay. GDPO port is the post back. We are terbium dropping. The terbium dropping usually that those the emissions green emission occurs. Okay. Green emission you see here around 550 blue and blue and green also. But you see here. But when the terbium is actually when the serum doping, enhancement of the terbium. Why? Terbium absorb light in a 300 nanometer. The energy is transferred to the terbium. Why terbium? The terbium, because 500 terbium in the 355, the emission occurs, serum absorb light, emit occurs in the 355. This 355 emitted light by the serum is absorbed by the terbium. Terbium absorbs this, okay? This terbium absorption pattern is this energy is transferred to the serum from the serum to terbium. This luminance enhancement. Okay. This proof how to prove that. So you see, terbium serum is just fixed 20%. Terbium amount increases. Okay. What happens is the luminescence of emission of the serum is decreasing, which terbium is increasing. Means energy transfer increase because the terbium the absorb light more and more from serum. That's why you see 355. Emission of serum is reduced with the terbium amount increase. This is called energy transfer process. Okay, this was serum as a sensitizer and terbium as an activator. This is the one of the useful properties. Okay, of the enhancement luminescence. Okay, this concept I use again antenna force back. Then happen is another was there is a serum for this for serum terbium. That beautiful this. Can I use this? Some other kinds of sensing types. So, but you see here this the phosphate serum terbium system, I put potassium permanganate, the luminescent points. But I put ascorbic acid, luminescent recover. So means what is actually lowered is actually potassium permanganate happen is that this is reducing the oxidizing agent. So serum 3 plus that is a port F1. Okay, the port F1 when potassium permanganate you're putting this potassium permanganate putting oxidize the serum 4 plus that. Okay, this 4 plus that. Then this because of serum doesn't have the port electron. So this way, whatever you're exciting around 300 or 250, it doesn't absorb anything. Okay, all non-reactive process coming. Okay, this is the happen in the case of this. Okay, serum 4 state. Yeah, when additional potassium permanganate. But when ascorbic acid, then hopefully the serum 4 plus state and the serum plus 3 state. Then now port F again recover. Okay, port F1 happen. So luminescence again recover. Okay, so this is actually the redox section. Okay, we can do this. We can do milliseconds, and this can be used as a glucose sensing because ascorbic acid is a reducing agent and glucose also reducing agent. And for some permanganate and hydrogen peroxide, we can use as a sensing in this system. Okay, so this only we can do the sensing of this through the redox section. And now this actually the beauty of this that sensor sensitizer. I can work in the in the white paper. We thought that. Okay, so what happened? We thought that actually okay, sometimes white serum is we know that the very good sensitizer. Bismuth is a very good sensitizer. So, but in the case of white paper European, the serum or bismuth we are doping. What happened is after doping, we thought that luminescence may be enhanced European, but luminescence again quenching. Okay, but we heated around 900 degrees Celsius, luminescence again recovered. So how to explain this? We published 2 JAX paper, 2010-11 without any revision. They explain that what happened is white paper European is actually this is the tetrahedron phase. But when serum is bismuth, serum is the ionic size and the bismuth is ionic size more than of the European or white. Okay, because of the ionic size increasing, this one white paper tetrahedron phase in the hexagonal phase. The hexagonal phase is like this hexagonal phase. They have water was occupied in the pore. Okay, C-axis. Okay, like a zero structure. Because of this, so when the transition from the tetrahedron in the hexagonal phase, the water absorbing, so luminescence is quenching because what presents water. This is how to prove. We prove that actually when compound preparing water medium, luminescence quenching, but D2 medium preparation luminescence enhancement because the water having the overturn and the second overturn can absorb the European emission. Okay, but that's for the D2 having the vibration energy less, they cannot absorb this. They cannot be matching with the European absorption. Okay, this side luminance enhancement explosion. So this we prove by the TG mass spectroscopy, others techniques also, but I will explain many things, okay? This is actually very simple. I want to say in any compound preparation, you cannot remove the water in the surface, okay? This is already we know. But water is in the surface, they have a 4 hydrogen bonding. This is I show you 4 hydrogen bonding. Water molecule in center is surrounded by 4 hydrogen bonding. And but in the pore, nanopore doesn't have proper hydrogen bonding. This proper hydrogen bonding does not dare having just like gas, okay? The gas like okay, just doesn't have proper hydrogen bonding. And this water in the inside pore in the surface water, which can be differentiated. Okay, how to differentiate? This is Swiss NMR is one of the techniques you can prove. This Swiss NMR probe you see here, this white paper European serum of this system. This example happened is that you see NMR, but how to take NMR, proton NMR happening? Because water is the one we can take as a proton NMR. NMR we take NMR because of Brownian motion. Okay, the all proton or molecules are moving with the Brownian motion, so we can take the average view. Okay, that's why NMR when we do NMR we do the liquid NMR. Okay, we do that. Okay, we do the solvent use or DMS or chloroform use, okay? But the Swedish NMR, in the time of the inoscopic interaction energy increase, okay? So because of that kind of interaction increase, this NMR is very broad. So to avoid this, what we use the Swiss NMR technique. This called we using this magic angle, and we apply the frequency around 10 kilohertz frequency we apply. You see here 300 degree Kelvin means room temperature. You say that NMR we take the NMR. You see here 1 peak is belongs to this 5 ppm is belongs to surface water, but you see have some harm around less than this 0 minus ppm. You can see this very harms. But keep on decreasing the this temperature decreasing. You can see some another peak. This is actually. But when the we don't use any this one. Frequency, you see already this hub was remaining, okay, but surface water frequency. So this proves that the surface water is quenching in the minus 50 degrees centigrade, but pore water doesn't quench, okay? Means water doesn't have in the pore, it doesn't have the proper hydrogen bonding. That's why there's a gas type, okay? And this, we cannot do more than minus 50 degrees centigrade because NMR tube doesn't work less than minus 50. So this is a first report we proved this, okay? So this then we have the neutron physics in the BRC. How we can do this compound? We use the neutron diffraction studies, and we published 2018 and 19 published on two papers. And this you see here, you see the white paper. But we cannot do water because water is the scattering factor very high in the case of water absorbing the neutron. So we use a DTO, and we do prove that this white paper having the two types of pore. Okay, one is the hexagonal pore and the triangular pore. We prove by the output. This we prove that. What happened is we prove that when we fitting with the event program. Okay, so without the water content, we just prove we different fitting, and with the water content, the triangular and the hexagonal, this is fitting better. So means we prove that this is the one of the D2 having the water or D2 having the occupied the hexagonal and the triangular pores. This we prove by the, you see here, I want to show structure, the three-dimensional structure. You see here, water here, and pore, and another water pore in the triangular and the hexagonal pore. It's proved by TG analysis. You see here. P1 is actually it is surface water, and P2 and the P3 is a triangular and hexagonal pore. Okay, this will prove by the TG analysis. Okay, this is proved. So this original work from BRC Mumbai so far my last 16 years in BRC. Finding of water molecule in the pore of the layer phosphate by TG mass spectroscopy. Distinguish the water molecule in the pore in the surface of water particles by Swiss MR. Stability of the water molecule up to 800 degrees centigrade. Decrease of freezing temperature of water down to minus 50 degrees centigrade. Finding of water molecule in pore, triangular, and hexagonal by the neutron scattering. This is the origin of the work from BRC. Now outcome versions. So that outcome version we published on 2019, published in the December issue of these papers. The near far right negative responsive sodium fluoride and composite for hyperthermic application induced by the fluorescent resonance in transfer surface problem absorption. This I will not explain all because time is limited. So sodium nitrogen fluoride is very good host for the upconversion because the non-nitrogen process will be less. And then when you see that we excited light, 980 laser is the, but we produce emission, the green. 980 we cannot see by eye, because exciting in near light, but we can see green. Green means we prove that energy is converted from the near to the visible. Okay. This green emission, the two green emission, you see green emission, they have two transitions. One is the transition you see there. One is the from this another green one, another green one. Okay. You see why we using YB? YB using because YB is a sensitizer. They absorb the light because absorption cost is very high and the energy transfer radium. Okay. YB to radium energy transfer. But this absorption of emission of this this is 520 and 545. This is very good for the sensor. Okay. What happens? You see, if we take this this one, okay, this 298 room temperature, this 545 emission is more. But when a temperature increases around 673, means around 400 degrees centigrade, this 520 is emission. The emission is more. Means what will be happen this? This transition is very close. Okay, means IS11 2IS11 by 2 and 4S 3 by 2 is very close. When the temperature increases, because of the Boltzmann distribution law, the electrons going from the another excited to the higher excited state level. Okay, because of because of Boltzmann distribution law to follow this, and from Boltzmann distribution law you can use a temperature sensor. You can see next slide. Okay, you can see the how temperature sensing. Okay. And also you see that this very good green emission by this compound, but how this is going to use for the how to use for the heating? How heating is happen? You see here. This one in a heat energy transfer. For instance, in a resonance energy transfer, you see here the upconversion particle. Okay, the water dispersion, silica coated, and this excited by 990. The blue light you see, green light is dropping, dropping by the auras. You put in the auras nearby. Absorbing the light, this light is absorbed by the auras. Because auras is because auras particle has the surface plasma absorption around 550. Okay, this absorbing light, this then produces a heat around 40 to 40 degrees centigrade. This absorption light, this heat is important killing of cancer cell because the particular cancer cell can be killed by the 40 degrees centigrade. This is called hyperthermal treatment for cancer cell. This can be used as photothermal heating. This form. This I told you that this transition I 520 to 545. This is called fluorescence intensity ratio gives you temperature sensor. You see next slide. You can see here. This next slide you see here. You see a parade is called fluorescence emission ratio, intensity ratio, and temperature how variation. Okay, how this. Okay, so this a parade increases, temperature increase. Okay, this is we can see up to as a sensor you can use up to 350 degrees centigrade can use easily as a sensor. And also you see here that this thermal, how to put the temperature analyzing, we prove by the thermal camera. Okay, this one infrared based thermal camera can see temperature. Okay, so now this nanoparticle we prepare various down conversion, up conversion nanoparticle can be used as security or anti-counterfeit, okay, or alternative. So this you see here, we make the water dispersion and the oil dispersion nanoparticle. This used for the as a security point of view because without the nanoparticle, we cannot see the light. In presence of light, this excited light, you can see the light. Okay, means nanoparticle present, you can see. So we can see my paper is belongs to me or authoritative, which is we can use as a this we can use. Okay, and you suppose in the pens you put this nanoparticle. Okay, in the mix up with your pen inks. Okay, you can light something. Okay, then you can put the nanoparticle this light. You can see the light means this pen belongs to you. Okay, or the ink belongs to you. This is very important as authenticating. Okay, as a security point of view. And this extensively we are working in the VRC now. Another was the suppose in the dark light means you cannot see light. That time how to see that this money is 100 rupees, 200 rupees. So this one of the we can do this called persistent luminance. Okay, persistent luminance. What is persistent luminance? Without light also you can see light. Means in the daytime discharging. Okay, they absorb the light from from daytime in sunlight, then the produce emission continuously. This is called discharging. So nighttime is discharging green emission. You see here, discharging. Okay, this green emission you can see. So blind people, suppose I putting the blind people or any suppose nighttime someone want to see, you can see light. Okay, night, but blind people have to I put the 100 not directly written in the printing. Put some height the parchments. You can see it by touching. You can see it one ice, two ice, one say 5 ice. So they can see distinguish. Okay. Now most of currency not use a star or just a diamond shape. Okay. This for this okay for currency more distinguish. Okay. So those things we can use, and this actually all this based on the concept of the nature having the this you see our peacock in its horse, meaning this is based on the all this actually we are this on luminescence based. Okay, this is only I want to say currency not can be distinguished by the UV light or near light. This will develop in our PRC. The biological application I will explain because on hungry I know this one actually I want to tell you that hyperthermal treatment for cancer cell. I know many treatment cancer therapy, chemotherapy, radiotherapy, hyperthermia, many treatment was there. Okay, I will explain those. Today I want to explain all the hyperthermia treatment. Hyperthermia, what is hyperthermia? Our normal body temperature is 37 degrees centigrade. But temperature above, okay, we call hyperthermia. This hyperthermia temperature means normal cell cannot survive, but cancer cell can be gained. Okay, this actually how people use this actually long back, 50, 100 years back, hyperthermia treatment has started. Not now, okay. But originally that in the time they use extracellular heat treatment. They excite light with the IR or water bath and microwave use, okay, to produce heat. Now the nanotechnology comings, we are now using the nanoparticle can heat this okay, produce the heat. This is called intracellular. This you can see using next slide. The left side of this extracellular hyperthermia is the current approach is a cancer sand is surrounded by the some our extracellular tissue. But see in this water bath I want to produce the 40 to 40 degrees centigrade. I have to use more higher temperature for ultrasound and microwave more. Because of this, you have to heat. Suppose you want to do 42, you have to heat more 45, 46. Then normal cell also die. Okay. Or because I use microwave something, the whole body was heating. Okay. So this is one of the that have the whole body surrounding bodies are heated. This is not good for the cancer treatment. But another new approach, this is called emerging approach, the intracellular hyperthermia is actually nanoparticle going to the cancer sand, apply the estimated pins around kilohertz frequency, heat produce. Okay, all the cancer sand can be gained by this. Okay, this one intracellular. This was developed in our this one. See, you see, this is the test sample we developed in this one our lab, and you see, suppose cancer sand is there in the hands. So apply the nanoparticle inside this, localize or intravenous IV. Nanoparticle accumulate to the cancer sand, apply SA pin, you can see the heating. So you can see more paper you want to see this is some of our book chapters. So many example of the today I just tell you that we have many work in the the feature for the transmission meganite, against ferrite, there are DOF, beta emitter, copper sulfide position emitter. You can see many paper or paper. You can see more details. I'm going to explain more. So this I tell you that in the case of major nanoparticles, you said major nanoparticles absorb the light of the absorb the estimated pins, and you see that they produce heat. So I'm going to explain this section. This heat produced because of the Hessius loss and the AD current also, and Nernst recession and Brown motion. Okay, I'm going to explain this today. So that now happen this cancer cell can begin more something. You see here one of the we do cell variability test. Okay, control one. We use the M7. This M7 is a magnesium nanoparticles we are putting biocompatible. But when the already sequestered nanoparticle cancer cell is more thin. Okay, this is proof. In here we prove that iron contain more or iron contain same, but the already sequestered is nanoparticles better in of cancer cells. Then we do the in vivo in the mice experiment. This usually happening. The cancer cell is we inject to the mice in the mice. Okay, localized injected in 0 day. After either 10 days, growth about 1 centimeter cube growth, and then we apply the magnetic pins, and then particle injected in the tumor region, apply magnetic pins. So we do the 9, 10, 11 days. We do the different times with the particle injected or sometimes acid pin applied. So from that we found that more and more you apply the acid magnetic pin, the cancer cell growth is decreasing. Okay. This time we do the histophysiology, how the this how the mechanism of the killing something. Okay, so by description we have done. Okay, so I just explain just few actually how to prove that actually how to prove the cancer cell is decreasing something. We use a suppress expressing this blue light. Okay, this we put in the with the nanoparticles. Okay, nanoparticle together something. This is our luminescence patterns, and then happening we see different time of the estimated pins. We see that under the magnetic pins, the blue light means cancer cell is died. Okay, and this proved by we can see by view also we can see. Okay, decreasing. Okay, this is actually we see in the mice experiment. Another was treatment of the cancer cell. One treatment is deoxyglucose. Deoxyglucose. You see, cancer cell. The cancer cell happened is this cancer cell usually happened is most of cancer cell they actually uncontrolled growth. They need glucose. Okay, and glucose in this glucose and they consume, the uncontrolled growth happen. But if we do not glucose not giving this side, cancer cell whatever cancer patient we don't give glucose because the growth of the cancer is more. This happen is what happened is actually this deoxyglucose when consuming they produce glycolysis and ATP produce. Okay, energy produce, and then the cancer cell growth increase. But now this instead of this something we this one OS group, okay, is removed. We got 2-deoxyglucose. This 2-deoxyglucose, if then what happens to 2-deoxyglucose when going to consume by the cancer cell, it doesn't produce the glycolysis because it doesn't produce the glycolysis because the one OS is missing. Okay, this 2-deoxyglucose can be used as a anti-cancer drug, and also because of this nanoparticles when this nanoparticle attests this deoxyglucose, the glucose was accepted by the target accepted by the cancer cell, and more accumulation of nanoparticle occurs. Okay, then this nanoparticle accumulated. Then happened is now because of this nanoparticle goes to the cancer cell happening, starvation of cancer cell happen because it doesn't produce glycolysis. So cancer cell can be more. This is one of the that people use a positional emission topography. People use this concept. Okay. Now we are working many. That we are working one of the persistent luminescence means the excited light and the UV light, and emit a few hours. So you see here, you see one thing. See this persistent luminescence silicate base. We excite light, okay, and in the test tube, or beaker, and then emit then inject to the 10 of the head, 10 of the mice, and then nanoparticle and drug together going in the different part of the body. This in the tumor region more accumulation happens. Okay, so now this is working last for 5 years. Now hopefully we can publish this year. I think this paper. And then this actually one of the good things that this deoxyglucose is a targeting. Okay, molecule. What about this because of the cancer cell targeting. Okay, and this now the PET scan is very expensive. You want to PET install PET is 100 crores necessary to install this. Very expensive, and because of expensive, the cost of the treatment of through the imaging or diagnosis by PET is very expensive. So that can be replaced by this nanoparticle base. This is where we are working. And the arthritis. Arthritis is one of the most common form of the slowly progressive systematic autoimmune. Is most happen in the the joints of our bones, and this is most affected in the agent populations. This was actually how to cure this. So many people use the abrasion of disease, okay, or people use the surgical type something. They remove the part of this, and then like another was beta emitter. Sometimes beta emitter, the beta emitter is put something. Then this abrasion part is this xenoblend part was recovered. This was actually we put by having epitope particle, this agglomerate particle. We absorb the beta emitter. Ytteria, chromium, dysprosium, samarium, lutetium, ytterbium, iridium. We accumulate this, absorb this what, and the agglomerated part can absorb this. Okay, then produce a beta emitter. Okay, then we joint of the knee joint, we put this neural particle. This this one. Then this we can see 72 hours. This neural particle is stay as this, and this produce beta emitter. So this beta emitter can be used as a for the physics treatment. And with this this one, I want to conclude this today my talk. The useful of there are neural parts in different areas are would mention here. One is the display and light harvesting, on-off switching, stability water up to 100 degrees centigrade, decrease of freezing temperature of the water down to 215 A, temperature sensor, security in, cancer therapy, imaging through the optic and regular light, attractive treatment, PGT beta ray. And so I acknowledge my associate director, Dr. Eketiagi, P. Hassan, my section head, BN Padi, my collaborator, Nina Azadov, Sujito Sakapati, their collaborator, and Dr. BP Singh, and Rasmi Singh, Rasmi Joshi, and Ramaswamy, and Sandeep, and Pooja Jain for their collaboration work with me. And this presentation is based on my work and other literature. And also my collaborators, I just mentioned some of the folks, Rajmohan Singh, and Doridajit, Srivastava, Rameswar, S.B. Roy, Sapor, and Lovindo, David, Lekhaba, Santa, Gangam, Neeraj, and Dhirend, and Professor Frank Vegan, Canada, Dr. Pasu, Thorat, Ford, Prasad, Lina Pradhan, Gautam, Piyobata, Premananda, Taru, Romeo, many collaborators. I am not mentioning many things. So about IT scholars from many colleges and university institute visited my lab since 2006. Some are occupying position in abroad. I thanks today I given to give a talk is because of their contribution. I thanks on my collaborator. Thank you for listening my talk.
Hello.
Yes, yeah, I finished now.
Very nice talk, very informative talk given, sir. We'll take some questions. One question is there in the chat box, sir. I will read it.
Okay.
Sai Supriya Lakshmi asked this question. Okay. Does magnetic nanoparticles kill normal cells surrounded by cancer cells? Are there any side effects associated with it?
Yeah, this is a good question. Yeah, the natural particle we see this is biocompatible, okay? So it doesn't affect in the normal sense, okay? Because this is biocompatible. Because iron epitope iron already contain our body, okay, and hemoglobin. So it doesn't affect anything, okay?
Okay, sir. If there will be any question from participant side, please unmute yourself. You can ask the question. Or you can raise the hand. Is there any? Okay, sir. Okay, I think there is no question. So I come to the next point, that is vote of thanks. Sir, you have given your valuable time for inauguration purpose as well as invited talk. We are very grateful to you. I am thankful from the side of Department of Physics, Yashwantrao Chavan College, our society. We are very thankful to you for your for giving you your valuable time and giving very nice lecture, which focused on the light emitting displays, light harvesting, sensor applications. Thank you very much, sir. Thank you.
Thank you.
So now we'll come to the invited talk number 2, and the resource person for this talk is Dr. Anurag Gautam, sir. Anurag Gautam, sir.
Yes, I'm audible. Yes, thank you.
Okay, thank you, sir. I welcome Dr. Anurag Gautam, sir, who is the Associate Professor from GCET Hyderabad
and he is going to deliver his talk on nanoparticle synthesis and their applications in magnetic resources, resonance imaging. So before starting the lecture, I request to my colleague, Dr. Madhukar Patil sir, to give his brief introduction. So I request to Dr. Madhukar Patil sir.
Okay, thank you, sir.
Welcome.
Good afternoon, all participants. I feel very glad to inform
that we have a distinguished resource person, Dr. Anurag Gautam, among us. Now, Dr. Anurag Gautam, he has been education from BSc Chemistry, Ranchi University, India, 1999, MSc in Physical Chemistry, RD University, India, and PhD in Nanomaterial Synthesis and Applications for IIT Kharagpur, 2008. And Sir's teaching experience, current position, Associate Professor at Hyderabad, and research experience also postdoctoral research fellow, Department of Chemistry, University of Victoria from Canada, September 2009. Now postdoctoral research fellow, School of Aerospace and Mechanical Engineering, University of Columbia, Norma. Doctoral research fellow, January 2003, August 2008. Awards and honor, teaching assistantship, IIT Kharagpur 2006, CSR SRF individual from CSR New Delhi 2007, postdoctoral fellowship from University of Oklahoma, USA 2008. Now, Sir's postdoctoral fellowship from University of Lund, Sweden 2009, and postdoctoral fellowship from University for Victoria, Canada 2009, and membership also Chemical Institute of Canada. Selected skills also teaching OP Jindal University, Raigarh, February 2018. Now there are referred journals for 18 and international journal also, and national and international journal also, and invited talk, various talk from Sir Uttam sir. Now 18 invited talks, so 16 invited talk from various places, and so I will brief introduction from Dr. Anurag Gautam sir and deliver the speech.
Thank you. Thank you. So, thank you to the Dr. K.M. Jadhav sir and Ashok Pandit sir for inviting me for this talk. So I will not take much time, and I will straightforward go on my topic, that is nanoparticle for high field magnetic resonance imaging applications. So let's move on this. So introduction. MRI actually is based on the principle of NMR, entirely based on the principle of NMR. So hydrogen proton relaxes, and that signal is processed to the contrast. So initially, when the name was proposed, initially when the committee sat to decide what will be the name of this imaging tool, many of them came with the NMR diagnosis tool. But later they decided to drop the name M, because later they decided to drop the name N, that is nuclear, was related to the radiation. So they thought like it's going to damage more than the curing the person. So then that N was dropped from that, and it came MR imaging. So N was dropped from there. Then it came as a MRI, and it was clinically introduced in 1981 first as an MRI diagnosis tool. So magnetic resonance imaging is a process where the contrast agent is used to improve the visible internal body structure. So as I said,
Excuse me, sir.
Yes.
Your screen is not visible, sir. Please share your screen.
Share. Okay. One moment.
Hello.
Yes, just one moment. I'm trying
Okay,
to.
okay.
Just a minute.
Okay, till that I would like to announce one thing, that after this session, Dr. Manas Srivastav sir's session is there, and then paper presentation from the researcher side is there. So the paper presenters, the list already displayed, send on their links. So they must be ready for the paper presentation. So Anurag Gautam sir.
Just one more minute.
Okay, so okay.
Is it visible now?
It
Yes,
is there,
sir.
sir, but PPT is not showing, sir.
PPT is not showing still.
Yes, yes, yes.
Yes, yes, okay, okay.
Visible, right?
Okay, yes,
It is
sir,
visible
visible.
now.
So, yes, yes. So, one moment. So, it is basically based on the technique of the relaxation rate of the hydrogen proton in the normal tissue or maybe the diseased tissue. So, for the normal relaxation rate of the tissue in the body is actually, if you go first, I will introduce, like there is a relaxation rate that we categorize T1 and T2, and so you can any contrast is T1 T2 is the relaxation mode. It's a longitudinal or transverse relaxation rate. So T2 is transverse relaxation rate of time, and T1 is the longitudinal relaxation rate of the time. So these two are for hydrogen proton in the body is 3600 milliseconds nearly. T1 is 3600 and T2 is slightly longer, 3800 milliseconds. So when we apply the contrast agent in the body, we try to shorten down the relaxation time by application of the contrast agent. So they relax faster, and that signal will process in the contrast more effectively through the computer and the amplifier. So as I said, there are two categories possible for the contrast agent. It could be T1 and T2, and T1 is a longitudinal, T2 is a transverse relaxation rate. Further, but when we are applying, we talk in terms of the relaxivity. So you have to convert the time to the relaxivity. That is usually done by applying the inversely, that is proportional to inverse of the time divided by concentration of the contrast agent applicable. So you can say R1 is proportional to 1 by T. It could be T1 or T2 divided by the concentration of the contrast agent. So you will get the relaxivity. So when we talk in the MRI term, we talk in terms of the relaxivity. So further, any material you have, that has both contrasts, T1 and T2. So that means they have both relaxivity R1 and R2, but one can be dominant over the other. So with respect to that, suppose R2 by R1 is higher, this is going to work as R2 contrast agent. Whereas if R1 by R1 over R2 is higher, it's going to work as R1 contrast agent. So mostly for this purpose, the paramagnetic nanoparticle have been getting used, even iron has been used, but the iron is only for T2 contrast agent. When we say T2 contrast, you have to imagine that it's a darkening signal. Compared to the normal tissue, the contrast of the undiseased tissue, compared to the normal tissue, the contrast of diseased tissue will be more darkened. It's blackish. But that can also be possible with the oxygen trap in that area. Suppose a person do not have cancer, but still possible that oxygen trap in that area can lead to the darkening contrast. So the diagnosis tool is taking to that direction where we can, and in the case of R1 is a whitening contrast. So R1, so the diagnosis is taking to that direction where we can see the both contrast, like R1, T1 and T2 both. So suppose oxygen molecule is misleading to darkening contrast, you will switch the mode, come to T1 contrast, and that is gone because oxygen is darkening contrast. So in the whitening contrast, there will no be whitening contrast by oxygen molecule. So you can clearly see with respect to the normal tissue, that area is more whitening contrast, white contrast having. So that could be a cancer pre-stage or maybe whatever the stage. So paramagnetic compounds, which they have large number of unpaired electrons, such as gadolinium 3+, Mn2+, iron 3+, are desirable for T1 contrast agent. So T1 is also decided by the relaxation time. They relax faster, and it's complex. I think you have to go behind the theory again. So then comes the gadolinium-based complexes have been widely, so till date, today, suppose one going for the MRI diagnosis, you will go, get the dose of gadolinium DOTA or any other gadolinium DTPA based complex. Eventually, they are going to inject the gadolinium 3 ion in your body in the form of the complex. But they have some drawback. You feel itching due to leaching of the gadolinium ion in the body. That's also reported. And the gadolinium complexes have few additional advantages, such as short circulation time. That means once you inject it, they may be out of body within 1 hour or maybe 2 hours. So that circulation time is short, and their efficiency, the contrast efficiency also decreases at high magnetic field. Suppose you have to increase the field, the contrast will decrease. So according to this NMR, as we increase the field, more you align, the more the splitting in alpha and beta. I will come that in later section. So let's say then FDA already want to use up gadolinium-based complexes in application of the MRI. So can nanoparticle be alternative, and how we can fabricate them? I think in morning lots of talk went on around how we are fabricating, but two approach are there. One top down, other is bottom up approach. They are widely categorized in two category only. So one is top down, other is bottom up. So the bulk material you can top down means disintegrate it to smaller particle by applying few methods such as ball milling, where you increase the ball in the mill with high in RPM, increasing RPM, you speed it up, and the ball will rotate faster, generate lots of kinetic energy, and then you put your sample. The transfer of energy from ball to the nanoparticle will disintegrate them to smaller size. This is one way, like getting used from the last pass. So that's getting you are disintegrating. I think all milling are based on this process. Then come lithographic, which is more electronic process, where the particular shape you cast of that material in the given shape, input the material, you get the lithographic technique. That could be one 3D printing, like already in the market. If you in some way, what we can do, put the statue with the computer and program it. So we can get my 3D picture throughout of the computer itself. Then come the pyrolysis in the same category. That is another top-down approach where you heat the material, get it disintegrated to the smaller particle. Then the next is thermolysis, where you apply both pressure and temperature to disintegrate the particle. Then when we come on the bottom-up approach, but some disadvantage of this top-down approach where you cannot control the size and the uniformity of the material. So it came to the bottom-up approach, which is well known in chemistry from long time. One could be the chemical synthesis. That is further categorized to the green synthesis. It's more attractive approach because of the pollution in the environment. People are trying to switch to the more special category of the chemical reduction is the green synthesis, where you do not apply the strong reducing agent, you use mild reducer, or could be the polyol method, where you use alcohols or polymers to reduce the nano ions to the nanoparticle. So in bottom-up approach, you use the atoms. First, you bring the ions that get reduced, then they converted to the atoms, and atom build up the clusters. That cluster 10 atoms quantum dot, and then the further size grows, that goes to the nanoparticle. If size is growing further more than 5-6 nanometer, 10 nanometer, we say it's a quantum dot. It's become nanoparticle. Below that, it's the quantum dot. So there's a kind of cluster. So synthesis, green synthesis, I already said you use mild reducing agent and polyol. Then comes the microemulsion. This is given by Schulman in 1959. Schulman emulsion method is also attractive, but the size of the nanoparticle will be vary over the range of 10 nanometer to could be the 60 nanometer. Because in this process, we use two solvent. One is polar, one is non-polar. So and we also use a surfactant. So at the interface of the polar and non-polar, the surfactant create different shape, that is called microemulsion. And that microemulsion has the variable sizes. So in that microemulsion, the nanoparticles are formed. But they have the variation in the size. Then other technique is the laser reflection, where you apply the laser that help in reduction and breaking the size of the nanoparticle. And the similar technique is the microwave irradiation, where we use the microwave rather than the laser light to disintegrate the particle and reduce it. Then so this is one of my old paper, that is 2011, where we use the polyol method to produce the silver nanoparticle. So it was very simple process, where you took 3 gram per dl of polyvinyl alcohol, heated over a beaker, temperature was 60 degrees centigrade. Then you disperse dropwise the silver nitrate solution with different content as you desired in the matrix. So for A, it is let's say it's a transparent. Number 1 is a transparent solution, and the composite is also PVA film, has no color. But as we started increasing the content to 0.2, 0.5, 1, 1.5, and the 5%, 8% of the Ag in PVA, the color of the composite change throughout the composite with the increasing concentration of the silver nanoparticle. Similar approach has been used in the next article that was published earlier. Actually, this was the gold, where we use the gold nanoparticle generated by the polyol reduction. Again, certain desired weight of the gold nanoparticle previously calculated, added to the polyvinyl solution, and the beaker was heated over the temperature 60 degree, and the excess of solvent were evaporated. So finally, at the later state, it was casted in the form of nanocomposite film, and the color of nanoparticle changed throughout. So as many speakers already said, so the size, because the nanoparticle size is changing, so the color is changing throughout the process, depending on the content of the ions added in the solution. So So color is also reported by earlier group. They got changed the size. We haven't worked with lots of size on the nanoparticle because still you need to change from one size to other. You have to work a lot. Stirrer rate and dielectric medium and pH of the solution. Every parameter is important. So further, that can be tuned with the literature given. So there they converted this spherical nanoparticle to the capsule or the rod shape, small rod shape. So with the change in aspect ratio, that is length to width, they tune the gold nanoparticle color throughout from the blue to light blue, purple, and then orange to red ribbon. Similarly, they use the core shell nanoparticle silica and the shell of the gold over that. The color were further tuned from the orange to the pale purple, you can say. And the last one is prepared. Actually, the cage. This was the prepared by the displacement reaction. The last one is a cage of silver nanoparticle, and finally, this was reacted with the gold nanoparticle. The silver ion solution were added with the gold ion solution. This is due to galvanic displacement. The gold cage were formed, and again the color were changed throughout the process. So you can see initially the gold was yellow color, gold ions were yellow, auric chloride is yellow, and as the time process, the color were changed from orange to purple, purple to blue, and then ultimately light purple. And so what is the advantage of this tunable color? This has great advantage, particularly during the FET transition, FET process, FET spectroscopy, all the biosensor, because if you see the next slide, that will, you will see the wavelength is tunable for this gold nanoparticle as evident from the color. This is tunable to the entire region for the gold nanoparticle. From 600 to 1100 nanometer, they are tunable. So it is going to the nearly both biological window, that is one from 600 to 1000 and other is from 1000 to 1400. So nearly going to the both biological window where that's desired for the application in human body or related to cell experiment. So that's tunability. And at this stage, so if you want to sense any fluorophore with the gold nanoparticle, gold is usually going to act as an acceptor. So any donor molecule is coming either 600, 700, 800, 900, or 1100 is going. The emission will be trapped by the gold nanoparticle and color will change. So we will see this strong sensor. That's why they have strong sensor and preferred over other nanoparticles. Similar approach, the core cell were also tuned from 700 to 1200 nanometer, and though the spectra is wider, but the tunability is still from 600 to 1200 nanometer. In the same case for the cubes also, shell cubes also, the tunability were wide from 1000 for 4000 to 1000 nanometer. But why they are growing? What is the reason of this growth? Why nanoparticle grows? That's also an important factor, and that goes with the So how we prepare this sodium dysprosium fluoride nanoparticle, because dysprosium or gadolinium, dysprosium is T2 contrast and gadolinium I said is the T1 contrast. Usually the MRI getting done nowadays is just T1 contrast. So how we prepare this one by taking 1 millimole of dysprosium chloride, 6 and oleic acid. After this in mixture was heated to 300 centigrade, and that will form mostly the oleates of any rare earth. All the rare earth nanoparticle can be prepared by this method. Sodium dysprosium, sodium gadolinium, or sodium lutetium, all can be prepared by the same procedure. So that will initially form dysprosium oleate, and if you further cool down the room temperature, adding 2.5 millimole of sodium hydroxide and ammonium fluoride, so that sodium is coming in the matrix, and fluoride is also coming. So it's a sodium dysprosium fluoride. Cool down, wash 3 times. That will be dispersed in hexane, chlorobenzene, all the organic solvent. They are dispersible because oleate on the surface. But the problem with this nanoparticle, the oleate is there, they will not be dispersed in water. So for making this procedure to the biological applicability, you have to modify the surface. Otherwise, they will be not going to disperse in water at all. They will form the clumps. So we further modify also the surface. But why the nanoparticle is growing? Suppose in the first, we are saying they are formed maybe half nanometer or something. Why they are going? There must be a size. There must be a size where they can grow. So that we can explain by the nucleation and growth process, why they are doing actually. So thermodynamically, the process of nucleation and growth, can we say that's two parts. One is surface energy, other is the bulk energy. So they will grow when on the expense of surface energy, right? So because the bulk energy is also, the volume energy is always negative. So we can say delta G equal to 4 pi r square, and sigma is the energy density per unit surface area, where 4 by 3 pi r cube is delta GV, that is gives free energy of the bulk, that is volume contribution. So if the size of nanoparticle radius is below 2 sigma by delta GV, they are going to, that's a critical size. Below this, they will not grow. They will re-resolve and go on the bigger nanoparticle surface. But if size is bigger than this one, you can see in the picture also critical radius, then they are going to grow. Otherwise, they will re-resolve, and that is also kind of Oswald ripening process. If they are below, they will re-resolve and go on the particle of the bigger surface. Similar process like putting a big small tree in the big plant, they will not grow because the energy is getting transferred to the other particle. It's a very similar process. And the critical gift free energy will be sigma pi, 16 pi sigma q divided by 3 dg delta GV square. So this is the gift free energy at that critical dimension of the nanoparticle. Then we came, as I said, the Oswald ripening. So that process will be the actually Oswald ripening. So this Oswald ripening, like as I said, if the critical dimension is below certain CR, that is 2 sigma by delta G, they will re-resolve and go on the bigger particle surface that has slightly bigger size. That's why we don't see the monodisperse. Monodisperse means the particle are 10 nanometer. There is no all monodisperse. But there is always variation if you calculate the size distribution during whole growth process. Suppose we quench at 1 nanometer, or maybe quench stop the reaction at 2 nanometer. So they will be dispersity plus minus maybe 0.2 nanometer. But during the particle growing up to 20 nanometer, this dispersity will be plus 1.2, 2, plus 2, minus 2 could be varying till 2 nanometer. So that's why, because you are extending the time, the growth will vary. This is due to the Oswald ripening also. So that's like smaller particle is getting re-resolved, growing on the bigger particle surface. So this is Oswald ripening process. Then we are, as I said, this is based on the principle of the NMR, where when we are saying the magnetic, we are bringing any magnetic particle, iron or maybe dysprosium, sodium disulfuride, or even if someone can make the dysprosium nanoparticle, those will be awesome for making the MRI application, because they'll be small and we have intact there. We are not diluting the dipole moment, magnetic moment also. When you add the sodium in the matrix, you dilute the magnetic moment also, but that will hard to make the dysprosium nanoparticle. So when we place the nanoparticle in the magnetic field, they are lying in the beta state or alpha state, depending on the energy. So it is out of 10 to the power 4 parts, only one is different. So mostly in the both population level, in alpha and beta, both are same. Only one is excess. Suppose we are taking 10 to the power 4 molecules, so only one is the difference, or rest are in the both state. So that's why the NMR is bit insensitive compared what is the desired. That's why the contrast agent is getting designed to improve the contrast, because this is not very sensitive technique. So actually, when we put the sample and the field, with the field, this splitting, we need the split, the energy splitting between alpha and beta state is more and more, as much as possible. That's why this is taking the MRI at the higher field. If we increase the field, splitting will be more in both states, and the energy change will be more, that will be processed in the signal. So That's why this technique is going to the higher magnetic field application. And this is a scanner that is getting used, how you go in the scanner and then signal getting processed through the computer. And yeah, so basically when you place the sample in the magnetic field, they align with the magnetic field. We haven't applied the pulse once, so all the particles will be aligned with the magnetic field direction M. When you apply the RF pulse, you bring Z component of the magnetic field to the XY direction. So you apply the pulse, RF pulse. This is the principle of MRI. You undergo the, they'll put you in instrument and apply the RF pulse. Then we'll switch off the RF pulse, and then they try to as the pulse is switched off, the molecules will try to realign their position as earlier. So as is going from X to Y, G direction. So gain in the magnetization is T1, and the loss where they're coming from Z axis to XY direction, that was T2 component. But the gain in the magnetization is T1 contrast, and the loss in magnetization is T2 contrast. Then this is the magnetic moment of the rare earth ion, that is also called lanthanide. We are calling them rare earth, but most of them are not rare earth anymore, because last decade there were lots of production of rare earth in China and North America. So most of them are not rare anymore. And because large chunks of rare earth found in China and America and Canada as well. So things are changing. So these lanthanide have the magnetic moment according to this. The highest magnetic moment is for, you can see from this one, predicted magnetic moment is highest for dysprosium and holmium, that is around 10.2 mu B for the both, and the gadolinium is approximately 8 mu B. So out of that, and so for the dysprosium, that is dy, and the holmium has been chosen as a T2 contrast agent, and gadolinium is a T1 contrast agent. So there is a model proposed by, like, because when this old model, how the complex work at the moment, when you this is the diagram where we are trying to show that the gadolinium complex in the DOTA is designed in such a way. So there is two types of water relaxation in the body. Suppose it's injected in your body in the blood pool. So water molecule some will be directly coordinated to gadolinium. Some will be the second coordination sphere. Could be the outer sphere. So the one in direct coordination, that will relax more. So design is needed in such a way where because they have to come in the contact, relax, and give the signals. But once they are not coming, they are far away from the center, the relaxation rate will be really slow and you will not get much signal. So idea is to bring more and more nanoparticle in the first or second coordination sphere, outers. But the technique we are using, the oleate base, that has a hurdle that when we use hydrophobic layer of oleate, they will not come in. And that's the hurdle at the moment with the nanoparticles designing, which mostly with all. So work is going on to bring more hydrophilic particle where the water can reach to the surface of the nanoparticle and enhance the relaxation rate. Then comes the design could be T1 and T2 both. Suppose you are keeping T1 contrast as a surface. Let's say you are keeping T1 contrast as a surface, gadolinium. In this model, we are keeping gadolinium at the surface. This is the idea to show that how we can get both the signal T1, T2 in one nanoparticle. Because suppose I am injecting two shot, it's a costly. As I said, why we need both contrast agent, why we are going for the clinical diagnosis is that oxygen can lead to T2 contrast and you cannot rely only on T1. So we need certain design where the T1 and T2 both can be generated by one injection of the nanoparticle. So if you switch the mode, so one design is telling that the T1 contrast when the gadolinium is on surface. For getting T2 contrast, we just need the pores where the gadolinium, through the gadolinium, the dysprosium can in. So water can go through the pores till the surface. So in this design, if the red is the gadolinium. It's not a porous though. If you design the porous structure where the water molecule can reach to dysprosium surface, then that molecule will act as T1, T2 contrast. As in the picture 2, where the red is the gadolinium, that is going to work as so red particles are dysprosium, and okay, the red is the gadolinium, and where they are doped in the porous structure of the dysprosium. So that design will be diagnosis for both T1, T2 diagnosis. And this can be further improved, this diagnosis. This can already explained by the previous speaker, like how we can do the T1, T2 together with the treatment also. Treatment means once you know the cancer site, you reach there, you got the signal, and you are sure that both T1, T2 contrast showed that it is a tumor, then you can radiate that tumor by applying 980 laser. You apply the 980 laser. So in that case, we have to dope the particle with thulium and erbium, and then we will excite. Once the particle is on the target, we will excite with 980 light from outside over the skin. That particle will excited, emit the light that will regenerate energy that will kill the tumor cell. So this is kind of multi-modal imaging where we are nanoparticle is getting on site and showing the tumor is getting probed by T1, T2 diagnosis. Then applying 980 laser, we are getting cured the tumor as well. So this is one injection process where, that's why you need the longer circulation time in the blood. Otherwise, gadolinium, if you are trying to do with the gadolinium complexes, they will get out of the body within no time, 1 hour. So that's why we need something that can travels in the body or circulate in the body for the longer time. So next is the size we prepared nanoparticle. These are energy diagram where they are the lengthenide diagram is given. So I'm not going on that much, but I'm coming to the size of nanoparticle prepare. So we prepare different size of nanoparticle. You can say this is sodium dysphosphate fluoride. A is 5 nanometer. They are nearly uniform, and B is also 10 nanometer, and C is also June picture, that is 10 nanometer. G is slightly bigger picture of 10 to 11, 20 nanometer. And the next one is which also trying to design the core cell nanoparticle. That is in the next diagram. So these are the core cell structure where we are saying gadolinium is in dysprosium is in core and gadolinium is on surface. That will be applicable for the T1, T2 contrast agent, because dysprosium will magnetize. Lots of ions are dysprosium in the core, because the core number of ions are more, so will generate magnetic moment. T2 contrast will come from there. Gadolinium is T1, that will come T1 from the surface. Then we also try to play with all models, like different type of particle with this picture. So they are nearly monodispersed, but still the dispersity is plus 1.2. If you go on the first picture, that is still not very, you can see the bar diagram that the variation in size from 18 nanometer to 23 nanometer. So plus minus, or maybe plus minus 1.9, the variation in the size. So here we try to see the relaxivity of different coating diamagnetic surface when the nanoparticle surface is already diamagnetic. So that is yttrium. When the nanoparticle surface was dysprosium in the both case, so that was diamagnetic in that case. In the case of dysprosium, it was paramagnetic. So this paper JPCs talk about how the nanoparticle when the surface is diamagnetic and when the surface is paramagnetic, how they enhance the relaxation rate of the water molecule, hydrogen ion in water molecules. So just because we, in the designing process, we need the tune to appropriate level where we can find the maximum relaxation of the water protons or the hydrogen molecules in the body. So this was just technique. Then we coat yttrium with dysprosium, and then Y with dysprosium. And the XRD, the next one is XRD, that I will not take much time here. And so XRD also proven that 5 nanoparticle were approximately 5.6, and rest all is in the next figure. So This is, most of you are familiar with this XRD process. So this where when the size is below 5 nanometer, all the lanthanide particle are mostly in the cubic phase by the process we are using. But if the size is growing further more than 5 nanometer, so they transform from the cubic to hexagonal. They dissolve actually, that all cubic particle will dissolve at certain stage. Maybe after this reaction goes usually for 1 hour, and they dissolve at half an hour, and then they regrow in hexagonal phase, and as you can see in the diagram next. So when the size is bigger than 12 nanometer, 10 nanometer, mostly by this method is most of the time you will get hexagonal phase. And if they are below size 5 nanometer or 6 nanometer, they are usually in the cubic phase. Then we measure the magnetic squid measurement data that source for the maximum magnetization for 20 nanometer particle. This is evident with the literature because the number of ion increasing when the particle size is 20 nanometer. So for one ion it is 10 μb. So when there is 10,000, 20,000 ions together, the size is increased. So magnetization also increased. So it is as the bigger particle, more is the magnetization. Sorry. So it is desired for T2 contrast. If we are making the dysprosium, they are T2 contrast, and they will generate T2 contrast. But because they are high magnetic, for the T2 we generate more contrast. We can grow even the bigger particle, 30 nanometer we can grow. That will generate even better contrast. But there will be certain size that is really optimum for MRI application. So in this study, we went with 20 nanometer particle and 10 and 5 to check the magnetization, and then how the result came in the MRI application. So as the surface was the oleate stabilized, so anyhow we need to transfer them to the water to make them water dispersible. The first thing you have to make them water dispersible. That's the hurdle at the moment this literature is facing actually for direct application, because the hydrophobic layer on the surface that is protecting nanoparticle, longer stability, lots of things are providing, but they are not really dispersible in water. So lots of glucose molecule or maybe glycol also coming on surface to generate them water dispersible. So we used PMO and PEG polymer to modify the surface, and then they were water dispersible, and the size distribution was between 10 to 15 nanometer. And then we measured the relaxivity, because when you have to measure the relaxivity, you need to disperse the particle in water, because that's environment the particle is going to get in the body. So before going for relaxivity measurement, you have to disperse them in water, check how much the relaxivity. So our observed relaxivity was, in this case, for the observed relaxivity. Oh, I missed one. Okay. So what we observed in the relaxivity, because this was mostly we are using dysprosium here, not gadolinium on the surface. So for the dysprosium, the relaxivity T1 dysprosium, I already said that dysprosium is only T2 contrast. It has very little T1 relaxation. So you will see that relaxivity is very less, 0.3, but T2, that is the R2 relaxivity, is very high. That is also increasing with the increasing magnetic field. That is at 3 Tesla, around 20 millimolar per second. But as the temperature went up, as the magnetic field went up to 9.4 Tesla, the relaxivity further increased to 1.120. That's very, very high compared to the contrast agent available at the moment. So we can compare that also. I think in the next slide there is comparison how they increase. So if the particle size were 21 nanometer, the relaxivity was around 101 per dysprosium ion per millimolar per second. And for the per particle, it was very high, 6,479 per millimolar per second per nanoparticle. So if we compare this with the size, you see the bigger particle, bigger the T2 contrast agent, and then when particle size decrease, the contrast per nanoparticle relaxivity decreases. That means they will generate less contrast also. So when we compare this one, the relaxivity with this is Faraday's this iron compound that is available for the MRI measurement. This is Rezovis. So compared to that, this sodium dispersion fluoride has very high relaxation rate. R2 by R1 is very high, that is 61. So then we measured also the toxicity with this nanoparticle. So our study, we basically study their behavior of the mouse after injection of the nanoparticle with respect to mouse body weight. And the behavior were fine. They were happy making nest and jumping all around the ground. We did not study the blood component, how the changes, but we went for the normal behavior of the mouse. They were fine by the process. So next we did the biodistribution study in this model also. So biodistribution studies. Biodistribution study suggests that most of the particle accumulated in liver and spleen, mostly the liver, they accumulate in liver, then spleen. And the parameter we are looking to, we looked for imaging the brain. That was very difficult due to the blood-brain barrier, where at the present condition, nanoparticle cannot cross the blood-brain barrier except the viruses. Viruses can cross the blood-brain barrier. So we saw very little, almost no nanoparticle reached to brain, but so composition is given there. So maybe very, very less. And then we went for the MR imaging of the brain, though the nanoparticle was less, but still the imaging were done. And little bit contrast can be seen in the next picture. So this is the T2 contrast of sodium dispersion fluoride. You see the diagram A, where the tumor showed the nothing, no before signal. But when we inject the nanoparticle, you can say this area become the right in the middle. That whitening become darkening, and it was good for 10 minutes, and the signal remaining persists for 2 hours. But after 24 hours, when the nanoparticle get renal clearance or out of the body or out of the tumor location, the contrast was gone. This was T2 contrast, so that got original contrast. And then in conclusion, we will say nanoparticle of different size were synthesized, and the size of nanoparticle were tuned from 5 to 10, 20 nanometer. The measured magnetization was highest for 20 nanometer particle because more number of ions were there to contribute in the to generate the magnetization. And the surface were modified with PMO PEG. And the costing, later they transfer to the water. The relaxivity measured data for sodium dispersion fluoride at 3 Tesla was twofold that of Hello.
Hello, Anurag sir.
We have to prepare more. So future work can be to develop better contrast agent and try out the dysprosium fluoride, gadolinium fluoride, where we are not diluting the magnetic moment much. So because when you add the sodium in the matrix, you actually dilute the magnetic moment. So that maybe the dysprosium fluoride, gadolinium fluoride can be better contrast agent compared to this sodium dysprosium fluoride, and also the facilitate the targeted specific delivery of the nanoparticle at tumor site by improving the surface coating. So if you modify further the surface coating, that might take to the tumor site more. So thanks to my collaborator that Van Wiegel in University of Victoria, Canada, and Slavik in the School of Institute of Biodiagnostics, Calgary, Canada, and Dr. Alton, University of Oklahoma, USA, and most faculty member at IIT Kharagpur. Thanks. Thank you. Done from my side.
Thank you. Thank you.
Sir, may I audible? Hello.
Hello.
May I audible, sir?
Yes, sir.
Okay. Thank you, Anurag Gautam, sir, for your kind lecture. You have focused very nicely on the applications of nanoparticle synthesis in MRI. There is one question, sir, one doubt
Yes.
from participant. I will read, sir.
Yes.
Hello.
Yes, yes.
How toxicity and biodistribution studies be performed?
So for that, you have to inject the tail vein injection of the nanoparticle, and then you have to you can go for the, let's give for, suppose I am doing biodistribution study, I also did the time dependent biodistribution study, but I have not shared yet. But this is 24 hours. We injected nanoparticle via tail vein that circulated, remains in the body for 24 hours. Then the mouse were killed and the all organ were taken out. Liver, spleen, brain, everything was taken out. Then we digested that to HNO3 solution. That was also digested in HNO3 solution. And the later ICP-MS were performed with these organs. So that solution were used to measure the ICP-MS. It was very costly actually to do that. We spent actually, for this experiment, we gave, University of Victoria gave 7 lakhs, particularly for the biodistribution study. So like you need ICP-MS, then processing and digestion, lots of labor also, like getting out the organ was done with the technician because I was not expert in this. So somebody, the technician at Victoria, University of Victoria, they get out the organs and hand over me. Then I store that in the freezer and waited for my turn to come for the ICP-MS. Then got dissolved in the HNO3 and digested for 2-3 days. And then the solution were used to do the ICP-MS. From there, we calculated like how much the organ were used and how much weight were of the sodium dysphosphate fluoride were there.
One more question is there, sir.
Yes.
What is the criteria for monodispersed nanoparticle synthesis?
When you are doing this technique, this will give you monodisperse. But this, the way I use, my paper is also there, Journal of Physical Chemistry C. If you use, you will get nearly 1% variation. That will be only 1% variation overall. Suppose a particle is 18, that could be overall particle will be 18 to 20 nanometer. But you have to be really alert about that because I saw that reaction hour is approximately 55 minutes. And particularly for sodium yttrium fluoride, suppose by chance your reaction went to 1 hour, they will be completely non-uniform. So when you are working with sodium yttrium fluoride, try to stop reaction at sharp 55 minutes, between 55-60 minutes. Then you need not to do the TM also. I will tell you that if you've done everything correctly, you will get monodisperse particle. But if you are doing something, I was very alert. I have lots of 1,000 TM on that. I have not published. But if you have to be really alert, you will get, without seeing, I will say that these are monodisperse particles. So while we're doing, make oleate solution that should be transparent and remove the traps from there like chlorides or moisture from solution. And then you Finally, add the sodium hydroxide, sodium chloride as is given in the process, and heat the sample to 300 centigrade, degree centigrade. That will lead to the mono-disperse particle with variation of 1%, like plus minus 1, that's it.
Very thankful to you. Now, I request my colleague, Dr. M.S. Patil, sir, to present the vote of thanks. Dr. M.S. Patil, sir.
I am thankful to our society, Yeshwant Rachon College. I am very thankful to your valuable guidance of nanoparticle synthesis and their application in magnetic resource imaging. So it was an academic feast to all of us to listen to these thoughts. I am very much thankful to you again and again. Thank you.
Thanks, welcome, welcome.
Thank you.
Thank you, sir. Now we'll go for further next lecture. That is invited talk number 3, and we have the resource person for this session is Dr. Manas Srivastava, sir. He is from Department of Mechanical Engineering, KBT COE, Nashik, and his topic for the lecture is controlled magnetic hyperthermia based nanoparticles for cancer therapy. So before that, I request my colleague Dr. Gopinath Dapke, sir, to give a brief introduction of our guest, Dr. Dapke, sir.
Thank you, sir. Good afternoon, sir, and good afternoon to all of colleagues who are attending this session. I will give a brief introduction of Dr. Manas Prakash Srivastava. So I feel very glad to inform you that all the delegates that we have distinguished resource person Dr. Manas Srivastava is an assistant professor at Department of Mechanical Engineering, Karmavir Bhaurao Thackeray College of Engineering, Nashik. He obtained a PhD from IIT Bhubaneswar, Varanasi in 2018 in nanoparticles. So title of the title of the thesis: Control magnetic hyperthermia using substitute nanoparticles. Sir.
हॅलो सर.
हॅलो.
नाही सर, 4च आहे आपले पहिल्या दिवशी, दुसऱ्या दिवशी 3च ठेवलेले आहे.
Dr. Srivastava has a working experience in Crompton Glues. I worked in Sangamner, IIT Bhubaneswar, Varanasi, Sandeep University, Nashik, and presently working at the KBTCOE College, Nashik, till today. Dr. Srivastava has a practical experience in wet chemical synthesis of substituted magnetic nanoparticles. The area of research interest is nanomagnetic materials, nanocrystalline structural, microstructural, and magnetic properties of substituted magnetite for hyperthermia applications. They have completed 7 projects on the industry areas and academic projects also. He has published more than 10 papers in reputed journals, and patent on the trivalent aluminum doped magnetic and method of preparation is registered. So this is the with this brief introduction, I conclude and hand over the proceeding to Dr. Sanap, sir. Thank you, sir.
Thank you, Dapke, sir. With this brief introduction, I request today's guest, Dr. Manas Srivastava, sir, to guide us. We are eager to listen you, sir. Hello.
Thank you very much, sir.
Okay, welcome, sir. Please start your lecture.
So I will start my lecture. That is brief introduction of controlled magnetic hyperthermia based nanoparticle for cancer therapy from the KBT Nashik. First of all, I will cover 3 contents. What are the different contexts are introduction, hyperthermia, internal heat generation from magnetic fluid, basic principle of internal heat generation, control magnetic hyperthermia, conclusions, and future aspects. So, in a control magnetic hyperthermia, what is a basic need? We have to control the heat generation from the magnetic fluid in the temperature range of therapeutic temperature 40 to 43 degrees Celsius. So this is our whole slides is based on control the temperature between 40 to 43 degrees Celsius. Next is, we talk about some introductions of magnetite. What is magnetite? We have to cover the structure and magnetic properties of magnetite. Magnetite has a cubic FCC phase, inverse spinel structure, which has cubic cross packing of 111 oxygens alloys. Having space group is FD3M. And we have magnetic property also. At room temperature, the bulk saturation meditation is 90 ampere meter square per kg at room temperature. We have a lattice parameter is 8.394 angstrom. From this, we have to draw the attention towards the unit cell of magnetite. How the unit cell of magnetite looks like. That is a tetrahedrite and octahedrites. So this is called tetrahedrite. This is the oxygen ion leadite which has 1.38 angstrom, and this is octahedrite. This is tetrahedrite and this is the octahedrite. A sites and B sites, because the vacant site, that is voids, are created due to the cubic cross packing of 111 oxygen ions. Next is there is 56 ions because Ab2O4 is the formula unit. 8 A site, 16 B site, and 32 oxygen ion. Total contains 8, 7, 56. 8 cross 7 equal to 56 ions it contains. Next, we know that in researchers there are different synthesis methods, but the synthesis method is useful for very cheap and low cost. It is very useful. So we have by using microwave reflexing method. These are very cheap. You can be in laboratory also. That is, there are different synthesis methods are co-precipitation method, hydrothermal reduction, salt gel, combustion method, and mechanical beading. But microwave reflexing method is very useful because it is very cheap and very low cost. As per the application point of view, we are used here for magnetic hyperthermia. Magnetites are used for magnetic recording, catalyst, target drug delivery, and magnetic resonance imaging. Previous talk, we have talked about magnetic resonance imaging, but here we will talk about magnetic hyperthermia. That is a controlled magnetic hyperthermia between temperature range of 40 to 43 degrees Celsius. First of all, we go some basics of magnetic hyperthermia for cancer therapy between 40 to 43 degrees Celsius. There are different types of losses: nil losses, Brownian relaxation, and hysteresis losses. For superparametric, that is single domain magnetic nanoparticle, they have nil dissociation, Brownian dissociation. For multi-domain, they have hysteresis losses. So, first of all, how to prepare the nanofluid? Nanofluid is a stable and homogeneous suspensions of the magnetic nanoparticle in carrier fluids. So far, we have to prepare this nanofluid by polymer like dextrin, cytogen, starch, PEG, PVA, and oleic acid. We know that from the researcher point of view, on earlier paper, we know that low Curie temperature near therapeutic range 40 to 43 degrees Celsius is used for magnetic hyperthermia. But it has very much drawbacks. Low specific magnetization and inferior biocompatibility for some material CU, NI, and Erasmus. So, in my PhD thesis, I have done a patent also for stabilization of temperature near therapeutic range 40 to 43 degrees Celsius. On this slide, I will talk about stabilization of temperature near therapeutic range 40 to 43 degrees Celsius. To achieve this temperature, we go in detail. First of all, we have to draw attention of there are two types of hypothermia: extracellular hypothermia and intracellular hypothermia. This paper has published in Journal of Radiation and Cancer Research 2019. Since here we are using NIR, ultrasound water bath, but it has a very lot of side effects, just like a thermoblisters, thermoablation, and sudden death to the patient. So it has a lot of side effect to cancer patient. So we are using intracellular hyperthermia. In intracellular hyperthermia, we have to control hyperthermia is required because magnetic nanoparticle, when we are using applied AC magnetic field, it generates lot of heat. The SR varies too much in our condition, but we are required a control magnetic hyperthermia near 40 to 43 degrees Celsius. So there is different type of losses. Nil dissociation, without the nil dissociation and Brownian motion, there is superparametric particles because their particle size is very much less than particle size, that is particle energy, very much less than thermal energy. So when particle energy is very much less than thermal energy, it goes to thermal energy barrier curve, that is flipping will start. Due to this flipping, it's just like 0 degree to 180 degree. The flipping will start, it causes relaxation. The relaxation time is 10 to the power minus 9 seconds. Please see here. The relaxation time is 10 to the power minus 9 to minus 13 seconds. So it can be seen by Morse bar spectroscopy. We are doubt that it can be seen by MH curve. Please see here, this can be seen only by Morse bar spectroscopy where their sextet and doublets are there. So here in this slide, we can be seeing the Morse bar spectroscopy also. Brownian motion. Brownian motion is simple. This is suspended particle in a solid state. Just like a sunlight is in a suspended particle falling to the surface, they are in a Brownian motion. So they are a solid state. Solid means suspended states. So how they are suspended state? They are corrosion, approaching. So this is a schematic view of the particle. Without this terminology, you cannot gain a knowledge of magnetic hyperthermia. So next topic is about superparametrium. The particle size is very much less than below the single domain particle size. That is when the corrosivity is 0. Definitely, strictly speaking, the corrosivity is 0 for superparametric particle. Here, these are a single domain. Here, these are the multi-domain. Multi-domain is for perimedium. Magnetite is perimedium, but we require single domain particle size. That is a superparametrium. So here, this curve, figure 5, this is energy versus angle of magnetic nanoparticles. Here the particle size is reduces. When the particle size is reduces, that is kV energy. Energy of particle size is reduced with k beta t. It crosses from 0 degree to 180 degree. Flipping will occur. So it shows that how it can easy axis one direction is there. So as per the mechanical point of view, I am from the mechanical branch. So we discussed the first law of thermodynamics and second law of thermodynamics. So everyone is known that first law, second law of thermodynamics, because as a mechanical point of view, This is an interdisciplinary branch. Hyperthermia is an interdisciplinary branch where we have to talk about first law, second law of thermodynamics. When you supply the heat to the magnetic nanoparticle plus tumor, magnetic nanoparticles are inserted inside the tumor. Due to that, the shrinkage of the tumor volume will occur. So, according to law of thermodynamics, there is a net heat generation is there. Net internal heat generation. This internal heat generation, in my content, I will explain you that net internal heat generation play an important role in a hyperthermia application because heat is directly proportional to your temperature difference. So it will play important role. Next slide. We try to explain in the in vitro and in vivo switch experiment. Here, this is a human body where the magnetic nanoparticles are inserted by the DC magnetic field. I am telling you AC is for heating purpose. DC is for giving the direction to the magnetic nanoparticle. That is, we are giving the direction to magnetic nanoparticle to the tumor tissues. When they are reaching the tumor tissue, then we are applying the AC magnetic field. So due to there is a heating will take place. But here we cannot use the bare magnetic nanoparticle. We are using functionalized magnetic nanofluids. But here for in vitro experiment, here I have used bare magnetic nanoparticle with different set of field and frequency combination. These are the nanoparticles which are heated due to the applied AC magnetic field. In the previous literature, they have used one set of field and frequency, but I will use different set of field frequency that we use to generate heat. So first of all, in researcher want to use very cheap and low cost. So every researcher want to use in experimental condition should be cheap and low cost and time only 15 minutes. Only 15 minutes we can generate the magnetic nanoparticle. First of all, we are using a concentration of 1 milligram per ml. Here, metal salt solution, they are precursor of different salt, monovalent ion that is lithium chloride, ZnCl2, AsCl3, different salt. We are with plus 2 and plus 3 state of Fe, that is FeCl3 and FeSO4.6H2O is dissolved in a ethylene glycol. Then we have added NH pellets. NH pellets are increases to increase the pH up to 12. It causes thermal agitation. That is causes mobility will be increased around pH equal to 12. Then we have done the microwave reflexing method for 15 minutes. We have some additional reflexer are used for 5 minutes on and 2 minutes off position. Then we have done decantation. Decantation is done to remove the impurities. We have done 12 to 14 times decantation. Then dried at 100 degrees Celsius for 10 hours. Strictly speaking, we are used bare magnetic nanoparticle. Characterization are XRD, TM, XPS, magnetic property measurement system, and magneton 1.5. Next is we go about tetravalent ion substituted magnetite nanoparticle. We will study this structure and magnetic properties and most part spectroscopy. First of all, the structure property of hafnium substituted FeCO4. Here you can see the bigger 311 has a shifted form lower angle to the lower angle side. So it goes to octahedral side first up to 0.2. Then further it goes to tetrahedral side and octahedral side both. That is hafnium ions goes to first octahedral side. then it goes to tetrahedral site and octahedral site both. So it has dawned the attention that hafnium is substituted in Fe3O4. So octahedral site and tetrahedral site, the comparative nuclidi also confirm our study. Please see this attention that Fe3O4, there is no vacant site, only substitution is there. So we talk about substitution of hafnium ion in Fe3O4. Next is TM analysis. This is for bare magnetic nanoparticle, accumulated magnetic nanoparticle for lower concentration to higher concentration. Side pattern shows that it has FCC phase and particle size is distribution between 20 to 22 nanometer. XPS spectroscopy is used for Fe contain, because Fe3O4 is there, magnetite is Fe3O4. They have +2 and +3 oxidation score. We can be confirmed by Fe, that is XPS spectroscopy, and this analysis confirms that iron contain +2 and +3 state, and hafnium contain +4 state at lower concentration and higher concentration. Next is, we draw the attention towards the magnetic measurement. Everybody know that we can achieve, please see the attention, we can achieve the 40 to 43 degrees Celsius by low Curie temperature, but it is not right. It can be attained by combination of feed and frequency, set of feed and frequency. So here we draw the attention towards magnetization versus temperature curve. Here at lower concentration to higher concentration, it has higher Curie temperature beyond 600 Kelvin. So you keep in mind that it cannot be used for hyperthermia application. But in our PhD thesis, I have published a paper of AC magnetic field which can be used for hyperthermia application in a controlled magnetic hyperthermia within the temperature 40 to 43 degrees Celsius. Since MS is, that is substitution magnetization, is quite decreasing because hafnium substitution in octahedral site up to 0.2, afterwards it goes to tetrahedral site and octahedral site both. And it has a higher saturation magnetization, which can be used for hyperthermia application also, because it has a saturation magnetization is about 50 ampere meters per kg. But at room temperature, bulk magnetite nanoparticle is 64 ampere meters per kg at room temperature. So this is a MOSFET spectroscopy in which we talk about sextet and doublets, where sextet A represents tetrahedral side of magnetite, sextet B represents octahedral side of magnetite, and sextet C represents spin relaxation. Since hyperfine field, there is a continuous decrease in sextet A, B, C. So it can be shown you that hafnium ions are substituted in Fe3O4. But in sextet A, there is tetrahedral site, and sextet B, octahedral site, hafnium ion substituted in tetrahedral octahedral site at higher concentration. In isomer shift, the doublets are present. Doublets are due to the paramagnetic component. And sextet C is the spin relaxation time. Next is, we talk about tetravalent zirconium sulfated magnetite nanoparticle. Here, I have also FCC phase. Magnetite is in FCC phase from zirconium sulfate magnetite nanoparticle. There is no impurity present. But this magnetic nanoparticle is polycrystalline in nature. So this XRT analysis is for polycrystalline material. TM analysis, it shows that particle size distribution is 20 to 24 nanometer, but this also has a FCC phase. Next is magnetic measurement. Magnetic measurement, here we have obtained the zigzag nature. zigzag nature is present due to the zirconium ion is distributed that is substituted in tetrahedral both. We draw some attention towards the magnetization versus temperature curve. We talk about control magnetic hyperthermia. Here the temperature is beyond 300 degrees Celsius. So this is not attained the Curie temperature. They have higher Curie temperature for all the sample from 0.01 to zero point 0.1 up to 1.0 I have done. That is at 50 millitesla. So all the sample has higher Curie temperature. So what is our kept in mind that for control magnetic hyperthermia? This will be explained in the next slide. Next, we will try to explain the bivalent ion secure meta particle. So one question is kept in your mind that why I am trying to explain tetravalent, trivalent, bivalent ion substrate meta nanoparticle. We draw the attention towards the researcher that by using that is sets of feed and frequency combination, we can use the temperature 40 to 43 degrees Celsius in therapeutic temperature range. So here Zn substituted Fe3O4 magnetic nanoparticle, we have FCC phase and Zn goes to first tetrahedral site, and after the MOSPA spectroscopy has confirmed us that in tetrahedral site they have contained Fe2 plus ions. Due to the content of the Fe2 plus ion, it goes to Zn is also goes to tetrahedral site and octahedral site, which can be confirmed by MOSPA spectroscopy. They have a comparative ionic radii at octahedral site and tetrahedral site. In TM analysis for the lower concentration for Zn substituted Fe3O4 and higher concentration for the bare magnetic nanoparticle. It draws the attention that it has FCC phase for set pattern and particle size is distribution between 15 to 18 nanometers. XPS spectra for Fe2 plus ions and Fe3 plus oxidation states are in Fe3O4 because Fe3O4 has plus 2 and plus 3 state and Zn in plus 2 state from the XPS spectroscopy, X-ray photoelectron spectroscopy. So we try to explain the MOSPA spectroscopy. We have sextet A represent tetrahedral site, sextet B represent octahedral site, sextet C represent spin relaxation. But here we have observed that there is two doublets are present, doublet 1 and doublet 2. Since it contains both ferrimagnetic and superparametric component in the system. So doublet 2 is observed at 0.8, x equal to 0.8 of Zn concentration. So it draws our attention that they have sextet A, sextet B has Fe2 plus ion in tetrahedral site and octahedral site both. So there is continuous decrease in the sextet A, sextet B, there is continuous decrease because Fe2 plus ion contained in tetrahedral site and octahedral site. So their magnetization is different for Zn separate Fe3O4. For magnetic measurement, up to they have very much high magnetization, up to 65 ampere meter square per kg. Up to the 0.2, there goes to tetrahedral site because afterwards it goes to both tetrahedral and octahedral site both. They have high saturation magnetization. Since M versus T curve, it draws attention that they have not attained the Curie temperature. They have high Curie temperature beyond 250 degrees Celsius. Now we talk about monovalent ion substituted magnetite nanoparticle. Since we have done all these studies, that is tetravalent, trivalent, bivalent, and next is monovalent ion substituted magnetite nanoparticle. Since in monovalent ion substituted magnetite nanoparticle, lithium is goes to octahedral site for lower concentration to higher concentration. And it contains FCC phase because we are here understanding that bigger peaks are occurring 311 or are FCC phase. So one draws attention that why we are not going to higher state up to beyond 0.3 because it has a double phase. We only want monophasic, not double phase. We do not want because it decreases your saturation meditation and also they have an impurity present in the system. So that we have not want in magnetic hyperthermia. So lattice parameter versus lithium concentration due to the lithium ion present in octahedral site, there is slight increase in the lattice parameter. And crystal size has opposite trend. There from 5 to 3 nanometer, crystal size is decreasing from 0.01 to 0.3. So they have a comparative indicator in octahedral site and tetrahedral site. TM analysis. TM analysis for this is bare magnetic nanoparticle. That is, draw attention that they have FCC phase for lower concentration at lithium substitution of 0.06 and lithium substitution of 0.3. It contains both FCC pattern from SAT pattern and it has a particle size distribution which can be analyzed from TM. It has a 20 to 25 nanometer. So magnetic measurement draw our attention that it has a higher saturation meditation. That is a lithium 0.06 is 55 ampere meter
Hello. हॅलो आलं ना आलं ना हॅलो बाकीच्यांचा
तुरंत बंद कर दी पता नहीं आवाज नहीं आ रहा है
हेलो
सॉरी
हेलो आई एम ऑडिबल टू ऑल एम आई ऑडिबल टू ऑल
क्या बंद हो गया तो मेरी वजह से बंद हो गया अरे बाप रे देखो बंद हो गया आवाज आ रहा है बंद हो गया तभी
सीडी
कोई क्वेश्चन पूछ रहा है
Hello. 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 Am I audible to all?
Yes, yes, sir, you are audible.
Okay, okay. Sir has some technical issues. So we will resume it. We will wait some moment.
ठीक है काही नाही झालं.
Sir, what is the next paper ID, sir?
Yes.
What is the next paper ID number, sir?
There will be this session will be open for discussion after
Okay.
finishing, sir. And then technical session will be start after this session.
Okay.
It is oral presentation.
Okay, okay.
Please wait, Subharav, sir.
नहीं, Dr. Datta Kakre.
Yes, yes, ma'am. I'm hearing you.
Muttaliki, what is going on?
Speaker is not available, ma'am.
There is some technical problem from the invited speaker side. Just we are waiting for.
Hello, Pandit sir. Hello.
Hello, हाँ बोला.
Shall we call on phone call to sir?
Okay, okay.
हम खोल के दें?
हेलो सर. हाँ, आपके साइड से ही कोई प्रॉब्लम है. हाँ, आपके साइड से प्रॉब्लम बोला, आपके तरफ से कुछ तो भी. हाँ हाँ, ऑन योर साइड देयर इज सम टेक्निकल प्रॉब्लम. ओके ओके. हेलो. हेलो. हेलो, मिस्टर काकड़े.
Yes, 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 sir. You are
हाँ,
audible.
hi. He is trying to solve his problem.
Okay, okay.
हाँ. Like 2 minutes, otherwise we will go for the oral presentation session.
Okay, 2 minutes we will wait for him.
Oh. हॅलो सर, त्यांच्याकडनं आता श्रीवास्तव सरांच्या याच्याकडनं प्रॉब्लेम काहीतरी टेक्निकल, 1-2 मिनिट थांबा म्हटले ते, नाही तर मग याला कन्क्लूड करू. हा, त्यांच्याशी बोललो मी फोनवर, त्यांच्या साईडनंच काहीतरी टेक्निक. हो 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 चालेल. येस येस येस. ओके ओके सर. हो हो हो, नाही एक्झामिनरशी बोललो मी तिघांशी पण जस्ट 5 मिनिटापूर्वी. हो, जॉईन झालेले आहेत ते. हो, यांना फक्त सिक्वेन्सनी सांगून. चालेल चालेल.
Sir, shall we proceed? Pandit sir.
हाँ, हेलो.
हाँ, shall we proceed?
हाँ, declare the oral presentation.
Okay.
हाँ, list हाँ.
Due to the some technical issues from resource person, we will start a technical session, that is oral session. So may I request to Dr. Pandit sir?
नहीं, first of all talk with Mr. Manas Srivastav sir. Take his permission and just go proceed. Yeah.
Sir, may I request to Manas sir for the permission of to start the technical session?
एक मिनिट, I am talking with him on telephone. Hello.
Yeah. Till I wait.
Okay. Yeah. Okay. And just we will announce the list of the oral presenter meanwhile time.
Okay.
Hello.
Yes sir.
Hi. He just going to connect again. Meanwhile, in meanwhile time, declare the list of oral presenters.
Okay.
Their sequence and give them instruction. Be ready for your presentation.
Okay.
Huh? Okay. Manas Srivastav sir is going to join again.
Okay sir. Okay. Now I am going to announce the list of oral presentation participants. The paper presentation is of maximum limit is 8 minutes and 2 minutes for doubt sessions. I will read the serial number of the oral presenter. The first will be of Dr. Nikila Nair. Second one will present M. Shashikala, Somaya S.S. Devan, Dr. Chetan Chanmal, Dr. Kranti Zakade, Supriya Patade, Aruna Sudapalli, Sheikh Irfan, Dipali Andhare, Govind Kulkarni, Dr. Ram Subaiya, and Mangesh Khedkar. These are the people who are going to present their paper orally. So the instructions are 8 minutes, maximum 8 minutes for the presentation and 2 minutes for the doubts. Okay. So
be ready for.
May yes, sir. There Manas sir just came now.
Join him.
Manas sir.
Yeah.
Okay. आणि चालू करते.
Yes, sir. I am audible.
Yes, yes,
sir.
yes.
My slide is visible, sir.
Yes, sir.
Yes, yes, yes.
So I am sorry for disturbance, sir.
Okay, sir. No doubt.
Okay,
Go,
it's
go
okay.
ahead, sir.
Okay, sir. So next, I will continue up from XPS spectroscopy. Here in XPS spectroscopy, we have draw the attention that Fe contain plus 2 and plus 3 salt. That is, we have oxidation state of plus 2 and plus 3 state from XPS spectroscopy analysis, and lithium contain plus 1 state. So, all of them, this is a quite interesting topic. This slide is quite interesting because we will talk about contour magnetic hyperthermia with tetravalent, trivalent, bivalent, and monovalent ion substituted magnetite nanoparticle. So how do we have to control the temperature between 40 to 43 degrees Celsius? So for magnetic hyperthermia of hafnium sulfate Fe3O4, for single field and frequency 23 millitesla and 173 kilohertz, they have stabilization of temperature between 36 to 49 degrees Celsius, and this shows the continuous rise in temperature. In your mind, one attention has drawn that the temperature has not reached 40 to 43 degrees Celsius, but with different set of feed and frequencies. That is, here arrow mark are represent the temperature are between 40 to 43 degrees Celsius with different feed and frequency, that is set of feed and frequency under AC magnetic field, that is 11 millitesla, 479 kilohertz, 23 millitesla, and 173 kilohertz, 9 millitesla, 636 kilohertz. We have a stabilization of temperature. Please remember, this is not a Curie temperature. I have published one journal in Journal of Alloys and Compound in hafnium sulfate Fe3O4. Please hear the SR value, specific absorption rate, is quite high. This is a 600 watt per gram. It can be used for hyperthermia application with small amount of concentration, that is 1 milligram per ml. It can be used for hyperthermia application. That is about 450 watts per gram is also there with different set of feed and frequencies under AC magnetic field. So I definitely say that for future application, it can be used for AC magnetic field regulated in vivo shifts. We will talk about zirconium sulfate Fe3O4. We are talking about tetravalent ion doped in Fe3O4. Here with different set of field and frequency combination at lower concentration. Below zero point 0.2, you can see here they have a temperature range of 40 to 43 degrees Celsius. This black dot is for 25 millitesla, 112 kilohertz. So different range of feed and frequencies, set of feed and frequency, we have attained temperature range 40 to 43 degrees Celsius. This paper is also published in RSC Advanced. Next is about aluminum substitute Fe3O4. This is granted patent and published patent at 2020. So aluminum sulfate Fe3O4 also shows stabilization of temperature between 40 to 43 degrees Celsius with different set of feed and frequency combinations. Here this has 33 millitesla and 260 kilohertz. This also attained stable temperature between 40 to 43 degrees Celsius. That temperature for lower concentration also attained stable temperature. So we draw the attention that at lower feed and frequency set of feed and higher set of feed. This is not depend on concentration. It purely depend on feed and frequency, set of feed and frequency under AC magnetic field. Also for Zn substituted FeCO4 for different set of feed. Zn is a bivalent ion. We have bivalent ion in FeCO4. We draw the attention that from tetravalent, trivalent, monovalent, bivalent, then we draw the attention that this is not depend on concentration and not substitution, that is bivalent substitution, not on tetravalent substitution. It purely depend on EC magnetic field with set of feed and frequency combination. Here at lower field, that is 7 millitesla and 170 kilohertz, it also attended 42 to 43 degrees Celsius. Please see here, 42 to 43 degrees Celsius. So it has also attained stable temperature at 17 millitesla and 170 kilohertz, also 11 millitesla and 478 kilohertz. This shows continuous rise in temperature. Next is monovalent ion substituted FeCO4. With different set of feed and frequencies, we have also attained stable temperature, that is 42 to 41 degrees Celsius. It can be also used for magnetic hyperthermia application point of view. So lithium substituted FeCO4 has attained stable temperature, but concentration is we have up to 0.3. After 0.3, it has a double phase. We have obtained only monophasic because monophasic is used for higher saturation magnetization. Next, we have drawn the attention towards the different set of feed and frequency data. Here, zirconium substituted FeCO4, hafnium substituted FeCO4, they are all biocompatibility. But here we draw the attention towards Zn substituted FeCO4. Zn from FDA approval. It can be intake of 15 milligram per day. So Zn substituted FeCO4 can be used for AC in vivo switch. I have done only in vitro trial for magnetic hyperthermia using magnetron 1.5. And aluminium substituted FeCO4, we have draw certain temperatures which are less than 42 degrees Celsius. But our temperature range should be 40 to 43 degrees Celsius. And CRT has shown that continuous rise in temperature. This all the temperature here, these all temperature are stable temperature. Next, we draw the conclusion. In conclusion, we have studied the basic principle of hyperthermia because as a researcher, we know what is hyperthermia and what are the different types of hyperthermia. So the next is major conclusion. The ferrofluid of single phase, that is monophasic, that is hafnium, zirconium, aluminium, Zn or lithium ion substituted FeCO4. We are not talk about vacancy. Please see here. We not talk about vacancy. We talk about substitution. That is hafnium is substituted in FeCO4. Zirconium is substituted in FeCO4. Aluminium is substituted in FeCO4. Zn as well as lithium are substituted in FeCO4. That has shown the stabilization of temperature between 40 to 43 degrees Celsius. Even they have higher Curie temperature. I draw the much attention towards Curie temperature and stable temperature. They are different terminology. They have high Curie temperature, but we have attained the stable temperature with selecting suitable set of frequency and amplitude of field. Despite the material have TC even higher than ambient temperature, even higher than 300 degrees Celsius, that kind of hyperthermia application. Only 42 degrees Celsius temperature can be used. Next is feature scope. The feature scope from this is an important parameter. If we go to the researcher directly and we in vitro and in vivo studies they be conducted to see whether this material have station temperature between in vivo and in vitro and in situ also. So the final result I will draw from this feature scope is that the material may be used for clinical trial also if we have obtained the positive result. So this is not the conclude of my slide. Please wait for 2 minutes. The major conclusion I will draw from here. Sir, interdisciplinary branch. Hyperthermia is an interdisciplinary branch. So every pupils from different background should come together, just as physics, chemistry, biology, mechanical, engineering background. They should come together in one platform to draw the hyperthermia in a controlled manner by using modeling and simulation. We are using heat transfer mechanism for modeling and simulation by conduction, radiation, perspiration in a skin surface. If I will draw your attention that you talking about that if 1 degree Celsius temperature can do the wonder in hyperthermia application. This is the figure 33. We show the attention towards the blood flow inside the normal cell and tumor. This is a micron size. This blood cell has a micron size. Their dimension is different. Scale-wise, dimension is different in micro mm size. So, if the dimension is different, this created lot of pressure. The pressure is proportional in heat generation is temperature and heat transfer rate. So, from third to one, there is lot of difference in pressure. So for both let's say rising temperature, it causes more amount of heat generation because change in rate of heat transfer is directly proportional to the temperature difference according to the Fourier law of heat conduction. So our practical importance, I will draw the attention towards that this is an interdisciplinary branch and mechanical always all the engineering background come together. That is skin surface also play important role in a AC magnetic field inverse application. So what is the interface temperature? Nobody has studied the interface temperature in molding and simulation of heat transfer mechanism. So thank you for have a nice meeting. Any queries and for sorry for disturbance.
Okay, sir. May I audible to you, Manas sir?
Yeah, you are audible.
Let me permit that your session is open for question and answer.
Please.
Okay, with your permission.
Please.
All the participants, I request to have some doubts or questions. You may ask by unmuting your mic.
In short.
Please ask.
In very short. There is a 2 question from audience in my chat box. Shall I ask?
Please ask.
The question is asking Venkata Nagendra Kumar, what is the criteria for monodispersed nanoparticle synthesis?
The criteria for monodispersed nanoparticle synthesis. They are synthesized by polyol method, but they are uniformly distributed. Here I have synthesized the bare magnetic nanoparticles, not the monodispersed magnetic nanoparticle.
Okay, there is another question from Sai Supriya Lakshmi, that is how toxicity and biodistribution studies be performed.
Yeah, this should be definitely performed in our next level. I have not performed the toxicity and biodistribution. For in vivo switch application, I will try about in vivo switch application that we perform in later stage.
Any other questions from participants? Okay, if not, then I will proceed for the next.
Okay.
That is, I request to ask the vote of thanks to Manas sir, to Dr. G.P. Dapke sir. Sir, proceed.
Yes, sir. We are thankful on behalf of Department of Physics, Yeshwantrao Chauhan College, Silo, for giving your valuable time and very informative talk on the control magnetic hyperthermia based nanoparticles for cancer therapy. So thank you, sir, for giving your valuable guidance to all.
Thank you very much, sir.
Okay, thank you, sir.
Thank you, sir.
Very nice lecture has been given by the Manas sir. Very informative, sir. Thank you. Thank you very much.
Thank you very much, sir.
Thank you, sir.
So we'll go for the next session, that is oral presentation. So I announce to ready all the participants. Okay. May I request to Dr. Pandit sir to introduce the examiner of this session.
Please
Dr. Ashok Pandit sir.
unmute my video.
Okay. CD सरांचा व्हिडिओ अनम्यूट करा. Okay, sir.
Hello. Good afternoon, everybody. Now, first of all, due to some delay, because our inaugural function gets delayed, and that's why all the invited talks also, and due to the discussions, our scheduled program for the oral presentation has been prolonged. For that, I regret to all the participants as well as for the invited speakers also. Now, for the oral presentation, we have selected 12 papers, and we have to select the best paper and have to award the 2 best paper presenters. For that, we have appointed an examiner panel. The examiner for this oral presentation are Honorable Dr. Rohila Nathuram sir. Second is Dr. Kunal Modi sir from Saurashtra University, Gujarat. And third one is Dr. Dhanay Kumar Kurmude from Aurangabad, Dr. Babasaheb Milim College, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. Now, in brief, first of all, I will give you the introduction of these 3 examiners. First of all, I would like to give the brief introduction of Dr. Rohila Nathuram sir. He had been working over a period of 38 years as a scientific officer in Baba Atomic Research Center. His research and development career span, he had the complete period in various projects he was associated, and he had set up a primary standard laboratory for determination of absolute activity of radionuclides. He has also developed low-level counting system for monitoring radioactive contamination on materials used in various applications. Further, he has worked on development of gas flow proportional counters. Now, his contribution in development of primary standard brought this laboratory recognition as a secondary standards laboratory by IAEA and WHO. In addition, he established several secondary standards such as ion chamber, scintillation gamma spectrometer, HPG multi-channel analyzer for photon emitting radionuclide, surface barrier detector for alpha and N window GM counter setup for beta particle. He has participated in several national, international inter-comparison program of activity measurements organized by SIR UK of UK, BIPA of France, and ETL of Japan. He has organized about 10 national inter-comparison of I-131 activity measurement in hospitals and radiotherapy centers. During his studies on standardization of radionuclides and
हॅलो आलाय. Hello, am I audible to participant?
Yes, sir. Yes, sir.
Okay. जाना पड़ता है. Due to some net connectivity, Pandit sir, we will wait for Pandit sir. Just 2 minutes. Hello, may I audible to Pandit sir? Hello, Dr. Pandit sir, may I audible to you?
Hello.
Hi, yes sir, you are audible.
Yeah. I have given the brief. त्यांना दाखवून चला म्हणा. I have given the brief introduction of Dr. Rohila Nathuram sir from Dr. Bhabha Atomic Research Center. He has published around 120 research papers in national and international journals. The second examiner for this today's oral presentation, and Dr. Kunal Modi, he has completed his UG and PG from Bhavnagar University and PhD from Saurashtra University, Rajkot. And the title of his research work was Study of Bulk and Microscopic Properties of Oxide Material Prepared by Ceramic Techniques. He has 20 years of teaching experience and 27 years of the research experience. He has published around 90 research papers in national and international journals and has completed total 12 major and minor research projects. Under his guidance, 8 students has completed their PhD and 8 are working under his guidance. He has also guided for MPhil and 25 students has completed their MPhil degree under his guidance and 1 student is working for MPhil degree under his guidance. He has received various awards in the field of research and in general activities. He has been nominated for Young Achiever Award by Department of Atomic Energy, Solid State Physics Symposium, Mumbai 2005. 2 times he has been awarded by Gujarat Science Congress. First time he has got the 3rd prize and for best paper presentation, and in 1998 and in 1994 he was awarded by 2nd prize by Gujarat Science Congress. He has have received felicitation shield for the contribution in the field of science and technology from Sri O.V. Seth Regional Community Science Center, Rajkot. And presently he is working as a professor in Saurashtra University, Rajkot, Gujarat. The third examiner is Dr. Dhanay Kumar Kurmudai. He is working as an associate professor in Milind College, Aurangabad, Maharashtra. He has completed his MSc from Marathwada University, Aurangabad in distinction in 1989 and has been awarded by PhD in 2013 from Dr. Babasaheb Ambedkar University, Aurangabad. And the topic for his PhD thesis was Mosbar and magnetic studies on pure and substituted ferrite compounds. He has a teaching experience of around 21 years. He first of all he was joined as a junior lecturer and has junior lecturer experience as in 5 years. He has been awarded by the Bharat Vikas Award for loyalty, diligence and outstanding performance in the field of magnetic materials on the occasion of National Seminar Intellectual Social Responsibility held on December 2018 at Bhubaneswar and organized by Institute of Self-Reliance, Bhubaneswar, Odisha. He also has received faculty with maximum publishing in CSI Publication Award by Computer Society of India during CSI convention held in January 2020 at Bhubaneswar, Odisha. He has worked as a resource person and has delivered many times invited talks in various conferences, particularly on nanomaterials bringing change, characterization of nanomaterial techniques and data preparation. He has chaired person in international conference. He has 15 research publications in national and international journals. He also has published books or journals. With this brief introduction, I request all the examiners to evaluate for the oral presentation and declare the two best paper presenter. So I request examiners be ready as per the format given to them, and the list of the oral presenter we have already declared. First of all, I request the first research fellow to be ready,
Okay, sir.
and you have to deliver. You have to deliver live presentation. If anybody has any technical problem, their video will be shown. Okay.
Thank you, sir. Thank you very
Okay,
much, sir.
Nomish.
Okay. Sir, with the permission of examiner, Dr. Nathuram sir, KB Modi sir, and Kurmude sir. Shall I proceed, sir? Kurmude sir.
Yes, sir. Yes, sir.
Okay,
Yes, sir.
okay. Okay. May I request to Dr. Nikila Nair to present your paper? You have 8 minutes maximum and 2 minutes for questions.
So can you see my presentation?
Yes, yes, ma'am. Yes.
Hello? Yeah.
Okay, okay,
Thank
yes.
you. Thank you. Thank you to the organizers for selecting my presentation. So since today's conference is on nanomaterials, so all are telling about the applications and everything, applications point of view, but I've taken a different topic. My topic is basically basically on the synthesis method. So today I'm going to say a facile method for synthesis of metal chalcogenide nanomaterials. We know that synthesis methods can be basically classified under physical and chemical method. The physical methods includes physical vacuum deposition method, pulse laser deposition method, molecular beam epitaxy. Chemical includes chemical vapor deposition method, Sol-Gel method, Cellar method, and CBD. These are some of the examples of the synthesis method. My focus is mainly on the chemical synthesis method. This is because what I found is in physical method, the instrumentations are expensive, the deposition conditions are harsh, and the reproducibility is limited. While in chemical case, it is more versatile, it's a feasible method, large-scale deposition is possible, plus you control the surface architecture. These are the two most common chemical methods which are used. One is chemical bar deposition, another is Cellar method. As you can see in chemical bar deposition, it is a process where the material which is to be coated on the substrate, a solution of that material is taken and a substrate is placed in that solution. Now, depending whether you want to do the process in a high temperature or low temperature, you can place it in a hot plate. Next is the Cellar method. As you can see in Cellar method, there are four beakers are taken. One, there will be a cationic precursor, another will be an anionic precursor. So in between that, there will be DI water. Now, what is the process is that we take a substrate, place it in a cationic precursor, where an adsorption process will take place. After that, as you can see in the presentation, there will be some extra precipitates will be coated on surface of the substrate. So in order to remove that, we use the rinsing process with the help of DI water. Again, we'll place this substrate in an anionic precursor where the reaction process will take place. Now, after you'll see that again, when you place it in an anionic precursor, the layer is formed, but some extra precipitates will be there. So in order to form a uniform deposition on the substrate, we'll do a rinsing process with the help of DI water. Now, this is the basic chemical bar deposition and Cellar method. Now, my work was in chemical bar deposition method. Why chemical deposition method? Because it's basically a low cost method. If the temperature required is low, I can deposit it over a larger area. I can also go for a mixed metal chalcogenide method with thin films and stoichiometry plate, as that films are reproducible. So the process was initially to form a cadmium hydroxide layer on the substrate and then try to convert it into different materials. So as I've shown in the presentation, I've taken glass substrate, placed it in a cadmium solution containing cadmium source and ammonia. Then after some optimized time, I found that some white precipitates are being generated on the surface of the substrate. Now, these white precipitates were of cadmium hydroxide. Now, why these are being generated? Whenever the ionic product is greater than the solubility product of cadmium hydroxide, such precipitates are obtained. Uh, here I've shown the image of the what we have got. You can see that on the substrate you'll get a uniform white deposition. Now, when another thing which we found that when we did the same, we got an ultra long nanowires were being generated on the surface. Further, I wanted to convert it into sulfide. So I took the same cadmium hydroxide, placed it in a sulfide source, and found that after some time, this white precipitates were getting converted into yellow color. Now, this yellow color is because of cadmium sulfide. As I've shown in the presentation, this is mainly happening because of the difference in the solubility product. As you can see, the solubility product of cadmium sulfide is -27 and that of cadmium hydroxide is -15. That means the more negative the solubility product, the more chances of that particular material being formed. So here you can see the image that I have taken the same cadmium hydroxide and the color has been changed. So this is visible through naked eye. So this is one of the simple methods to observe the experiment. Again, when we did the same, we found that the structure is not altered. The same long morphology is maintained. Now, since I had to change metal part, I had to convert it into silver sulfide. What I did, I took the same cadmium sulfide, placed it in a silver source. And again, after some optimum time, I found that the color of that particular CDS was getting converted into black color. Now, this was because of Ag2S. As you can see, the solubility product of Ag2S is -50 and the solubility product of cadmium sulfide is -27. And as I've said before, that because Ag2S is more negative, the possibility or the conversion process is more probable. I'll show the image of the here is the image we have got. You can see the color change taking place. Now, similarly, we have done this study for mercury also. So when we did the SEM, we found the morphology is not changing. So what is the advantage of this process is that you can keep the same parent morphology and change the material. Now, in order to study in order to study the effect of time for which the CDS material is placed in the sulfur source, I've changed the time. I've taken a random time where Ag2S was the CDS material was placed in a silver source for 1 minute, 1 hour, and 6 hours. These are some random times which I have taken, and you can see that as the time increases, the morphology, the nanowire structure remains the same, except for 6R where the nanowire morphology is there, but with some over depositions. Here's the graphical representation. You can see the cadmium sulfide was placed in AgNO3 for 1 minute, 1 hour, and 6 hours. And you can see that cadmium is getting replaced by the silver cations. And one more thing which we found was that at the intermediate time, there was a coarser heterostructure is being formed. So here, to validate that cadmium is being replaced by the silver cations, we have taken the XPS as it gives the elemental and chemical formation about the atoms present in the first few atomic layers. So you can see that as the time duration increases, the cadmium component is reducing while the silver component is increasing from 1 minute to 1 hour. Now, what is happening? When the nanowires were placed in the silver source, some precipitates are being generated on the surface of the nanowires, as it is visible from the TEM image. As I've told you, we have done this study for edges also. You can see a better image of the HRTEM. Here we have taken CDS nanowire and that you can see the edges precipitates. Now, what happens as the time duration increases, these HGS precipitates on the surface of the nanowires goes on increasing, and after some time, a complete sheet is being generated on the surface of the nanowire, which ultimately afterwards convert completely into the final material. So here is the image. Here's the image of the intermediate stage where the core shell heterostructures nanovirus being formed. Now, in order to validate that after some time, the material is completely getting converted into silver sulfide, we have taken the XRD. Here you can see that initially there were CDS peaks were available. As the time increased, that is from 1 minute, 1 hour to 6 hours, the peaks corresponding to CDS were reduced, while that of the Ag2S was increasing. Similarly, in case of mercury sulfide, we found that the CDA peaks corresponding to CDS were getting reduced, while that of the HGS were increasing. From this, we can conclude that the final material which we got were that of the silver sulfide and that of the HGS, mercury sulfide. Further, we have done the supercapacitor study of these. After the synthesizing such materials, we have done the supercapacitor study of these materials. These are being published in reputed journal of chemical physics. There is a journal of chemistry, and we have also published it in nanostructures and nano objects. I've done my PhD from Shishma National Institute of Technology under the guidance of Professor B.R. Sangal, whose talk will be tomorrow. Thank you. Sir, hello. Hello.
Yes,
You are audible. Yeah.
Sir, finish the.
On examiner
Thank
side,
you,
have you
madam,
asked?
for your nice. Yes,
Hello,
yes.
sir.
Am I audible to you, madam? Yes.
Yes, sir. Yes, sir. Yes, sir.
Thank you, madam, for your nice presentation. Just I would like to ask you one question.
Yes, sir.
Basically, you have prepared your sample with wet chemical method, and
Yes, sir.
the methods are having the method is having a number of advantages over the conventional methods. So,
Yes,
can
sir.
you justify one of the advantage why it is so? What are the reasons for the advantages of the chemical methods?
Sir, as I've told that mostly what happens, these nanovires, according to my literatures.
Yes. Justify the advantages. Why we are having, why chemical methods are advantageous over the conventional method? That basic question is that.
Methods are useful.
Why
That means
it
I
is
have shown that
advantageous?
even at low temperatures, such materials can be generated.
So, but why it is so? That I am asking.
So sorry, why such materials are being generated?
No. Chemical methods have advantages over the conventional method. So,
Yes,
what
sir.
are the reasons for the advantages by chemical methods? What is the basic difference that gives superiority in the results of the material produced?
So in chemical method, this is more controllable.
Yes. So
More
that's
controllable
why I'm
methods.
asking why it is controllable, how it is controllable. That I'm asking actually.
Okay, sir.
It is
So
reproducible. So
why?
why it is reproducible?
Yeah, so why controllable means you can see that as I've told you for hydrothermal methods. Hello, sir.
Yes. Yes. Yes, you can justify any one of the advantage. Okay.
Sir,
Please.
yeah, I'm mainly convert. Hello.
No, yes, I am listening. I am
Sir,
listening to you.
yeah, sir, I think the main advantages of temperature, sir. For me, the temperature is the main advantage, what I found. For physical methods, there were some temperature problems were there, while in case of chemical method, these temperatures can be controlled. So means at room temperature, not control. I can say that it's a room temperature method. That is the thing which I found the main drastic difference which is forming. Another is that the morphology is maintained. In some cases, this morphologies may or may not be maintained in physical cases. That is one other thing which I found.
Reactions took place. Basically,
Yes.
reactions took place at atomic and molecular level.
Yes, sir.
Basically,
Yes, sir.
that is the main reason
Main
behind all
reason.
the superiority.
Yes, sir. Yes,
Acha,
sir.
please mention any one of the future applications. You have mentioned one capacitor application. Are there any application, other applications of nanowires?
Yes, sir. Actually, there is solar cells is also there. I haven't worked on that, but one of my colleague is working on that. I know that.
Okay, thank you, madam.
Okay, any other question from audience? Okay, if not, with the permission of the examiner, I shall proceed further.
Thank you, sir. Thank
Yes, sir.
you.
Yes, sir.
Thank you. Yeah.
Yes, sir.
वाक तिकडे बसा ना. Thank you, Nikhila ma'am. Hello.
Hello. Thank you,
Thank you,
sir.
ma'am. Thank you very
Thank you.
much, ma'am.
Thank you.
Okay.
Thank you
Next
for
is
inviting.
M. Shasikala ma'am. Am I audible to Shasikala ma'am?
Yes, sir. Good evening, sir.
Hello.
Yes, sir. Yes, sir.
Okay,
Good
okay.
evening,
You may go now.
sir. Okay. Shall I start my presentation, sir?
Yes, madam.
अरे इकडे बसून स्क्रीन शेअर करणार आहे तुम्हाला.
Just a minute, sir. Just a minute. Sir, I can't share my presentation
Ye
because
presentation
other
wala.
participants are present. They're sharing, so that's why Zoom is not allowing me to share the screen. Sir, am I audible, sir?
Yes, madam.
Sir, someone is sharing the screen, so the Zoom did not allow me to share my screen.
Yeah. Mr. Kakade, please mute video and audio of all other participants.
करो का पूर्ण एक झालं आता बघ.
Hello, sir.
Hello, madam, you are audible now.
Yes, sir. Yes, sir. It's audible, sir.
Yeah.
I can't share my presentation, sir.
Screen is not get shared.
Yes, sir. Yes, sir.
Oh.
Zoom is not allowing me to share because other participant is sharing.
Yeah. Mr. Kakade.
Madam, please wait for a moment.
Yeah, okay, sir. Okay, fine. Okay, sir.
We'll Okay, ma'am. Now you may share
Okay,
now.
sir. Yeah, sir.
Okay.
Is it visible, sir?
Yes, yes.
Yeah,
Yeah,
yes,
yeah.
yes.
Shall I start it? Shall I start it, sir?
Yeah,
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 madam.
yeah.
Okay, sir. Okay. Good evening to one and all. This is M. Sasikala doing my MBA Apparel Management in University of Madras, Chennai, Tamil Nadu, India. So my presentation nanotechnology. So before we get into the detailed presentation, I just like to give some about how the nanotechnology is applied in the textile and apparel industry. So the application of nanotechnology is growing day by day in different fields, including textile industries. Its application can economically extend the properties and values of textile processing and products. This nano-engineered textiles cover from the protective clothing, smart textiles, hygiene textiles, bulletproof vest, functionally finished clothing like water repellent and wrinkle resistant clothing. Nanotechnology offers the developments of fiber for human, which have both conventional property like comfort and modern property like water repellent finishes. The future success of nanotechnology in textile applications lies durable, multifunctional textile systems without compromising the inherent textile properties, including the process ability and flexibility. So some of the sectors that nanotechnology widely used in the textiles is acted in the form of coating, technical textiles, clothing, medical textiles, hygienic textiles, sports textiles, geotextiles, agriculture, home textiles, leather textiles, and footwear textiles. So the next one is how the nanomaterials are applied in the textiles. So integration of nanotechnologies into textiles products is being realized in the form of treatments, coatings, nanoscale fibers, fiber material composites, and generally applied in the form of nano finished textiles, nano composite textiles, fibrous textiles, and nano enabled nanowoven. So some of the advances and development in nanotextiles, the important one things are the microencapsulation, applications of nano silver and electroconductive fibers in textile industry, and composite fibers with nano-sized clay particles, and the applications of titanium oxides in the textile industry in the form of using the nanotechnology. So, in today's performance market, microencapsulation in textile includes the application of fragrances, skin softness, insect repellent, and antimicrobial agents. Nano silver can be applied to be a range of other healthcare products such as dressing for burns, scars, skin donor, and resistant sites. Carbon nanofibers and carbon black nanoparticles are effective reinforcing materials for composite fibers. Both nanomaterials are also led to high chemical resistance and electrical conductivity when used in composite fibers, and composite fibers with nano-sized clay particles or flakes such as hydrated aluminosilicate exhibit the excellent flame retardance and blocking power with the inheritance to corrosive chemicals. A thin layer of titanium oxide nanoparticle is formed on the surface of the treated cotton fabric, which provides an excellent ultraviolet protection. And the nanostructure coating on textiles is a novel way to impart various functional properties such as gas barrier, antibacterial, abrasion resistance, ultraviolet resistance, flame retardant, and super hydrophobic properties. Nanomaterials such as layered silicate clays, carbon nanofiber, nanotubes, nanosilica, nano titanium oxide have been incorporated in the basic polymeric coating to enhance the performance of coated textiles to achieve these properties on fabrics. Conductive yarns and fibers are made by mixing pure metallic or natural fibers with these conductive materials. On the other hand, it's proven that the addition of carbon nanotubes to a common commercial polymer, polypropylene, leads to eliminate dicewell effect causes in swelling of polymers when passing through the capillary tube in electrospinning process. This improvement enhances the strength of the fibers against the high voltage between the capillary tube and the collector. Static electricity and metallic ions play a vital role also in case of finished textiles, and the potential uses of for electric spun fibers are in filtration, wound dressing, tissue engineering, nanocomposites, drug delivery devices, and sensors. Metallic ions and metallic compounds are also display a certain degree of sterilizing effect, and the resist-static is the first permanent anti-static treatment for the synthetic textile fibers. Not only does it repeal static, but the treatment
हाँ
also
सर
repeals the statically attractive substance such as a dog hair, lynch
हाँ
anti-dust.
ते
So the
इन्फॉर्मेटिव्ह आहे
titanium
फक्त
oxide and
ॲक्च्युली
zinc oxide nanoparticle.
कॉन्ट्रीब्युशन काही नाही आहे
Sorry, sir.
त्यामध्ये हो 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 इन्फॉर्मेटिव्ह सेशन आहे फक्त
Hello.
ठीक आहे
Titan. Sir, shall I
Kurgode sir.
continue it?
Yes, continue, madam.
Okay, so some of the titanium oxide and zinc oxide nanoparticles are electrically conductive materials and help dissipate these static charges in these fibers. So some of the applications of nanotechnology in textile industry, they are act as a water repellent, wrinkle resistance, optical displays. They are strength, and antimicrobial. So this is one of the example of the nanotechnology used to fight fabric. A normal fabric is acted as a water-resistant fabric after the finishing of the nanotechnology used by the nanotechnology. And some of the materials, nanomaterials widely used in this textile materials are carbon black nanoparticles, nanotubes, metal oxide nanotubes, and clay particles. They are act as an abrasion resistance. They are gives good chemical resistance to the fabrics. They feels lightweight and they are thermally conducting. They gives an UV protection to the fabrics, and they are electronically conductive and fire retardant, UV shielding, like that. So the future of the nanotechnology. The future trends of nanotechnology in textiles and fabrics will be in two ways. Firstly, the advancement of existing characters and their performance in textile materials. The second one is the development of smart and intelligent textile materials with an extraordinary functions. So some new functions with the textiles to be developed may include the wearable energy storage devices and solar cells that are applied in the textiles for the formation of the intelligent textiles that are especially used in the defense field, army, that is helpful for the army soldiers. And the second was the wound healing and healthcare systems that widely used in the medical textiles, sensing abilities and information transferring technology that are commonly used in the ICT sectors, and they are able to self-cleaning and self-repairing themselves. And finally, they are sophisticated and diverse protection, not only for the humans and also for the environment. So finally, the conclusion: textile industry has discovered the possibilities of nanotechnology in textile as the understanding, manipulation, and control of matter such that the physical, chemical, and biological properties of the materials can be engineered, synthesized, and altered to develop the next generation of the improved materials, devices, structures, and systems. Hence, the nanotechnology brings opportunities and challenges for textile industries, which can make. There is no doubt that in every area of the textile industry. So thank you to the organizer for giving me this opportunity. Thank you,
Thank
sir.
you, ma'am. Thank you, ma'am. Now the paper is open for questions. I request to participant to ask the question.
Hello.
Yes, sir. Yes, sir.
Hello.
Yes, sir. Yes, sir.
Sasikala ji, what is
Yes,
your
sir.
contribution in this presentation? What is your contribution?
Sir,
It is just information available in Google.
It's a non-technical paper, so it's basically a
Okay.
non-technical paper. I
Okay.
just
Okay.
try
Fine.
to. Okay.
Okay. Okay. Fine.
Okay, sir. Okay, sir.
Any other
Thank you.
questions from participant? Okay, if not,
should I ask one question?
Yeah.
Yes, sir.
Allow the
Yes,
examiners, and their video also should be open, unmute.
Sorry, sir. Sorry, sir.
Okay. Yes, thank you, madam, for your nice presentation.
Thank you, sir.
Your presentation was more informative. Actually, it was informative session. But I would like to ask one question to you.
Yes, sir.
Based on your study,
Yes,
do
sir.
you have any innovative idea that can be applied in textile industry? Whatever you have told is that is known to us. As Modi sir has told, it is on the Google actually. So
Yes,
you
sir.
have studied it in well manner, and so I am asking you that: do you have any innovative idea that can be applied in the textile industry, or that may be the that may serve as a problem to the researchers?
Yes, sir. Yes, sir. Sir,
Yes.
actually, nanotechnology played an important role in the textile industry for the formation, especially in the
No.
smart textiles and intelligent textiles. Actually, sir, shall I continue it?
Yes.
Yeah.
Uh,
Yes. Yes.
if we take the smart textiles, I like to give some.
Madam, madam, complete
Yes, sir.
Okay.
complete it very short period. We have very
Okay.
short
Okay.
period.
Okay, sir. Okay, sir.
I
Okay, sir.
Yes.
Okay,
Yes.
sir.
Thank you, madam. Thank you.
Okay.
Okay, thank you,
Okay,
ma'am.
sir. Thank you, sir.
Uh,
Thank you so much, sir. Thank you to the organizer to giving me this
okay.
opportunity. Very happy to see you. Thank you.
Now the next presentation is so, Somaya SS Devan. May I request to Somaya SS Devan to present your paper? Somaya SS Devan. Am I audible to Somaya SS Devan?
Audible, sir. Audible, sir.
Okay, okay. You may go now. Okay, you may start, ma'am.
Okay, sir. I can't share my PPT. Something
You,
error
you may
is
share it.
share screen. Then, are you seeing, sir?
No. Please share, ma'am, your screen.
I share. Put the share screen, sir.
There is a screen option.
Share screen.
Yeah. We enabled for multiple participants can share simultaneously. So you can share your screen.
Such a blessing. Okay, sir. 1 second. Are you seeing, sir?
Okay.
Sir. And the screen share has failed to start. Try again
We
later.
have enabled it, sir, ma'am.
Uh,
Yeah. Yes.
are you seeing? Are you seeing, sir?
You can share it your presentation, ma'am.
I already do that, sir. Share screen.
Okay. You are facing some problem.
Yes. I just
So
tried, sir. Screen sharing has failed to start. Please try again later. Oh,
okay.
I
Just hold on. You try it, ma'am. I will give you 30 seconds for you to share your video.
sharing that green button.
Pramode sir,
हाँ बोला ना.
am I audible
Hello.
to you?
हाँ.
Madam,
Okay.
madam is unable to share her screen.
हाँ yes that I know.
Shall I proceed? Shall I proceed to
It,
next one or?
You can take the decision. You can take decision.
Sir,
Share her video and then
anything else?
later on examiner will ask the question. Share her
Okay.
video. Okay.
Okay. Just a moment. Okay, here is a video. Okay. Shidi. एरर येत आहे रे. Hello.
Hello.
Hello. Am I audible to all?
Yes, sir.
Share.
Yes, sir. Yes, sir.
Play.
Give opportunity to next one. Later on, she will present her paper.
Just right. विचारना दिसते का सगळ्यांना. Hello.
Hello.
Hello. Is your PPT audible?
Hello. Sir, kindly share me video recorded.
No, nothing is seen.
Hello. Okay. Kurmode sir.
हाँ बोला ना.
So we will go to the next participant.
Yes, sir. Yes.
Later on, we will give the opportunity to Somaya ma'am. Okay.
Yes, sir. Yes, sir.
Okay. Now may
Announce
I?
the name.
Okay. May I request
Announce name.
May I request to Dr. Chetan Chanmal to present your paper?
Yes, sir.
Yeah.
I'm audible?
Yeah.
Yes, sir. Yes.
I'm sharing my screen.
Okay.
My screen is visible, sir?
Yes.
Okay. Okay, I am now shared my PPT presentation. Is it visible, sir?
Yes.
Yes, sir.
Okay. Shall I start?
Yes.
Shall I start, sir?
Yes, sir. Yes. You can continue.
Yeah. Good evening to all. Myself, Dr. Chetan Vishnu Chanmal, Assistant Professor, Department of Physics, DB of Dayanand College of Arts and Science, Solapur. I am presenting my work in the National Conference on Recent Advances in Material Sciences and Nanotechnology. This is organized by Yashwantrao Chavan College Arts, Commerce and Science, Silod. The topic of my presentation is pulse laser deposited polymer nanocomposites. In the outline of my presentation, I will introduce the PVDF polymer, then the useful properties of this PVDF polymer, experimental procedure.
Hello. Screen is not visible, sir.
1 minute.
Your screen
My
is not
presentation
visible.
is not visible?
No, not visible. Initially it was seen, now it is not visible. Now it is again visible.
Let us start.
Now visible, sir?
Yes.
The outline of my presentation is PVDF polymer, Useful properties of this PVDF polymer, experimental procedure, morphology studies, structural characterization, conductivity results, and its conclusion finally. PVDF, that is polyvinylidene fluoride, is a commercially very important polymer. The structure of monomer of this polymer is CH2CF2. When this monomer unit is repeated, we get the structure of polymer that is shown here in this presentation slide, CH2CF2. This polymer is commercially important because it exhibits piezoelectric pyroelectric properties, and it also exhibits different phases and morphologies, which are popularly known as alpha, beta, and gamma phases. Out of these three phases, beta phase actually shows the piezoelectric and pyroelectric properties. The piezoelectricity in this polymer generates because of the fact that the fluorine atoms and hydrogen atoms, they are aligned on the opposite sides of the carbon backbone, as shown here in this slide. And due to this, there is a net dipole moment, and because of that, this polymer has the piezoelectric property and pyroelectric property, which makes it a very commercially important polymer. There are also some other useful properties of this polymer, like it is chemically inert, it has a flexible, it has high mechanical and dielectric strength, it offers resistance to most of the chemicals and solvents, ultraviolet and nuclear radiation, it has resistance to weathering because of its transparency, and it has a low permeability to most of the gases and liquids. Now here I'm showing the experimental procedure. We have prepared the PVDF MWCNT nanocomposites by using the pulse laser deposition. And before this, actually bulk samples were prepared, and these samples were used as the for the pulse laser deposition. The energy of the laser source is around 0.5 to 1 joules per centimeter square, and the vacuum of the chamber is about 5 into 10 to the power minus 6 torr. And these samples were characterized for structural characterization by using XRD and morphology characterization by scanning electron microscopy. The images here are actually PLD deposited materials. On the left side, the black portion is actually the PVDF MWCNT nanocomposite sample. And on the top of that, we have taken the conducting electrode deposition, that is a silver in this case. And on the right image is this nanocomposite coating on a flexible substrate. So we can deposit on both hard substrate and the flexible substrate as well. Here are the day morphology of the pristine MWCNT and multi-walled carbon nanotubes. On the right side, we have the MWCNT as received. Here we can see the scale of the TAM is 0.1 micron. Therefore, this clearly shows that the CNTs are in the micron length size. And when these CNTs are PLD, that is a pulse laser deposited, that is shown on the left hand side, we see that the CNTs are broken. And therefore, I say that the length of the multi-walled carbon nanotubes decreases when they are PLD deposited. And therefore, this in turn changes the aspect ratio, that is the diameter to length ratio of the MWCNT. When this CNT is incorporated into polymer matrix and they are deposited BLD, we see the same morphology, SEM morphology. We can see that these MWCNTs are uniformly dispersed in the polymer matrix. Here, it is the important property that the MWCNT dispersion in the polymer matrix is very important. Otherwise, without any dispersion, we cannot achieve the desired properties of the nanocomposite. So by PLD process, we can achieve the uniform dispersion of the multi-walled carbon nanotubes. In structural characterization, XRD is used. There are 4 curves in the XRD curves. The red XRD curve is the PVDF bulk sample. That is a PVDF sample before PLD deposition. Here we can clearly see 3 peaks, 3 characteristics peak. When this sample is PLD, that is a pulse laser deposited, that is shown here in the black curve. We see that there are no peaks. That means that PVDF, when it is pulse laser deposited, it goes into amorphous phase. When this CNT is added to this composite, we see that one single peak appears, a single intense peak appears. This single intense peak indicates the presence of beta phase. That I earlier mentioned that the beta phase is a piezoelectric phase of the PVDF. Therefore, we say that pulse laser deposition not only enhances the crystallinity, but it also enhances the piezoelectric and ferroelectric phase, that is beta phase in the PVDF. The same thing is confirmed from the FTIR, where I can see that alpha phase peak intensity decreases and beta phase peak intensity increases. Therefore, XRD and FTIR together indicate the presence of the ferroelectric and piezoelectric beta phase in the PVDF. This is the conductivity measurement. From conductivity measurement, we see that the conductivity increases systematically with the increase in the CNT content. So in conclusion, PVDF MWCNT nanocomposites were fabricated by PLD process. MWCNT addition found to nucleate and enhance the piezoelectric beta phase in PVDF. The non-percolating network of MWCNT ensures the dielectric and conducting properties in the nanocomposite. This MWCNT nanocomposite can be a good material for the electric field FET devices, and this uniform dispersion of MWCNT in PVDF is also observed in the PLD process. Thank you, sir.
Thank you, sir. Thank you. May I request to participant to ask the question? Okay. If if not, I request to examiner to ask the question.
Hello, Chetan.
Yes, sir.
Yes. You have claimed for piezoelectric effect, and you have not taken any measurement for this characterization.
No, that is under study, sir. And this polymer has a well-known property of having
Okay.
piezoelectric and ferroelectric property.
But
They are
at present, you have not taken.
Yeah. I have taken the XRD, which just
Okay.
confirmed that it has a piezoelectric phase, that is
Oh,
beta phase.
okay, fine.
Okay.
Any other questions?
Okay, sir.
Okay, Kurmode sir.
Okay.
Shall I proceed next?
Yes, sir.
Okay. I request to Kranti Zakade, Dr. Kranti Zakade, to present your paper. Am I audible to you?
Yes, sir. Yes, sir.
I request to
screen.
I request to Dr. Kranti Zakade to present your paper.
Is my screen is visible, sir?
Yes.
Okay. Good evening, everyone. I'm Kranti Zakade, Assistant Professor in Applied Science Department, Jawaharlal Nehru Engineering College, Indian University, Aurangabad. First of all, I would like to congratulate organizer of this National E-Conference for arranging such an informative conference and providing us a platform to share our research work. In this pandemic situation, I thank Principal Dr. Pandit sir, Professor Dr. K.M. Raghav sir, Dr. Datta Kakre sir, Dr. Kurmude sir for giving the opportunity to present my work. Morphology of dendritic pattern, electrodeposits, and X-ray diffraction pattern of zinc acetate. This paper mainly focuses on morphology of dendritic electrodeposits and X-ray diffraction pattern of zinc acetate. The method to form zinc aggregate for this experiment was through a process that is called as electrodeposition. So what do you mean by electrodeposition? So electrodeposition is a process that uses a weak electric field and Brownian motion to form aggregate, and that results in the branching pattern. So here what we observe at higher cell operating voltage, the electrodes tend to have more amorphous structure. Morphology of dendritic electrodeposits. So here we have got two aggregates. In both the figures, that means figure A and figure B, that shows a branching pattern that takes place in accordance with the lattice structure. So the characterization of branching at 120 degrees. This is more prominent in the second figure. The figure A is the electrodeposit obtained at a cell operating voltage at 9 volt, and figure B shows a cell operating voltage at 3 volt. The experiment that has been done to study the nature of branching pattern at low voltages when the effect of directional motion of ions is relatively less and the tendency of moving ions is to stick at a suitable location along the crystal lattice. The main primary branches clearly shows that almost all the secondary branches obtained from the primary branches exhibit strictly similar angles. So this is more prominently visible in the second figure.
So here is the X-ray diffraction analysis of these two deposits or aggregates. So here the deposits obtained from zinc acetate solution as an electrolyte at two different cell operating voltages, that is 9 volt and 3 volt. So this is a X-ray diffraction spectrum for electrodeposited zinc acetate at 9 volt 1 molar solution. So XRD spectrum corresponding to 9 volt shows the counts at different angles all over the spectrum with a distinct hump at around 30 degrees. The characteristic peaks corresponding to 110, 200, 004 and 303 are also visible, however less prominent. So this shows amorphous structure. And in the second XRD spectrum, the electron deposit obtained at cell operating voltage 3 volt shows prominent, sharp and distinct peaks that corresponds to 110, 200, 004 and 303. These peaks are seen to be more prominent here because of the fact that the electron deposit here is having more crystalline nature as compared to the 9 volt electron deposit. So here is conclusion. Electron deposits obtained from zinc acetate solution as an electrolyte at two different cell operating voltages of 9 volt and 3 volt were analyzed by using X-ray diffraction pattern. It is seen that at lower cell operating voltage, the electron deposit possesses more crystalline structure as compared to that for cell operating voltage at 9 volt. It means at higher cell voltages, the electron deposits tend to have more amorphous structure. So the electron deposit shown in both this figure exhibits branching at an angle 2 pi by 3, 120 degrees, which is of zinc crystalline structure. It is simple hexagonal with lattice angles of pi by 2, pi by 2 and 2 pi by 3. Also it is seen that at lower cell operating voltage, the electron deposit possesses more crystalline structure as compared to that of cell operating voltage of 9 volt. And obviously at higher cell operating voltage, it possesses more amorphous nature. This work was supported by RUSA Center for Advanced Sensor Technology, Dr. Babasaheb Ambedkar, Marathwada University, Aurangabad. The authors of this work is thankful to Professor M.D. Shirsat sir, Director RUSA Center, for his help in revising this article and access to the X-ray diffractometer. Here are some references. Thank you. Thank you.
Thank you, ma'am. Your paper is open for questions from audience.
Yes, sir.
Any questions from audience? Modi sir, am I audible to you?
Yes, yes, sir.
Okay.
No, it's okay. It's okay, no problem.
No problem. Not any question. So, with the permission of examiner,
Can Madam please tell any one application of your work?
Sir, we have formed here two different aggregates by using cell operating voltage at 3 volt and 9 volt here. This is the very first time we had taken XRD pattern, and here we can conclude that whether the material is amorphous or crystalline. So at lower cell operating voltage, so the material we have got here, that is more crystalline in nature.
Okay.
any other question from participants? Okay, if not, thank you very much, ma'am.
Thank you. Thank you so much, sir. And thank you, entire team. Thank you.
Dr. Nathuram sir, if he has any question.
Nathuram sir.
Has he joined?
Am I audible to Nathuram sir?
Hello, sir. Have you joined, sir? Okay, okay, yeah, okay.
Okay, the next
Video, yeah. Audio is, are you audible? Yeah, okay. Okay, okay. Okay, okay, okay. Okay, sir. Thank you, sir.
Now, may I request to Somaya SS Devan. Am I audible to Somaya, ma'am? Hello. Hello, Somaya ma'am, am I audible to you? Hello.
Hello, yes sir, yes sir.
Okay. You can start.
Are you sir?
Yeah, you can start your presentation.
Are you seeing my screen, sir?
Yes.
Okay, sir. I tried over my mobile phone. That is the
Okay, no
delay.
problem.
Hello, sir.
Yes, your screen
Hello,
is
sir.
visible, ma'am. Yes.
Okay. Sir,
Okay.
I'm Soumya, Research Scholar, Department of Physics, University College, working on the guidance of Trivandrum. My work is effect of thin films prepared by Soldier. Introduction nanoparticles. The particles are the size of the order of 1 to 100 nanometer are called nanoparticles. The nanoparticles properties are entirely different from their bulk properties. There are major two different approaches for the synthesis of nanoparticles, top-down method and bottom-up method. In top-down method, we are starting from the bulk material and cut away the material to make the desired one. In bottom-up method, we are building the nanoparticles by assembling it by atom, molecule by molecule, or cluster by cluster. These are the schematic diagram of top-down and bottom-up strategy. There are several synthesis methods are available for the nanoparticles, physical method, chemical method, and biological method. In chemical method, I choose the sol-gel method for the synthesis of nanoparticles. Sol-gel method, it is a chemical technique that uses the chemical solution or colloidal particle solution is used as the sol to prepare an integrated network called gel. Metal alkoxide or metal chlorides are the typical precursors used to form the sol. Desired materials are mixed with the precursors to form the sol. Then a continuous network of gel is formed. The liquid solvent is removed from the gel by drying. Then thermal treatments are done to enhance their properties. My base material is tin oxide. It is an N-type semiconductor. It has high transparency and high electrical conductivity. Its band gap is around 3.8 electron volt. It has so many applications. It is used in window layers, lithium-ion batteries, used in dye sensing purposes, polishing in ceramic glazes, thin film transistors. It is a good photocatalyst and it is used as gas sensors. It is a high IR reflecting property, so it is used in heat reflecting windows, flat panel displays. It is a non-toxic substance, so it is used in cosmetics, etc. How to prepare the film? We take SnCl2 ethanol as the precursor solution, and it is mixed with using a magnetic stirrer for 1 hour at 50 degrees Celsius. Then it is keeps for 24 hours under room temperature for gelation. Then coated on the pre-cleaned glass plate using a spin coating unit at 1500 RPM for 30 seconds. Dried using a hot plate for 10 minutes to remove the volatile solvents at 100 degrees Celsius. Then the films are annealed in a muffle furnace for different temperatures, 300, 400, 500, 600, and 700 degrees Celsius for better crystallization. Then characterization techniques, XRD technique, field emission scanning electron microscopy, energy dispersive X-ray analysis, and UV visible spectroscopy are done for this study. Result and discussions. In XRD, we have to calculate lattice parameters, lattice distortion, grain size, cell volume, orientation of the crystal planes, etc. These are the XRD patterns of the as prepared. That is the films not annealed 0 degrees Celsius and annealed at 300 degrees Celsius, 400 degrees Celsius, 500 degrees Celsius, 600 and 700 degrees Celsius. The unannealed films, that is at 0 degrees Celsius, as prepared film shows the amorphous nature, and the temperature, annealing temperature increases, it starts to crystallize, and the crystalline nature increases from 300 to 400. But for 500, the crystallinity is reduced. Then again, for 600 and 700, its crystalline nature increases. That is, we understand that there is a recrystallization. First, it starts crystallizes with temperature. Then again, its crystallinity decreases. That is, there is a recrystallization happens at 500 degrees Celsius. All the planes are tetragonal rotile structure, and for 500 degrees Celsius there is a mixed phasing of orthogonal structure is also observed for this recrystallization effect, and a major orientation along 110 plane. Then these are the parameters calculated from the XRD and some analysis also. That's grain size, structural parameters, lattice distortion, and lattice volume, all are calculated. And the average crystalline size calculated is shown here. For amorphous, there is no crystalline size. For annealed 300, 6.19, annealed 500, 8.52, 400, 500, 12.59. That is, there is a recrystallization there. For recrystallization, their crystalline size are bigger, and these are observed in the SEM analysis also, that is shown in the next slide. There is an agglomeration of particles is seen. The average crystalline size calculated by Scherer method and SEM analysis are incomparable. Then ABC values are in good agreement with the theoretical values. Lattice distortion, lattice volume all are in good agreement. Stress calculated by the film for annealed at 500 degrees Celsius is the stress is minus 5.41. That is the minimum than unannealed and 300 degrees Celsius and 400 degrees Celsius. And for 600 degrees Celsius, there is 1.99. Stress is the in the reverse direction. For 700 degrees, it is minus 8.82. This is the SEM analysis figures. From that, first one is for 0 degrees Celsius, then 300, 400, 500, 600, and 700. In 500 degrees Celsius, there is an agglomeration of particles are seen there. This cluster of particles is formed due to the recrystallization effect at 500 degrees Celsius. And this is the EDAX analysis carried out at a film for annealed at 600 degrees Celsius. From this, we can conclude that SNO2 films, SNO2 is formed, tin and oxygen are obtained from the elementary values of tin and oxygen are obtained from this. This is the UV spectroscopy transition spectra. Transmittance, maximum transmittance is for as prepared films, that is, it shows around 98% transmittance, and the transmittance decreases when we start annealing. Then annealing temperature increases, it's the transmittance also increases. So at 700, it is the highest transmittance among the annealed films. This is absorption spectra corresponding to the transmittance spectra. And from this absorption spectra, we can calculate the band gap by using Tower plot. The optical band gap of the films were calculated by the equation alpha h nu is equal to A into h nu minus Eg the whole raised to n, where alpha is the absorption coefficient, h is the Planck's constant, nu transition frequency, A constant, Eg band gap corresponding to a particular transition, and n is the transition type, where n is equal to half for direct allowed, n is equal to 2 for indirect allowed, 3 by 2 for direct forbidden, and 3 for indirect forbidden. Here we have to calculate the direct allowed transition. This is the band gap calculated using the Tower plot for as prepared and annealed at different temperatures. This is the value for as prepared. It is 3.82 electron volt. It is around equal to the bulk value. And for annealing start, the band gap will decreases to 3.37. Then again it increases to 3.7. But again for 500 degrees Celsius, it will be decreases to 3.30. Then again it starts increasing. That's this decrease is also in support with the recrystallization effect at 500 degrees Celsius. Conclusions: nanoparticles are synthesized as thin films using sol-gel spin coating technique. All the film possess tetragonal structure. As prepared film shows the amorphous nature. The 500 degrees Celsius film shows the mixed phase of orthorhombic and tetragonal phase due to recrystallization effect. The lattice parameters are good agreement with the theoretical value. XRD result shows that the particle size varies from 6.19 to 14.69 nanometer. FSM analysis reveals that the particles are uniformly distributed in all the films except for 500 degrees Celsius due to recrystallization. There is a small agglomerations are seen in 500 degrees Celsius. The particle size varies from 6.09 nanometer to 14.86 nanometer. It is comparable with the XRD results. Then EDAX analysis reveals that the film contains tin and oxygen. It gives the idea about the weight percentage of tin and oxygen present in that film. As prepared film shows the highest transmittance, about 98%. Annealing first decreases the transmittance, and then annealing temperature increases, its transmittance also increases. The lowest transmittance is for 500 degrees Celsius, which is due to recrystallization effect. The prepared films the band gap is high for undoped films. Doping band gap and the values are ranging from 3.8 to 500 degrees Celsius due to recrystallization effect. These are the and thank you, sir.
Thank you, ma'am. The paper is open for questions and doubts.
Thank you, sir.
May I request to participants to ask the questions? Any participants? There is a question in my chat box. Is it possible to study the defect inside the crystal by using XRD technique? The question is being asked by M. Naresh Kumar.
We can calculate the defects by calculating the dislocation. Dislocation density delta is equal to 1 by d square, where d is the crystallite size calculated from the Scharer method. From this, the dislocation density gives the defects in the crystals. That's why we can calculate the dislocation from the XRD pattern.
Okay. Any questions? May I request to examiner, please?
Hello, Somaya.
Hello, sir. Good afternoon.
So how your work is different from those available in the literature?
This is my own work, sir. My own research work.
That is okay, but how it is? It's okay, but how it is different from, because number of papers are available on similar study, and how your work is different?
My work is different from the explanation of recrystallization in the 500 degrees Celsius.
Okay.
And it is supported by SEM analysis and use the spectra also.
Okay, fine.
Okay, sir. Okay.
Okay, thank you, ma'am. Thank you very much for having a nice
Thank you, sir.
Okay.
Thank you, sir. Thank you, judges. Thank you very much.
Next one is, may I request to Supriya Patade to present your paper? Am I audible to Supriya Patade?
She has a network problem. Then play her video.
Okay, sir. Okay. Okay, sir. Okay. CD. Sudhapalli madam.
Yes, sir. Yes, sir. Am I audible?
No, before you, there is a one participant who is going to present her paper.
Okay, sir.
So you will have to wait for 8 minutes.
Okay, sir. Okay, sir. No issues. Okay, sir.
Supriya Patade. Please wait for 2 seconds. She is having some problem of network problem to play her presentation. Now, may I request to Aruna Sudapalli ma'am?
Yes, sir. I'm audible. Sir, I'm audible.
Yes,
So I will
yes.
share my screen.
Okay. Yes, you can share, ma'am. We enabled you.
Yes, sir. Sir, is it visible, sir?
Yeah.
Is it visible? Shall I start?
Yes, your screen is visible, ma'am. You can start.
Okay, sir. Thank you, sir. Good day to one and all. My name is Aruna Siddapalli. I'm a research scholar of Department of Chemistry from Mumbai University. I'm working under the guidance of Dr. Naveen Chandra Shunti. First of all, I would like to thank the organizing committee of National Conference on Research Advances in Material Science and Nanotechnology for giving me an opportunity to present my research paper. And the title of my research paper is Wet Chemical Synthesis and Characterization of Tetragonal Barium Titanate Nanoparticles. Today's plan of talk will be, I will start with the introduction, then literature review, synthesis of tetragonal barium titanate nanoparticles, results and discussion, conclusion, references. There are many titanate-based materials are there like calcium titanate, strontium titanate, barium titanate. For our study, we have selected barium titanate because it's a perovskite type compound and it has got many interesting and stimulating properties and it has got various applications in material science and it has ferroelectric, pyroelectric and piezoelectric properties. Barium titanate is a ceramic material with a high dielectric constant and ferroelectric properties. It is one of the important semiconductor having unique physical and chemical properties and it is extensively investigated by the researchers due to its direct band gap of 3.2 electron volt and is used in transducer, thermistor, capacitors and electro-optical devices. As you can see the schematic representation of two different crystalline structure of barium titanate. A is ferroelectric, that is tetragonal phase. B is paraelectric, that is cubic phase. One more thing I would like to mention, why this tetragonal formation takes place. This is the reason behind it is structural deformation due to the displacement of the Ti atom from the octahedron center causes the ferroelectric stabilization of tetragonal barium titanate. There, although the tetragonal phase is stable at room temperature, many synthesis ends up with cubic structure. So they consequently the main task lies we have to deal the synthesis part so that we can develop a tetragonal barium titanate nanoparticle. We have done literature review. From literature review came to know that many researchers have used various methods for the synthesis part like hydrothermal synthesis, sol gel method, microemulsion, molten salt synthesis, non-aqueous route, biological synthetic technique. All these methods are simple, but the powders obtained are often of low purity with uncontrolled and uneven morphology. So this is one of the reasons why we have selected wet chemical technique so that we can yield high quality barium titanium nanocrystals, the distinct morphologies and control crystal phases. In the present work, we have anticipated to fabricate a standard method so that barium titanate with controllable size and morphology. In order to obtain high purity barium titanate with small and identical particle size, wet chemical technique is used. And at the same time, it is monitored by the solubility of reactants, temperature, and viscosity of the solvents plays a vital role in controlling the nucleation, crystal growth, and morphology of the desired material. As far as aim and novelty goes, barium titanate is the tetragonal morphology is obtained because of two reasons. That is, the temperature of annealing was very high, that is 1100 degrees Celsius, and the dominance of electrostatic forces over the surface of barium titanate nanoparticles plays important role for tetragonal shape. And the particle size was obtained was approximately 34 to 39 nanometer. This is the synthesis part of tetragonal barium titanate nanoparticles. We have prepared two solutions, solution A and solution B. In solution A, barium acetate weighing 6.3 gram dissolved in 30 ml of hot glacial acetic acid at 75 degrees Celsius, and further addition of 20 ml of N-butanol was added in that solution. In solution 2, titanium isopropoxide plus 10 ml N-butanol was taken. Now solution B is added to solution A in stoichiometric amount. Then the hydrolysis was performed by adding 2-3 ml of deionized water, and the solution is kept for under constant study with aging at the same time aging also. The final solution was stirred about 8 hours and transparent gel was obtained, which then dried in an oven at 90 degrees Celsius for next 8 hours. The zerogel was annealed at 900 degrees Celsius. After an intermediate grinding, the powder was sintered at 1100 degrees Celsius for 6 hours in air and cooled down to 600 degrees Celsius at cooling rate of 20 to 100 degrees Celsius per hour. Then as you can see, the white powder is obtained, that is barium titanium nanopowder, which is used for further characterization. These are the results and discussion. XRD. As you can see, the barium XRD diffraction of barium titanium nanoparticles, all the peaks were well indexed, especially the red peak, which you can see. That is there is a split between 45 degree, that is 2 theta 45.1 degree, which shows the HKL value 002, and 2 theta 45.7 degree that shows 200 the HKL values. So that the splitting at 45 degree is a predominant one to confirm the formation of tetragonal phase. And the diffraction angle and FWHM of barium titanium nanoparticles, we have got three strongest peaks and FWHM values are given and the spacing was calculated. Then from FTIR it is concluded that the peaks to study the functional group, that 3436 centimeter inverse shows OH group, then 2922 centimeter inverse shows carboxylic acid group, whereas 1628 is for C double bond C stretching, and especially the fingerprint region between 562 centimeter inverse to 1435 centimeter inverse and 855 centimeter inverse. It is characteristic peak for TIO vibration mode, and this is which confirms the tetragonal nanoparticles. barium titanium. Then we have sent the samples for morphological studies from FESM and HRTM analysis. We have got excellent morphology. As you can see, from FESM, the A1 shows tetragonal in shape, but under the magnification of 100 micrometer. But as the magnification moves away, that is from 200 to 300, 400 nanometer, there is a agglomerations there between the particles, but no impurities are found in that because of the technique, wet chemical technique. As you can see, the E and F, that it shows a brick-like formation, bricks-like structure is there. That it is therefore agglomeration is there, but no impurities is there. From HRTM, it is concluded that the particle size is between 34 to 39 nanometer, and from A it is tetragonal shape, and B also shows the tetragonal shape. Then it is from D shows the SED pattern of electron diffraction pattern. Then from EDAX, it is confirmed that we have got barium, titanium, and oxygen. As far as optical study goes, there is absorption edge of barium titanate was found to be 427 nanometer. The barium titanate band gap energy was calculated to be 3.25 electron volt. Then Raman spectra. From Raman active lattice vibration modes, that is, we have got two peaks, that is broad peak that 269 centimeter inverse, and asymmetric peak that 528 centimeter inverse, which is the characteristic of tetragonal barium titanate phase. Zeta potential. We have observed that zeta potential is between -21 to -21.9 millivolt. So it is evident that the samples have got good stability. Then TGA and DTA. The TGA exhibits approximately 2% weight loss due to H2O, and DTA shows the endothermic reaction that is at 351 degrees Celsius. Conclusions. Barium titanate nanoparticles exhibits inherent chemical reactivity and displayed good photocatalytic activity and chemical stability. And we have used synthesis technique, that is wet chemical technique, which showed tetragonal morphology, and the particle size ranges from approximately 34 to 39 nanometer was confirmed by HRTM and XRD pattern. And barium titanate nanoparticles shows because of the agglomeration, due to the temperature of annealing was very high, that is 700 degrees Celsius, and the dominance of electrostatic forces over the surface of barium titanate nanoparticles, and the effective annealing temperature shows maximum reduction in particle size, which has been proved from the obtained experimental data. Moreover, it was observed that annealing of barium titanate shows significant improvements in its optical, structural, and morphological properties. These are the references which I have used for my research paper. Thank you for listening patiently. Once again, I am thanking the organizing committee for giving me an opportunity to present my research paper. Thank you once again.
Thank you, ma'am.
Thank you, sir.
I request to all the participants to ask the question. Now the paper is open for the questions and doubts. Any questions? Any other? Now may I request to examiner to ask the question.
Hello, Aruna.
Yes, sir.
In EDEX pattern, you have not labeled 2 kilo electron volt peak and 5 kilo electron volt peak. It is for what? In EDEX pattern,
yes,
you
sir.
have not labeled peak at 2 kilo electron volt as well as 5 kilo electron volt.
No, sir. Actually, we have got from the lab itself the data and the graph also. That only I have pasted on.
No, that is correct, but you can have a ready-made chart also, and from that you can able to find out.
Okay, sir. Okay, sir.
Some impurities there or what?
No, correct? Sir. Impurities are not. Yes, sir.
Oh, okay, fine.
Okay, thank you, sir.
Thank you, sir.
Thank you, ma'am. Thank you. Now the next participant, may I request to Supriya Patade. I think she is having some network problem, so we will play her video presentation. Just a moment. With the permission of examiner, shall I play the video? Gurgude sir.
Yes, sir. Yes, sir. Yes, sir.
Okay. 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 His screen is visible? Hello?
Yes, sir.
Okay.
Yes, it is visible.
काकडे सर आवाज येत नाहीये.
Okay. Stop sharing. Just a moment, sir. मी माझ्या मोबाईलवरून करू का? Okay, just a moment. ओपन करतो व्हिडिओ. एकच मिनिटात करतो. कुठे आहे तू? माझा आवाज ओके. आवाज येतोय तुमचा. हॅलो गुरुमुडे सर.
हा, बोला ना.
ऑडिओ येतो का सांगा?
हो, तुमचा आवाज येतो, पण ते व्हिडिओचा नव्हता आवाज.
नाव
तुमचा
व्हिडिओ
येतो.
इज विजिबल ना?
नाही, आता नाहीये सध्या. सध्या बंद आहे.
नाही होते. कुठे आहे ते? जस्ट मोमेंट सर.
सध्या रे ಯಾ ಬಾರ ಹೊತ್ತೈತೆ ನಿಂಗೇನ್ ನಾಕೈತ್ವಾ ಏನವಲ್ ಬಾಜರ ಹಂಗ ಮಕ್ಕೋದ್ರ ಮುಜ್ಜೆ ಮಕ್ಕೋಬೇಡ ಬಾ
तू जेवण करून घे.
ಬಾ ಎಲ್ಲಾರು
हा, बोला ना.
ಅವ್ರೆ
Shall I proceed?
ಯಾರ್ದಾರ ಕರೆಸಿರ್ತೈತೆ.
हा, ठीक आहे ना.
There is a problem we are facing some, so I will move to the next.
Yes, sir.
Okay.
ಅದು ನಾವೇ ಪೂಜೆ
May I request to Sheikh Irfan to present your paper. Am I audible to Sheikh Irfan? Hello? Hello? Okay. I think he is facing some difficulty. So, next
Govind Kulkarni.
Yeah. I request to Govind Kulkarni to present your paper.
Yes, sir.
Okay.
Yeah. Am I audible, sir?
Yes.
Yes, sir.
Yes.
Okay, thank you, sir. I will share my screen now. Just is it okay?
Yeah.
Is it okay, sir?
Yes, sir.
Yes. A very warm hello. Am I audible, sir? No?
Yes, sir.
Okay. A very warm greetings to all. Very good evening. Honorable Kurmude sir, Modi sir. See, nowadays, there is a green movement in nanotechnology. So I am going to work, I am going to pursue my research work under the able guidance of Dr. K.M. Jadhav sir. He is a senior professor at Department of Physics, Dr. Babasaheb Ambedkar, Marathwada University, Aurangabad. And currently I am working at MES Abasaheb Garware College, Pune. The title of my paper is CLO, that is Cesium aromaticum, assisted green synthesis of nickel ferrite nanoparticles and their structural and magnetic properties. The outline of or content of my today's presentation is Introduction to Nanotechnology, Ferrites, Advantages of Green Synthesis, CLO, Experimental Work, Result and Discussion, and Conclusion. The introduction to the nanotechnologies, it is the branch of technology that deals with making structures that are less than 100 nanometers long. During last decade, in the world, there is the huge interest in nanotechnology because of their massive specific area and good effects. You will see that in classification of the nanomaterials, they are based on the different shapes or different dimensions, such as spheres, clusters, nanowires, nanofilms, plates, nanoparticles, etc. In case of ferrites, basically they are divided into two different families, hard ferrites and soft ferrites. And the classification depends upon the crystal structure as spinel ferrites, garnets, orthoferrites, and hexagonal ferrites. Nanoparticles are made up of variety of materials. Most are commonly used as spinel, as MFE2O4, where M represents cobalt, manganese, nickel, zinc, copper, etc. Nanoparticles from iron oxides family. Generally, these materials can be prepared by chemical methods, or chemical reduction methods. But nowadays, as I told you, there is a green movement. So that's why we have chosen the different matter particularly, because they have different problems. You might have, there may be the low yield, cost effectiveness is there, or toxicity is there. And therefore, to overcome all these types of difficulties, we have chosen this method. Green synthesis have attracted a great deal of interest due to its rapid, eco-friendly, inexpensive, high yielding, cost effective, and non-toxic synthesis, and also eliminates toxic substances to restore the environment. What is the necessity of green synthesis? Why is it? Unfortunately, many of the researchers, they have contain the uses of hazardous chemicals and or high energy requirements are there, and therefore to overcome such difficulties or disadvantages, as I told you that we have chosen the new green synthesis method to synthesize the nanoparticles, and to get we are getting the good yields also. So what is the goal of present work is there to develop the synthesis or some strategies like that, nanomaterials which are eco-friendly and simple and clean to reduce or eliminate the use or the generation of hazardous substances in the design, manufacture, and application of the chemical products. There are different advantages of the green synthesis. I told you, as it is low cost, excellent stability of the nanoparticle, non-toxic byproducts, large scale preparation is possible, safe reagent is there, eco-friendly. Now we can reduce some hazardous substances or the gases. It has high dispersity, high stability is there, or narrow size distribution. See, as I have chosen the clove, so you know that it has the medicinal importance from thousands of years, and therefore clove possessed, there are good medicinal properties. It is antiseptic, antibacterial also, antiviral is also there, and anti-cancer agents are also present in the clove. So that is my view actually. The materials which we are going to use in our daily life actually, I'm trying to use them to synthesize the nanoparticles, and therefore clo is one of the good material in that I found. Clo is a rich source of eugenol or eugenol acetate and gallic acid, which finds the number of applications not only particularly in pharmaceuticals, but in cosmetics also, in food also, in agriculture also. And therefore, in view of this, the present work focus on the synthesis of nickel ferrite by using the CLO as an good fuel, or you may say that the eco fuel, and therefore we have observed some good structural and magnetic properties after the synthesis of that. So this is the experimental work which we have done in the laboratory. Actually, we have obtained the claw extract or the powder. We have filtered that and we have made the solution and added it to the nickel, you can say that the nitrate and the ferric nitrate to get the nickel ferrite nanoparticles by using sol gel auto combustion method. We have observed good results. See, you will see that different characterizations we have done actually, and you will see that XRD also, the all values they are going to match with the JCVDS data is there actually, which confirms also the nanoparticle size. Similarly for IR spectra, so we are getting the values for that. Even though in hysteresis also, it will show the ferromagnetic nature, that is in MH plot. You will see the different parameters such as lattice parameter, ionic radii, tetrahedral sites, octahedral sites, volume of unit cell, X-ray density is there, porosity, bulk density, or crystalline size. We are getting some appropriate values. You will see in the table particularly. So we are again getting the good result for that. And even though for absorption band also, we are getting the values 544 and 392. So as we have observed to get the nickel ferrite clone nanoparticles. Even though regarding some magnetic properties are there, we'll see different parameters such as saturation magnetization, coercivity is there, remanence magnetization is there, remanence ratio is there, and magneton number also. You will see the values in the table again. We are getting appropriate results or the values particularly for this regarding, you can say that the magnetic properties. Coming to the conclusion, so nickel ferrite clone nanoparticles we have successfully synthesized by the combustion method via rapid, eco-friendly, inexpensive, and the green synthesis method. XRD analysis confirms the cubical spinel structure here, and we have got the nano size for that. It is near about 24 nanometers. What we say the crystalline size is there. FTIR also shows that the absorption band particularly, and which shows the stability of metal oxide nanoparticles. MH plot is there, confirms the ferromagnetic nature of the sample, and with the value which we have seen in the previous slide, it is 32.79 EMU per gram. And the use of claw extract in the green synthesis, I found that it is a promising and the eco-friendly alternative to prepare the nanoparticles, particularly nickel ferrite nanoparticles. So I'm going to conclude here. Thank you very much. With good green approach, we will say that. And I must say thank to my honorable guide, Dr. K.M. Zadhav sir. Even though the Pandit sir, the convener of this conference, my friend Dr. Kakade also, and his whole staff for giving me a chance and for selecting my paper here to present over here. And thank you very much for chairing my session, Dr. Modi sir and Dr. Kurmude sir. Thanks a lot. Thank you very much, sir.
Thank you, Mohit.
Thank you, sir. Thank you.
Now your paper is open for questions and doubts. So may I request participants to ask the question? Okay, if not, now may I request to examiners, so please ask question.
Hello, Kulkarni sir.
Yes, Modi sir, please. Yeah.
Okay, you have done very nice and novel work, but unless and until you have comparison between the various parameters with and without flow, it is very difficult to accept role of flow in green synthesis.
Yes, sir.
What is your reply?
Yeah, sir, I can comment on this. There are many of the researchers, they are going to work on, you can say that not only the claw, but yeah, what we call it in medicinal plant, jest mud is there, or maybe the hirda is there.
It's like okay, that. It's okay.
But we have got, yeah, I have to, yes, sir, I have to show there in the, in my work also. I have not, due to the short time, I have not mentioned here, sir. Due to
it will be more effective.
Yes, sir.
It will be more effective.
Accepted, sir. Accepted, sir.
Okay, perfect, perfect.
Yes.
May I
Thank you, sir.
request
Thank you very
Kurbode
much.
sir, Dr. Kurbode sir?
Yes, sir. Okay, sir. It is okay.
Okay.
Okay. Thanks a lot, sir. Thanks a lot.
Thank you, Govind Kulkarni sir. Okay. Now, am I audible to Sheikh Irfan sir? I request you to present your paper. Am I audible to Sheikh Irfan? Okay. Now, may I request to Dipali Andare to present your paper?
I am audible, sir.
Okay. Yeah.
Good evening, everyone. I am Andhari Dipali, research student doing research under the guidance of Dr. K.M. Jadhav sir, Senior Professor and ex-head, Department of Physics, Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. I am going to present research paper on the topic synthesis physiochemical magneto-optical properties of cobalt ferrite nanoparticles by chemical co-precipitation method. Outline of my presentation: introduction, aim of the present work, experimental, result and discussion, and finally conclusion. First of all, I would like to introduce what is meant by nanotechnology. Research and technology development at atomic, molecular and macromolecular level in the length scale 1 to 100 nanometer range. 1 nanometer is equal to 1 billionth of the meter. On the basis of number of dimensions, nanomaterials are classified into 4 types. First, 0 dimension, for example, where 1 dimension, for example, nanorods; 2 dimension, for example, thin films; 3 dimension, for example, bulk materials. Recent, now last decade, the role of ferrite nanoparticles have vastly increased in the biomedical application. Ferrites are the magnetic material consisting of iron Fe plus as their main component. Ferrites are the promising candidate due to their combined electrical and magnetic properties. On the basis of magnetization, ferrites are classified into 2 types. First, soft ferrite, for example, nickel ferrite, zinc ferrite. Secondly, hard ferrite, for example, barium ferrite, cobalt ferrite. On the basis of structure of ferrite, ferrites are classified into 3 types, that is hexagonal, garnet, and spinel. The structure and molecular formula and example of these 3 types shown in this table, shown in this slide. These are the some applications of ferrite: memory storage, coil, biomedical application, circulator, antenna, gas sensor, etc. Spinel ferrite. Spinel ferrite is described by the chemical formula MFE2O4. There, M stands for the divalent metal ion, that is Zn plus 2, CO plus 2, Ni2 plus, Ni2 plus, etc. They are also called as the cubic ferrite. On the basis of distribution of cations at tetrahedral and octahedral sites, spinel ferrites are classified into 3 types. First, normal spinel, for example, ZnFe2O4. Second, inverse spinel, for example, Fe3O4. Third, random spinel, for example, MgFe2O4. Aim of my present work is to synthesize cobalt ferrite nanoparticles by chemical co-precipitation method with a view to obtain nano-sized particles, investigate truly structural, chemical, optical, and magnetic properties of cobalt ferrite by X-ray refraction, Fourier transform infrared spectroscopy, UV visible spectroscopy, and vibrating sample magnetometer, that is VSM. Cobalt ferrite nanoparticles were successfully synthesized by chemical co-precipitation method, and the flow chart of synthesis technique shown in this slide. Prepared cobalt ferrite nanoparticles are characterized by different characterization techniques. The structural properties of prepared samples were characterized by XRD analysis. In this XRD pattern, there is no any impurity peak observed, which indicates the purity of sample, and the reflection plane having HKL value 220311, it 222, 400, etc., indicates the cubic spinel structure. The structural parameters such as lattice constant, unit cell, crystalline size, X-ray density, bulk density, porosity, ionic radii are calculated from the XRD pattern. Fourier transform in infrared spectroscopy, that is FTIR spectra of prepared sample was carried out in the range 400 to 2000 centimeter inverse at room temperature for the identification of chemical bands present in the sample and also ensures the formation of ferrite phase. There is two absorption bands observed in this FTIR spectra which indicates the intrinsic stretching vibration of metal and oxygen, which is the characteristic of spinel ferrite. The first band, mu1, is observed with the high wave number having value 559, which indicates the intrinsic stretching vibration of metal oxygen at tetrahedral site. And mu2 indicates the intrinsic stretching vibration of metal oxygen at octahedral site. The optical property of prepared sample were characterized by using UV visible spectroscopy. This is the absorption spectra. The higher absorbance observed at the wavelength 452 nanometers, and the energy band gap of the prepared sample, that is found to be 2.407 electron volt, calculated from the top plot, that is the intercept made by the intrapolating surface, linear surface of the curve on the x-axis. The magnetic property of prepared sample were investigated by using vibrating sample magnetometer, that is VSM, at room temperature with an applied magnetic field 30,000 oyster. The prepared sample, the magnetic parameters such as saturation magnetization, coercivity, resonance magnetization, resonance ratio, and magneton number are tabulated in this table. The saturation magnetization is found to be very high, that is 66.62 EMU per gram, and the coercivity of sample was found to be 413 oyster, which is the characteristic of feature of superparamagnetic nature of the magnetic nanoparticle. From the image plot of cobalt ferrite nanoparticle, it is clear that cobalt ferrite possesses superparamagnetic behavior at room temperature. That's why these particles can be used in the biomedical application. From the above result, I concluded following my conclusions. The sample of cobalt ferrite spinel phase in the nanosize form successfully prepared by the chemical co-precipitation method. The cobalt ferrite sample exhibits single phase cubic spinel structure as confirmed by XRD diffraction technique. FTIR spectra shows two absorption bands near the 400 cm inverse and 600 cm inverse, which characterizing the ferrite phase formation of the prepared sample. From the usage of spectroscopy, the energy band gap was calculated, which is found to be 2.407 electron volt. The high saturation magnetization and coercivity approaches to zero, which is the characteristic feature of superparamagnetic nature of the magnetic nanoparticle. The magnetic parameters like saturation magnetization, resonance magnetization, coercivity were calculated from image plots, and it all well matches with the reported data. The relatively small crystal size and saturation magnetization is high of the sample suggested that the synthesis technique is suitable for the preparing high quality magnetic nanoparticles, which is useful in the biomedical application. Thank you.
Thank you, ma'am. Hello, am I audible to? Hello.
Yes, sir.
Okay. I request to all the participants to ask the question. Now the paper is open for question and doubts. Okay, if not, may I request to examiner to ask the question, please. Modi sir.
Hello, Deepali.
Yes, sir.
In table 1, you have mentioned RA and RB. How you have calculated that RA and RB, and what is that?
These are the ionic radii at A side and B side.
Okay, then how you have calculated it?
With the help of formula.
Huh?
With the help of formula.
With formula.
Sorry, sir.
Okay, fine.
Okay.
Hello.
Question?
Hello.
Yes, sir.
Hello.
Yes, sir. You are audible to all.
Yeah. Can I ask one question?
Yeah.
Yeah. In Deepali, in your presentation, you have mentioned the crystallite size 12.20 nanometer.
Yes, sir.
Right? In XRD, you are mentioning the size, but how did you calculate that size?
Debye-Scherrer formula, sir. By using Debye-Scherrer.
Pardon?
By using Debye-Scherrer formula.
Debye-Scherrer
formula.
Debye-Scherrer formula. Okay. But you have not shown any calculation there.
Yes, sir. I shown only
You have shown the particle size only, but you have not shown the calculation, and the peak width is also not very sharp in your samples. If you go back to that particular X-ray pattern, the peak width should be very small, very thin. Hello?
Yes.
Can you show the X-ray pattern again? Hello?
1 minute.
Yeah. Yeah, this is the same. So in this, the peaks are of the same width. Can you explain how did you calculate this thing? Which peak you considered for this?
Sir, high intense peak I consider for the calculation of
311.
311.
311.
Yeah.
Okay. Okay. Thank you.
Thank you.
Hello. With the permission of examiner, sir, may I request to Supriya Patade? I think she is having some technical issues. So, with the permission of examiner, shall I play the video?
Yes, sir. Yes, sir.
Okay. Is my video is audible?
No.
Yet not joined.
No, I have joined as a client.
Yeah.
Okay. Okay. Screen share. Okay, I have. Okay. Just a moment, sir. Okay. Okay.
This is Supriya Patade, pursuing PhD under the guidance of Dr. K.
Is audio audible? Kurmudi sir.
Dr. Baba Sahib
Yes, sir.
University, Aurangabad. Today I am going to
The
present
volume
a
is
research
quite
paper
low.
from the conference Recent Advances
You
in
increase the
Material
volume.
Science and Technology.
Increase volume.
Sir, I have increased.
Arts, Commerce and Science
It is
Technology.
quite low.
My presentation entitled the Magnetic Fluid Hyperthermia Study of Water Dispersible Zinc Substituted Package Ferrite Ferrofluids. Content. Introduction includes ferrites and its properties, ferrofluids and its applications, cancer and its treatment, hyperthermia, synthesis by magnetic nanoparticles and ferrofluids, characterizations, result and discussion, and conclusion. Introduction. Ferrite nanoparticles are meteorites, similar structure of angular formula Fe2O4, where A and P are metallic cation positioned at two different crystallographic sites. Tetrahedral A site has a primary B site. Classification of ferrite we introduced on the basis of crystal structure and magnetic field. According to crystal structure, it is classified in four types, which is spinel, hexagonal, garnet, and articular. Spinel ferrite are also classified in three types: normal inverse and high electrical resistance.
Hello? आता है
Fluorophores are engineered by systems. Magnetic nanoparticles, the average size is 100 nanometer, in traditional heat transfer fluids such as powder, oil, and liquid fiber. There is ionization of nanofluids in hyperthermia. In the present study, the emphasis on this hyperthermia application towards cancer treatment. In cancer disease, some antibiotics used to divide without stopping on cells into cell amplifications. By the cell within no abnormal or damaged cell, survive will be shut down and cells can divide within stop and move from pure or tumors. These are types of cancer and etiologies of cancer. They are how the organs or tissues of the cancer forms.
थोड़ा है
हो चालेल हो सर हो हो सकाळच्या याच्यातच घेऊन टाकू मॉर्निंग येत चालेल Hello, Mr. Kakade.
Yes, sir. Yes, sir.
The volume is very low. It is not audible.
Okay.
Then ask her to present her paper tomorrow in the morning.
Okay, okay.
Yeah. Send her a mail.
Okay,
and
I will mail.
Announce the name of the next paper presenter.
Okay, okay, sir. Okay. Okay, with the permission of.
Ask the examiner.
Okay, okay. Sir, will you permit me to the next oral presentation?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay. Okay. May I request to Dr. Ram Subaya to present your paper?
Yes, sir. I'm available online, sir. Yeah.
Okay, okay, okay. Okay, you may start your presentation.
Yeah, yes, sir. Sir, is my screen visible, sir?
Yes, yes.
Yeah.
Yes, visible.
Yeah, yes, sir. Good evening, one and all present here. Myself, Dr. Ram Subaya, working as Associate Professor in the Department of Mechanical Engineering, Gokaraju Rangaraju Institute of Engineering Technology, Hyderabad. The paper that I'm going to present is on Assessment and Microstructure Analysis on AISI 630 grade martensitic stainless steel by hardening and tempering process. Before going to the presentation, I would like to thank the organizing committee for giving me an opportunity to present my paper to all of you. And these are all the topics for discussion I would like to have. Objective of the paper, materials and method, experimental work done, results and discussion, conclusion and references.
Awesome.
Actually, the paper is on 630 martensitic stainless steel material. We are thinking that stainless steel material is applicable only for making kitchen utensils. We might have seen most of the stainless steel material only in our house, in the kitchen application utensils actually. But this stainless steel material can also be used for higher load and higher temperature applications. Why mainly I have chosen stainless steel material? Because stainless steel is very cheaply available in the market at very low cost. There are a number of merits available for stainless steel and demerits are also available. The merits of stainless steel will be in such a way that it doesn't get corroded actually very easily because of the alloying elements present on stainless steel like nickel and chromium. So it doesn't get corroded. On the other side, if we see the drawback of stainless steel material, the drawback will be it is having poor hardness and poor wear resistance and poor strength. So keeping these 3 points in the mindset, there are a number of heat treatment operations where this strength, hardness, and wear resistance can be compromised along with corrosion. Thereby, the material doesn't get corroded, so that we can make use of the stainless steel material for higher application and higher load applications. So whenever we manufacture any product, it has to survive against variable load and variable speed at any environmental condition. So now I have taken the stainless steel material and I have undergone some heat treatment operation. The heat treatment operation that I have carried out is on hardening and tempering process. So AISI 630 material is one kind of stainless steel which comes under martensitic phase actually. Martensitic stainless steel material generally they will be having the property like they will be having good hardness, good brittleness, and good strength will be there. But whenever we manufacture a product, the material we don't want the metal to be we don't want the component to have more brittleness and more hardness because it leads to fracture on the application of load. So what I have planned with this AISI 630 material, we have to compromise the hardness and brittleness along with the strength. So we have to balance all these criteria. So we have to balance the ductility, we have to balance the hardness, we have to balance the brittleness, and we have to balance the strength. So that martensitic stainless steel material will be having more hardness and more brittleness. I am going to decrease the hardness and strength, decrease the hardness, strength, and brittleness of the stainless steel material and compromise it with the ductility in order to have a balance of wear resistance. Recently, I have done all these works in ISRO ISRO. As I did my PhD work in ISRO, I have some contact details with ISRO people. And recently, I sent all my students to Indian Space Research Organization, Trivandrum. They have gone over there and they have got all those results. That results made me to publish this paper in this conference. These are all my students who are standing in the picture and myself also in the middle. And these are all the various equipments available in ISRO where we will be unable to find in some in colleges. And materials and methods. So there are a number of stainless steel available: austenitic stainless steel, ferritic stainless steel, martensitic stainless steel. And chosen for this research work, I have taken martensitic stainless steel material. We are all thinking that martensitic stainless steel, as it is very high hardness in nature and high brittleness in nature, it is applicable only for manufacturing of cutting tools. Because what we can do with a hardened tool is we can able to manufacture a tool which can able to cut any other metal. We are thinking like that, but this martensitic stainless steel can also be compromised with the ductility so that it can be used for manufacturing components for high load and high speed application. So chosen for this research work, I have chosen a martensitic stainless steel material as a challenging for my research work. And if you see the composition of a martensitic stainless steel, the carbon percentage will be roughly around it will be around roughly around 1.30 to 2% of carbon. Iron content will be roughly about 80 to 85%, and the remaining percentage will be on alloying elements like nickel, chromium. Chromium will be about 11%, and the remaining will be about nickel, molybdenum, manganese, sulfur, and phosphorus for about 1% or 2%. That's all. And chosen for this research work, what I have done is I have taken the sample and I have taken the sample in the dimension of diameter 8 mm and length 40 mm. And as I have made use of a pin on disc wear testing machine for conducting the wear test, I have to prepare the disc as well as I have to prepare the pin. The pin sample I have taken the diameter of 8 mm and length of 40 mm, and disc I have manufactured for 100 mm and 10 mm thickness. And the disc will be hardened to a saturated level because I'm not going to bother about the wear on the disc. I'm going to bother about the wear on the pin material. That's all. And the process that I'm carried out are hardening and tempering process. We know about hardening and tempering. Tempering is a reheat treatment process of a hardened metal, so that, see, in hardening, what will happen normally? Hardening, from the name itself, you can tell hardening is nothing but used to harden a metal. But after doing hardening only, we can able to do tempering operation. Directly, it is not possible to do the tempering operation. Tempering is a reheat treatment process where a hardened metal will be taken and it will be reheat treated in order to compromise the ductility, in order to promote ductility on the material. So first we have to do hardening process, and later on we can do the tempering process. And these are the things I have done. Wear test I have done by using pin on disk wear testing machine. Later on I have measured hardness testing with the help of Vickers hardness testing machine. Then I have taken optical microscope test results for measuring the case depth of the material. Then I am going to conclude the paper with scanning electron microscope results. And these are the results I got it for case depth. So I have taken four samples actually. Four samples in such a way that sample which is the first specimen will be an untreated one, untreated 630 material. And the second material is for vacuum hardening and tempering done for 1 hour. And the second sample is for vacuum hardening and tempering done for 2 hours. And the third sample is done for vacuum hardening and tempering for 3 hours. Actually, it is 630 material, not 416, 630. So in 630 untreated sample, I found to have a case depth of 19 microns, because that is untreated material which is having high hardness and high brittleness in nature. After doing this tempering and hardening process, my objective is to decrease the hardness and brittleness of the material, so that I can able to compromise ductility on the material. So in the first sample, which was treated to 1040 degree, 2 hours sample, I have decreased to 16 microns. Then in the second sample, which was treated for 120 minutes, 2 hour sample, I have got a case depth of 12 microns. And in the third sample, which was treated to about 2.5 hours, I have got a case depth of 8.5 microns. Thus, H is nothing but hardening by vacuum tempering. Both will be combined, both will be done together. Vacuum hardening process and vacuum tempering process. And coming to the SEM images of vacuum hardening sample, if you see, for the untreated sample, we were unable to find out anywhere, because that is very hard in nature, very brittle in nature. We were unable to see any wear. We were unable to see any wear on the specimen. But on the other three specimen, we have found out some wear was there, because as I have decreased the hardness and brittleness of the material, the specimen has started to wear on the third picture. You can able to see on the third picture. All these white color layers are nothing but they are all the peel off material, where it is obtained because of abrasive wear which occurred between the pin on disk while doing the pin on disk wear testing process. All these white color layers were found to be the peel off material. So in the first sample, which was subjected to 2 hours, we were able to find only less wear, as it is high hard and high brittle in nature. Whereas in the second sample, it was found to be little bit very high, and in the third sample, it was found to be very high. But the best specimen, what I can conclude is vacuum tempering and vacuum hardening, which was done at specimen number 3, will be the right material with proper ductility, proper hardness, and proper strength for high speed and high load application. That's what we have noticed it. We have also manufactured a blade on for an application of a steam turbine with the help of a stainless steel, and we removed one particular blade from the commercial steam turbine blade, and we replaced with the stainless steel material. We found that the life of the material has been improved. At the same time, there were less wear rate was found to be in that particular blade. And coming to the results and discussion, what I would like to conclude is the hardness of untreated martensitic stainless steel, that is a hardness of 630 grade untreated stainless steel, was found to be 832 Vickers hardness, and whereas it was decreased to 380 Vickers hardness after doing this tempering and hardening process. We found that this 380 Vickers hardness have stabilized the material in ductility wise, brittleness wise, and hardness wise, And in this condition, we can able to manufacture any product of the particular stainless steel, and we can install to the application so that the material doesn't get corroded, and the life of the material is found to be very high. Strength has been improved on the material, wear resistance also improved, and case depth also it was decreased from 19 microns to 8 microns. AISI 630 material was found to have 19 micron of case depth, and by doing this hardening and tempering process, we have decreased to 8 microns, which stabilize the material in all the states, in all the conditions. And the life of the material also we found to be increased. We have already replaced one particular blade on the steam turbine blades. We have replaced one blade, and we are continuously monitoring that blade. Till now that blade didn't get wear. Till now we have installed it 1 year before. Till now it didn't get any wear. We also checked the hardness of the particular blade. The hardness was maintained to be the same as 8 microns. 380 Vickers hardness is there. Still that blade is running. We have made it in the application. And these are all the references that I came across in making the paper. Thank you very much for giving me this opportunity to present the paper in front of you.
Thank you, sir. Your presentation is open for question.
Yes, sir.
I request to all the participants to ask the question. Dr. NK Sharma.
Yeah,
Sharma,
hello.
sir.
Yeah. See, I have one question.
Yes, sir.
So can I ask you, what is the annealing temperature and time you preferred for these samples?
Yes, sir. An annealing temperature, normally we prefer 725 degrees centigrade and above.
725 degrees centigrade.
Centigrade and above, and we will be going with a slow cooling process.
After that,
yes,
annealing. But
yeah.
how much is that? How much is the annealing time you preferred? Means your sample were found to be good.
Sir, normally 4 hours. Sir, it varies from company to company.
No,
because
I'm not talking about. I'm talking about your sample.
Yeah. 4 hours, sir. Normally 4 hours.
4 hours you annealed at 750.
Yeah. Yes, sir. Yes, sir. Yeah.
And after that, cooling was quenched or slow cooling?
No. It's a slow cooling process.
Slow cooling at what rate?
Slow cooling process in the sense, normally we will keep the cooling inside the specimen, inside the furnace itself, sir. Once the specimen have reached 725 degrees centigrade, we will switch off the furnace. Roughly around it will take some 7 to 8 hours for cooling. 7 to 8 hours.
Okay. This is quenching.
Yeah,
this is quenching of the sample. It is not slow cooling.
No, in my project, I have done hardening process actually. After reaching that 725 degrees centigrade, I have used a quenching media of water, which has taken roughly about 10 to 15 minutes for immediate cooling process. Immediate
cooling. But in furnace cooling, that is furnace cooling. But you did not maintain that constant rate of cooling.
Yes, sir. Yes, sir.
Yeah, that I wanted to know, because initially when the temperature is 750, the cooling rate was high when you switched off the furnace, and later on, as soon as you are coming back to the normal temperature of the atmosphere, the cooling rate becomes less. So your sample were not cooled uniformly. That I wanted to know.
But here I didn't undergo with annealing process. Directly I went to hardening. After once the specimen have reached 725 degrees centigrade, I have taken the specimen. I have done immediate rapid quenching.
Right. Correct. Okay. Thank you.
Sir. Yeah. Thank you, sir. Thank you, sir. Thank you, sir. Yeah.
Okay. Thank you, sir. May I request to examiner to ask the question?
Hello, Dr. Ram.
Yeah. Yes, sir.
Basically, your work is related with mechanical properties of steel.
Yes, sir. Yes, sir.
Right, treated with different experimental conditions.
Yes,
what
sir.
about elastic properties?
Sir, in stainless steel, we won't be having the property of elasticity, sir.
No, elasticity means Young modulus, rigidity modulus.
Yeah. Actually, I would like to discuss about Young's modulus here.
Yes.
The strength has been improved after doing this heat treatment process.
So actually, you should go for that one, because ductility, brittleness, everything you can able to calculate with the help of these parameters.
Yes, sir. Yes,
rigidity, elasticity, and bulk modulus.
Yes, sir. Yes, sir. Definitely.
So that you should go, because you are a very senior person.
Yes, sir. Yes, sir. Yes, sir.
Correct?
Definitely. I will go. Right. Sir. Fine.
Okay.
Yeah.
Thank you. Now, may I request to examiner sir to, there are three participants who are facing their problem for internet connectivity.
Tomorrow will.
I think sir will announce about that one. Dr. Ashok Pandit sir will announce it. Now, may I request to Pandit sir to cast the vote of thanks to examiner. Hello.
Please unmute my video.
Okay. Okay, sir. Sir.
Hello. Hello.
Sir, you are audible to all. Okay. You may start.
First of all, I would like to express my thanks to the examiners, particularly the Nathuram sir, KB Modi sir, and Kurumude sir, for giving their valuable time for examining the oral presentation. The first of all, I would like to request the examiners. The three paper presenters are left, and already the time is very late. So, may I request you, the remaining paper presented, can we give them an opportunity tomorrow in the morning session? Modi sir, Nathuram sir, and Kurumud.
From my side, no problem.
Yes, sir.
Okay.
Kurumude sir and Nathuram sir, may I request you, have you a time in the morning session? Yeah. Okay. Okay, the remaining three persons, paper presenter, we will give a time in the morning session after the first invited talk of Dr. B.R. Sankapal sir, a professor, Department of Physics, VNIT Nagpur. After his invited talk, we will give an opportunity to these three paper presenters. Today, I would like to express my thanks to all the participants, particularly the NR Singh sir, who is now with us to observe the paper oral presentation also. He is spending his valuable time. My guide, Dr. K.M. Jadhav sir, he was also along with us. And these all invited speakers, they have not only delivered their lecture and go away from the conference, but they are continuously joined with us, and they have spared their time, valuable time. On behalf of our institute, may I thank NR Singh sir, Dr. K.M. Jadhav sir, and our honorable president, Nana Sahib Palodkar. He also gave his valuable time for the inaugural function. Dr. B.B. Kale sir, who has delivered a keynote address and thorough knowledge on nanotechnology. The another speakers who have delivered the lecture, Anurag Gautam sir and Manas Srivastav sir. Our institution is very much thankful to them for spending their valuable time. Yes, and all the participants who are always along with us. Being the program get postponed and prolonged, may I request all of you, tomorrow you may join at 10:30 a.m. Yes, and tomorrow there will be three invited talks. B.R. Sankpal sir, Dr. Bhishma Pratap Singh from BARC, and Dr. H.D. Dhole sir. And after these three invited talks, there will be the valedictory function. And in the valedictory function, the best oral presenter's name will be announced and they will be awarded. With these few words, I thanks all of you once again. Thank you.
Sir. Thank you very much,
thank
sir.
you.
With the permission of chairperson of this session, I conclude this session, today's session. All sessions are over. And I request to all the participants to join tomorrow on as per the schedule. Okay. Thank you. Thank you very much.